Can you open the mic? All right. Is it? Yeah, fine. Well, I'd like to give you a very warm welcome to this first installment of FProPer, or if you're cheeky, FProPer. The idea of this workshop is to bring together productivity and performance. And when I was mentioning this to a colleague of mine, he said, "Oh, but don't we all do this? Isn't this what ICFP is all about, right? Productivity and performance." And although I agree, obviously I agree, I was a little bit flabbergasted what to reply to this. And I said, well, but there are different levels of performance, and there's a good reason why this is actually a follow-up on the previous workshops that were called FHPC and then FHNP. See, this is why we had to change it. Anyway, so the idea is that we have productivity, yes, and high levels of productivity, and performance, high levels of performance, but not necessarily HPC per se. So we're interested in all kinds of applications. We're trying to broaden the audience. And actually, let me introduce Mike Rainey. He's a co-organizer of this workshop. So any blame to me and any praise to him, please. Then without further ado, I'd like to introduce Dominic Orchard. It's an absolute pleasure of having him here. He has graduated, he has done his PhD in Cambridge, as I learned today, to my surprise, quite a few years ago. Then he has been moving around, mainly nowadays between Kent and Cambridge, as you can already see from his affiliation. And also, if you look at his title, you can see he has done quite a bit of a journey. I always thought that he has a very theoretical background, and I'm sure he has. But he has always seemingly also been tempted by the performance aspects of it. So I'm really glad to have him on this title, From Sea to Comets to Climate. Take it away.
Great. Well, thank you so much. Absolute pleasure to be here. Thank you for having me. Some people know me for graded modal types and the granular language and things with linearity and taking inverses of types and all these kind of things. This talk is not going to be about that at all. As I said, it's going to be somewhat of a journey thinking about array programming, and I've had a sort of a leitmotif, a kind of a cycle, a brain worm going around in my brain for about 20 years now, and I seem to keep coming back to a particular programming pattern, and so I'm going to be talking about that and my journey through that and the sort of the work I've done around that and where that's led me today. So, cycle 0, the origins, going back 20 years, back when I had much shorter hair. I think it's like the inverse, most people have sort of long hair when they're younger and short hair when they're older, but I had really short hair back when I was an undergraduate, and I was obsessed with C and low-level programming and assembly language and hardware design, and I spent all my time thinking about that, and I had lots of arguments with my roommate about how, the only way to get high performance is to write C code and assembly, and that's what you've got to do. And he was doing this thing called Haskell, and I was like, yeah, it's so slow, man. You could write C code instead. So I did change my viewpoint eventually, but I was still really enjoying C at the time, and I did a high performance computing course in my master's in the sort of the final year, and we were given an assignment which was to take this fluid dynamics simulation. So it was a discrete approximation to the Navier-Stokes equations, equations of fluids, and the idea was to take this C code and to parallelize it and make it faster. That was basically the assignment. And so we had learned various things in this course, and one of the ideas was that, okay, we could take this computation, which operates over arrays, and do domain decomposition. So you split it up into smaller parts, and you compute those in parallel, and there's some kind of communication that has to happen between the parts, and this is the way to chunk it up to get some speed up based on data parallelism. But it was using C, and we were generally sort of told, okay, you should keep it in C and use MPI, so use the message passing implementation to send these rows between the different processors. And I enjoyed this course. I thought, that's great. And I said, OK, I'm going to do two-dimensional domain decomposition, where you split it up across multiple dimensions, so you have to kind of communicate with not just people to the left and right, but also top and bottom. And I thought, that'd be really easy. Was that easy? So I started down this road, and I was trying to do this 2D thing in C, and it just kept not working, and the results were just wrong repeatedly and repeatedly. So with 1 day left until the deadline, I sort of gave up and said, okay, right, I'm just going to start again and just do a 1D, one-dimensional domain decomposition. And okay, I got that working in a day and submitted it and passed. But this was an experience that really stuck with me. At the time, actually, I was getting really, really into functional programming, and I did my bachelor's dissertation, and everything was written in Haskell. But I thought, this is going to be easy doing 2D domain decomposition in C, because I'm a really good C programmer, and it turned out to be very hard. And this was a sort of a formative experience in cycle 0. Now, at the heart of computational fluid dynamics is this pattern, this programming pattern known as a stencil computation. So in a stencil computation, you have some array of values. Here I'm going to call it A. And you loop through that array. Okay, forgive the imperative code down here. We're going to have various bits of code, imperative and functional, throughout this talk. You compute some values of a new array, and you do that based on some small neighborhood of elements around at each position. So if I'm going to compute the position at ij in the array B, I do that from A at ij and some small neighborhood around that, and I traverse the entire array to compute this output. So think the Conway's game of life, or blurring an image, various sort of image filters. But this also comes up in lots of numerical simulation, scientific computing kind of contexts as well. And that's at the heart of these computational fluid dynamic simulations, is a load of stencil computations. And so, okay, if this talk is about my journey, I'm going to fold space-time for the moment and go to the sort of the end part about climate, because fluid dynamics is really important for Earth system models and climate models. The atmosphere is a fluid, the oceans are fluid. That the core of climate models are fluid dynamics simulations. So in this diagram here, it's a kind of like a process model diagram. You've got this bit that says advection up here in the atmosphere and advection down here in the ocean. Advection is the bulk movement of fluids. And the way the core of the climate models is to solve some equations of state for the atmosphere. Conservation of momentum, mass of viscous fluids is basically the Navier-Stokes equations, and that's at the core of our climate models. So inside of all of these is these kind of models is a lot of stencil computations then to compute the movement of fluids in the atmosphere and the ocean. So we'll come back to that, but at the time I didn't really think very much about that in cycle 0, but this lesson was lodged in my brain. And of course, you have to then do this over three dimensions on some kind of grid representing the whole Earth. So let me just show you bits of that code. Has kind of, hopefully you can identify there's a sort of stencil computation things in there like this. This is computing some the pressure equation and okay, updating velocity. It's getting a little bit funkier, this code. And then you get these really kind of complex kernels which just have lots and lots of array indexing terms in them. And then, oh, look, there's another one that looks almost identical, but is actually different. And they're quite sort of detailed bits of code, really, in these fluid dynamic simulations. So, you get the hang of it eventually, but writing this from scratch at the beginning is a little bit tricky to get right. Just a little plus or minus or an I and a J and a 1 in the wrong place or the wrong variable can make everything go wrong. So we'll come back to that, though, in a future cycle. So cycle 1, DSLs for stencils. This was now fast-forwarding a bit to my PhD, lots of late nights and pizza, and I had sort of moved on from those kind of things, or so I thought, until I was sitting in a seminar one day. I think it was in the first year of my PhD, and I think it was not I can't remember where it was, somewhere in Cambridge, but it was someone who was from a scientific computing background. And they were talking a lot about the optimizations they had done to their code to make it a little bit faster. And it was lots of really clever stuff. It was lots and lots and lots of hard work. And we got a little bit of speed up. And I'm sitting there in the audience thinking, is this right? Okay, I wasn't exactly thinking we need more lambda, but I was thinking surely there's something that computer science can bring to this, that programming languages can bring to this, and functional programming. We should surely be able to build some kind of functional programming languages or DSLs for scientists that helps them be really productive, not spend all of their time sort of optimizing low-level C code or Fortran code, but that lets them just express the intent of their equations, intent of their solution, and then have it produce really fast simulations that you can retarget. Surely that should be possible. Why don't I have a bit of a think about that? And so I started writing down what I saw of all the kind of problems that I saw in these kind of approaches in scientific computing. Manual parallelization, it's difficult to express, it's error-prone, it's hard to debug. I had a week of not sleeping and eating lots of Doritos trying to do that. Imperative programming languages have a high potential for producing incorrect parallel programs. That was sort of what I deeply felt from my experience. Then often what you end up with is really hardware specific. You've really tailored it to the particular hardware architecture that you're going to sort of deploy it on. And then, okay, maybe there are some automatic parallelization techniques, but in principle they're undecidable, and then they can be really unpredictable. Like maybe your code's really fast one day, you change a little thing, and then it's really slow, and you don't know why. And I was sort of getting this impression that all of these indexing operations were kind of, in the C code, it was very general. You could kind of write anything in the indexing operations, and actually, if only we could just sort of corral things down into a very fixed kind of patterns, which is what I could observe in the sort of code that was around, then we could sort of cut out some of the noise and make the analysis or make the DSL much more fixed onto the problem. So these issues I actually took from a paper that we wrote after I had done some thinking about this, and this in sort of somewhere towards the sort of middle of my PhD, we published this paper about our DSL for doing productive and performant stencil computations. It's called Hypnos, which is a sort of rendering of the Greek word for sleep. You can ask me about why it's called that later. But the idea was to try to solve these issues and have a DSL that kind of dealt with these things. And there were kind of two key innovations that I'll talk about. One was using comonads, having a comonadic interface for arrays, and I will explain what that means, and also having a sort of special syntax and special way of accessing arrays, not just these I+1, J-1 kind of indexing operations, but something that's really quite novel, I think, and abstract, that's sort of decidable to analyze. So at the core of the DSL was the concept of a grid, and a grid is an array paired with a cursor, which is like an index into the array at some point. We sort of had this multi-dimensional grid type, which contains this cursor. Now, I had been getting really into some category theory things, and I've been thinking a lot about data flow programming and comonads, and I sort of realized, there's this pattern here, and it's exactly the shape of this comonad thing that I've been playing around with in other areas. So a comonad is, it's a data structure which has some operations, and those operations need to have some laws. If you know monads, think you're going to be sort of flipping the direction of arrows. If you don't know monads, well, don't worry about it. Hopefully, you can just sort of follow along with what I'm describing. So the data structure here is going to be this grid thing. It's an array paired with this cursor, as I've said. So the array is indexed by some type A. It contains things of type A. Indexed by I contains A's. And a comonad has an operation, which is called the extract or co-unit operation, which says I can go from a grid A to an A. And how do we do that? Well, the laws force you, there's some associated laws which I won't go into, but they force you to, in this particular instance, to index the array at that particular position. So you're sort of extracting the element that's at the cursor. Okay? And then you have this operation called co-multiplication, which I write as delta, which has to be as follows. You take a grid, and then you produce a grid of grids. Now, these grids, these internal ones, are sort of localized at the position in which they reside. So if you look at this one in the top left, you can see its cursor now is also in the top left. And if we look at the one to the right of it, its cursor is one along, and so on. So it's sort of copies of this grid where the cursor has been moved to every single position. And then that's represented itself as the entire grid with your original position highlighted. So this is a sort of like expand the context into all global contexts, and we'll see why that's useful for stencils in a second. So these grids, they're also functorial. That means that we can take a function from A to B and lift it to a grid of A's to a grid of B's. This is the sort of fmap operation in Haskell. And this is, point-wise transformations on a data structure. It's something we want to do lots and lots and lots of times. But stencil computations are more general than this, because we don't want to just take in a single element A. We want to take in a whole neighborhood of elements that are around the cursor. We want to get that like local neighborhood. You want to compute how fluids move based on the neighbors around it, for example. And that's what's provided by this structure. So the co-bind operation, this is sort of using the Joule's terminology for monads, but the co-bind operation gives you something that looks a bit like fmap, but instead of an A to a B, you're taking a grid of A to B. So you can see this function here, f, as something that's sort of localized at some position, a grid of A's, and from that you're going to compute a B. So this is like a description of the computation at some position. It's the local computation. You're going to run f, and you're located at some cursor, and you're going to look at some neighbors around you and compute a B. And what cobind does is it lifts this local computation to a global computation. It runs the whole thing over every position in your array and reassembles this new array at the end, which is your array of results. So the cobind is taking something local and applying it globally and doing this traversal. And this cobind is derived from that delta, that co-multiplication I had on the previous slide. So what's the derivation? You've got this f, it goes grid A to B. What you do first is you start with the grid A and you do your delta, which then sort of copies that array and localizes it, and then you apply f to every single position, so you sort of map over it, apply f at every position, so you're applying it to every localized point, and then you're assembling that into the output grid. And okay, you don't have to derive it in this way. It's actually more efficient to just write the cobind operation directly yourself, and that's how it works inside of our DSL. But this is the core of the stencil computation pattern. You have this local computation, and then you apply it at every position to compute the new global result. So that was a kind of discovery we had during this project, and it became the sort of the core backbone of the Hypnos DSL, that you write stencil computations, and then you have these combinators based on the comonad and some other things that plug them together, and inside this cobind is where all the interesting action happens with parallelization, because the cobind operation then, if we go back a bit and we can just look at its signature on its own, that's the place where you're traversing the array, and that's where you can then do the domain decomposition. You can have particular hardware implementations and split it up and actually get the parallelization. So the idea was to follow this kind of long tradition of skeletons, parallel programming skeletons, and have these combinators which do the work for you, abstract it, and you just have to write your little local computation. So that was sort of innovation one in the design of the DSL. Innovation two was to deal with these pesky indexing things. And me and my colleague Max Bolingbroke, we had many late nights in our office and just sort of talking about things. And we hit on this idea, which was kind of crazy, but sort of made a lot of sense, which was to use pattern matching to deal with indexing and actually throw out the concept of indexing altogether. So we have this thing called a grid pattern. This is code in Hypnos. It's a pattern match on the left-hand side, and what you're pattern matching on is a grid. But this thing here is a grid pattern between the pipes, and it has this at symbol C, and when you're pattern matching on a grid, what this does is it applies that co-unit operation of the comonad. It extracts the position at the cursor. So C gets bound to the element pointed to by the cursor in that grid. So it's like doing C is equal to AI, where I is your current position in the array. And then if you write a pattern to the left of that, it binds that left of the cursor, and if you write a pattern to the right of that, it binds that to the right of the cursor. So it's like saying L is A index at I minus 1, and C is at I, and R is at I plus 1. And we thought, oh, this is cute. Of course, there are 2 dimensions in text files, so let's make a 2-dimensional version. Oh, sorry, that's in a moment. Okay, getting ahead of myself. Let's just actually write, okay, this is the Hypnos code for taking a grid in dimension X. This B is to do with boundary information, which I'll mention at the end. But okay, this is just a simple kernel that takes those neighbors and averages them. And so I can take my run combinator in Hypnos. This is the cobind, and it applies it onto that grid. Now, there's a little bit of stuff around here. This B is to do with the boundaries, and this particular version deletes the boundaries. So if you want to just iterate inside the interior of an array, and if you're going to change the type, so everything in the array starts off as type X, but you're only processing in the interior and converting things to Y, well, now you have to throw away the boundary because it has the wrong type. But then there's a version of it called run A, where everything has the same type, and this can deal with its boundary, and we can preserve the boundary at the end. So there's some kind of, some subtleties to do with boundaries, which I'm not going to talk about today, but we had a lot of fun working that out. Okay, so the key thing is you write your stencil, like F here, and then you use the run combinator to apply it. So that's 1 dimension, but of course there are 2 dimensions in our files. So we can have a 2-dimensional pattern match as well. So this is the sort of Laplace, is this Laplace? Yeah, the 2-dimensional discrete Laplace operator. And we've got this grid pattern that's now in 2 dimensions. So if we go 1 line above the cursor, then that's going up. That's sort of -1 in the Y dimension here, and the B is +1 in the Y dimension. And so based on the lexical layout of the grid pattern, that's determining how you index the array. And the key thing here is that the shape of the patterns is completely decidable. It's very easy to statically determine then the shape of your access. There's no general expression to analyze. The programmer isn't tempted to do some kind of something more complicated. It's just captured there in this very abstract form using these grid patterns. And that was the sort of key idea we had there for making things very decidable and predictable, so that there wasn't any surprises. Now, there's other things that you want to do then to get increased performance. So one of the particular kind of grids that we had is a double buffering kind of grid setup. So this is when you read from one array and then you write to another, and then after you're done with that, you swap them around. And this can be captured by a comonad as well. So you have a pair of a read array, and I've called this I array for sort of immutable array, and then a writable array, an M array, a mutable array, and then a cursor. So you've got this pair of arrays. And again, the cobind operation is going to give us access to read from the I array here, but it's going to write its results into the M array and then freeze the M array at the end and thaw the I array and swap them around. So kind of swap the role of the immutable and mutable inside after one of these cobind operations. So we had a whole bunch of other kind of crazy stuff in Hypnos as well, where you could pattern match in time, and you could talk about the temporal dimension, and again, that was static, so it would know how many I arrays to allocate. So if you were looking 2 time steps back, then it would say, okay, what you need is 2 I arrays and 1 M array, and that was all statically determined because we reused our grid patterns to match in a special dimension T. So you could do these windows back in time as well, and then it would give you the right comonad. So the general idea, though, is that we wanted to sort of hide these kind of optimizations all inside of our comonadic interface, hide them behind that wall so that you don't have to mess around with doing mutation and things yourself. And then we did have ideas about like all of these really cool optimizations that exist, like stencil tiling and space filling curves and all this kind of stuff, but we never got to that because I got distracted into co-effects and graded modal things, and then the cycle died out. But I think there was a lot of cool stuff that we could have done there, actually taking it and making it really even higher performance. As it was, the sort of performance gains were a bit more modest in the sort of 5 to 10% kind of improvements. So we implemented this atop Haskell, and there was a lot of cool stuff trying to figure out how to do that as well. So there was a little bit of syntactic. The patterns got desugared into these indexing operations, and we had this way of leveraging the type system in Haskell to talk about safe indexing. So I'll use the cursor here. So a lot of stuff you have to deal with is the boundaries and making sure you don't get out of bounds access. That's another kind of bug that you can have when you're writing this kind of code. So we had a whole system for expressing boundaries. That's this information B. And then when you're indexing at I, you generate this predicate that I has to be safe with respect to B, so you're sort of not going out of bounds. But all of this is handled automatically by Hypnos because the grid pattern tells you the size of your kernel, so it tells you how big your boundary needs to be. If your stencil looks one to the left and one to the right, okay, then you need a boundary of size 1 on the left-hand side and a boundary of size 1 on the right-hand side. So then when you're constructing this thing, you have to provide that boundary information. It's sort of all handled automatically, and then it's desugared in Haskell into these indexing operations, which use some sort of lightweight dependent typing, and this predicate checks the safety, and we sort of proved that that was all sound. So you get this sort of, if you look at the sort of the Haskell code, you get these sort of predicates stacking up and saying, okay, for this little kernel, this little stencil, where you're looking positive 1, positive SZ, so that's positive 1 in one direction and negative 1 in another, and positive 0, then those need to be safe with respect to the boundary. And that, in this function, the boundary is polymorphic. So for any boundary, as long as it has enough to not cause some kind of out of bounds errors when you run this. And as I said, we did do some kind of performance benchmarking, not as much as I would have liked. As I said, I sort of got distracted into the more category theory stuff in the rest of my PhD. But there was some sort of nice ideas there, and okay, I worked on it for a bit, and then the cycle sort of died out for a little while. Now, again, I'm going to go nonlinear. Nonlinear dynamics and nonlinear storytelling. So I actually came back to the comonads for stencil computations kind of later, because I had been thinking about the fact that there's these laws that you have in a comonad. They kind of look a bit like rewrite rules. You can turn them into rewrite rules, and they correspond to some kind of optimizations that you can do to your code. So I think one of the things that I often think about category theory and using it in programming, it's, okay, there's a bunch of sort of useful design patterns here, but also the laws not only tell you what to do, and you can sort of generate tests from them or do proofs with them, but often some of the laws kind of encode optimizations as well. And I wanted to sort of understand exactly how that was true and actually really formalize that. So I did some work, which is really not well known at all, where I looked at these kind of container functors and comonads. So with the stencil computations as comonads, you could then think about doing other data structures like graphs or trees or things like that, as well as arrays, and you can sort of generally categorize these as container functors and container comonads. And I looked at generalizing sort of well-known kind of optimizations and how they come out from the categorical laws. So if we looked at this code on the left here, we'd say, okay, this is a silly piece of code. We've got this sort of inner loop that we kind of repeat because of the outer loop, and so we get some n squared thing going on here with the kernel f, plus then the outside of g, and of course you can just pull this out and go from a quadratic to a linear. Turns out that this corresponds exactly to one of the comonad laws about embedding in associativity. So I won't say more about it, but this paper sort of really looked at that categorical side and showed that some of these laws corresponded to asymptotic improvements in your code. And so in Hypnos, we turn these into rewrite rules for Haskell to sort of say, look, if someone's written things in a silly way, you should really sort of optimize them using these laws. And finally, sort of years later, I did the work to show that those were not going to make things asymptotically worse, that actually they were potentially optimizations. But I don't want to say more about that. I want to go into the next cycle. So I went and did a whole bunch of other stuff, but this kind of array programming and stencil computations was, again, lodged in my brain. And I finished my PhD, and I there was an academic at Cambridge who I'd spent lots of time chatting with, and he had been sitting down in college and talking to various scientists. And the way that it works in Cambridge and Oxford as well is that you have these colleges where you've got people from all disciplines sort of situated at this place where you kind of go and eat lunch, and students live, and the general thing is that you go to lunch and you sit down next to the next person at the table. You don't go and sit with your friends. You just find the next spot on the table and you sit down and you turn to the person next to you and you say, oh, how's your day going? What are you working on today? And then you have a conversation. He was having these conversations with the other fellows at his college who were saying, oh, I'm working on these kind of plant, these biosphere models, but I can't get it right, and I think there's bugs in my code. And he was like, oh, bugs in your code, well, maybe we can help with that, and maybe we should have some conversations. And he came to me and said, oh, I'm having all these interesting conversations with scientists, and they're having problems writing code, and they're interested about whether computer scientists could help them write better code. And I was like, well, yeah, I think we should be able to do that, right? So we started having these conversations with the scientists, and about correctness, and I'm going to move around a bit. And we said, well, in computer science, there's been all this work on programming languages, been all this work on verification. There's all these amazing results of verified pieces of software. Would you like some of that? And they're like, oh yeah, that sounds really great. And we said, okay, cool, right. So there's this theorem prover. You need to know about first-order logic and dependent types. And what? We don't know anything about that. Oh, okay. So what do we do then? So we're thinking, we've got all these great results in PL and verification. How could we possibly get some of these things into the hands of scientists? So we started a project trying to do this, trying to bridge the gap. And we thought, well, let's actually look at what you're doing. Let's sit in a bunch of your meetings. Let's look at your code. Let's talk about it and see how you develop things. And okay, you use Fortran. Didn't think about that so much at the time, but maybe we should start building some tools for Fortran then. And I was going back to then thinking about, I was seeing code that was like this again. I was like, oh no, it's these really complicated fluid dynamics things that I really struggled with. This is C code, sorry, I should switch to the Fortran. But I have a Fortran version of this as well. And yeah, this stuff's really difficult. How do you get this right the first time that you write it? I had first-hand experience of getting this wrong, very wrong. Lots of times. So we started thinking about array programming again and this stencil sort of pattern. And I have been saying oh yeah, stencil computation is really important for science. I think it's really important for science. So we sat down a bit and said, okay, let's actually get some evidence for that. So we did a bit of a kind of a study on code. So we took a bunch of packages. They ended up all being climate science related, really. The is the UK Met Office Unified Model. It's an amazing piece of software. It's a climate and a weather model used all around the world for both climate predictions and weather predictions. E3ME is a kind of mixed climate econometrics model. Hybrid 4 is a land surface model, which is then used in other kind of climate scenarios. GeosChem is a general atmospheric chemistry model. There's the old Navia code, the fluids, some libraries, and some stuff that went into more like geodynamics and things. So we sort of took these and said, let's build a static analysis that looks at how arrays are used in this code. It's about 2.5 million lines of Fortran code here, and we built a lot of tools for analyzing Fortran. And I sort of had this idea of, well, if we could, first let's get some evidence that this is a sort of common pattern, which I think it is. And then if it really is, and I think that there are always these kind of very regular things. Okay, we switch to Fortran now. I think there are always this very regular shape, and that was one of my assumptions in Hypnos. That was one of the things I was positing, oh yeah, stencil computation is always really regular. That's why we can do grid patterns. Instead of having a grid pattern, there should be some sort of very abstract way of describing this shape. So I was thinking, okay, here it's really you're just describing a little rectangle. and it's a sort of a centered thing, it's symmetrical, and it has depth 1, and it's in 1 dimension. So I wanted to design some sort of specification language, which in some ways was really like the Hypnos idea of just using the regularity, but writing a specification that's not like the code. You know, if you write a specification that's the same as the code, well, you'll just get the specification wrong as well, right? So I wanted a specification that was radically different to what you wrote, but then that captured the same information. So, okay, I think my slides are in a slightly wrong order. We did the analysis. There were tons of stencil computations everywhere. Like 50% of the array computations were stencil computations with a really regular shape, and it was a huge amount of the code base. Okay, so we started designing this specification language. So this centered description, as I said, it captures this kind of pattern of -1, +1, again, going back to this idea. Sometimes you have these kind of biased stencils, and it comes from doing the numerical analysis approaches. And in numerical analysis, you call this a forward approach. So I call this forward to a depth of 1. You're not looking at -1, you're just doing I and I+1, and then there's backward, going the other way. And then sometimes you're just looking at the single one. This is like the super simple case, so we call that pointed. You're just looking at that single point, back to the kind of co-unit of the comonad. And then, of course, depth of 2. And we also noticed that sometimes you get this sort of non-pointed version, where you have that part, but you're not looking at your current value as well. So we saw that as well. So, okay, well, let's put that in as a sort of modifier on these specifications. Now, that's 1 dimension. So you've got this sort of 1-dimensional descriptors, but you also want to combine these together. So we have these region combinators, combiners, multiply, and plus. So what do they do? So let's say I have a centered dimension 1, depth 1 description like this, so it's kind of capturing this kind of pattern. You can then multiply it by another specification in dimension 2, and it takes the sort of Cartesian product of those 2 specifications. So it gives you this box of 9 elements like this. So it corresponds to code that might be like this, kind of capturing all of those indices inside. Okay, and what do you do with plus? Plus is just sort of unioning the 2 things together, sort of overlaying them. So to get the classic 5-point stencil, you first describe a centered in 1 dimension that's pointed in the other. That's going to give you something like that. Plus centered and pointed in that dimension, and that describes the classic 5-point stencil, which is at the core of Conway's Game of Life and lots of other kind of bits of code. So this kind of scary, we're on the Fortran version now, great. This kind of fiddly, complicated looking thing is captured by these 2 specifications. So we see that U has the 5-point stencil, and V has this kind of forward-backward thing. So it's like a little box, 2 by 2, oriented non-symmetrically, and then the other loop does something which kind of gives us the other side. So I thought, okay, that's great. That's a nice sort of simple specification that you can start with, and then you can write this, and it's going to capture potentially capture some of those bugs. So the tricky thing is, how do you evaluate these kind of approaches? I mean, we had generated a load of evidence that these were common patterns. And okay, here's the thing, I think, okay, so we could run our tool in both a checking mode and an inference mode. So given a specification and some code, you could say, does the code correspond to the spec? You could also give it some code and say, infer the specification. So within our 2.5 million line corpus, there were essentially this number of specifications that we could generate. 73,000 of them were stencil ones. Access is for patterns that are not quite like stencils, but they're things like reductions over arrays. So we captured some other things as well. A lot of them were just really trivial, like point-wise transformations. So the specification was just pointed. A small proportion were just single actions, so also quite simple, and some of those were non-pointed. And then there was a little group of really quite complicated ones involving lots of actions, and then some of them were kind of a little bit more fiddly, and we had to use these approximation operations, which I didn't mention, at most and at least, because there was sort of, actually it's usually just at most that we use, but there was something that didn't fit one of these pluses or multiplies, something a little bit irregular. But our kind of argument was like, okay, this is quite a small percentage, but that's still a lot of code that covers, and these tend to be the really, really critical bits of dynamical cores, really kind of critical solving some PDEs in a discrete way, and they're the really fiddly bits. So if we could have some way to help the scientists write those, then that would be good, and it would be worthwhile. So we thought about how to evaluate this in terms of like catching bugs, because you write a paper about this and then the reviewers say, but have you caught any bugs? We go, well, no, not really, because we don't know exactly what the code is supposed to do, and it takes a long time to sift through 1 million lines of code with some people and say, is this the right specification? Is this the right specification? So I think it was our postdoc, Matt Danish, who had this really good idea. We had access to the version control system for the Met Office, and we said, okay, his idea was to go through the commit history and run our inference mode on the code and look for any places that the specification for a particular piece of code changed between commits, and then filter that by commit messages that had words like bug or fix or something like that. And so we found various examples of places where, yeah, people were saying, oh, there's a bug in this array transformation, and it should be I+1 instead of I. So we saw that because of the change of specification. And sometimes there was one that was a bit like this, where somehow the J and the I were the wrong way around, probably because someone had been trying to optimize it, because Fortran is column major and C is row major, and often people writing Fortran code get it the slow way around. And actually we have a tool that warns you about that as well. But we saw that there was some evidence that, okay, if you had some kind of way of thinking declaratively first about what the specification is, then maybe that would have helped you. Maybe that would have helped you write the code right the first time. That was at least our suggestion, and I thought this was a neat idea, though, kind of going back over the commit history and using the inference to like look for these places where it could have helped. So this project, we developed this idea, but there was, and we published it in this OOPSLA paper, and it had lots of things about how we analyzed the corpus. We designed this declarative shape specification language. It has lots of like neat equational theory things, and it has a denotational model. That's how we do all the actual analysis. We kind of turn things into some sort of denotational representation, which lets us do equality on these things. And then we have checking and inference algorithms, and we applied that back to our corpus data. But we built all of that into a tool which was called CamFort, which does lots of other things as well. So we sort of built a whole Fortran and static analysis pipeline so that we could then sort of start building these verification tools on top and bring in other ideas. And another thing that came out from this time, so slightly away from array computations now, was sitting down with the postdocs and looking at the code. And I was looking at the comments and saying, oh, this is nice. You've got units of measure information in these comments that tells you about what these arrays and what these values are. And then one of the postdocs said, oh, yeah, but that one's wrong. We said, this guy, Andrew Kennedy, did all this work about how units of measure is a kind of type system, and maybe we could build a type system for you. So we built that in CamFort as well. We built this sort of external optional units of measure typing system for Fortran. So now again, a little bit more Fortran here. This is really simple calculation. These bits in green are comments, and in Fortran you use the bang for a comment, but bang equals is the sort of telling CamFort, this is a specification that you need to parse. It has some semantic meaning. So here we're saying the mass is kilograms, the height is meters, and then potential energy is this thing. And notice that we didn't have to annotate gravity because that can be inferred from all of the rest of this information. And so you can give this to CamFort and say, check that this is consistent, and it says, yes, that's fine. You can ask it to infer things for you. You can ask it to synthesize specifications into the code for you, so you can sort of annotate some things yourself. and then click the, run synthesize mode, and it infers everything it can, and then inserts all those comments for you in the rest of the declarations. It has polymorphism as well, so you can describe polymorphic specifications, and it also has this mode called suggest, which I really love, which is you start with a file with no annotations, it looks at all of the constraints, and it says what's a minimal set of variables which, if you annotate them, we can solve all the other equations. And so then you go and add those declarations, and everything else works out. So we were sort of super happy with that, and we showed it to various people, and we showed it to the Met Office, and they were like, oh, that's nice. But really what we're interested in is checking a bunch of other things about our code. So we had a nice project with them, where they had a lot of internal documents about things that you should and shouldn't do in your Fortran code, and we basically codified a lot of those into sort of static analyses. So that was really interesting. We're still working on this project. Bloomberg have worked with us on this as well. They've been using our analysis pipeline too, and we've been able to work together on that. So that project had a lot of different axons or like kind of tendrils going out of it of different things that we could do, and we're still trying to leverage that to this day with scientists, which I'll come to in a moment. I just thought this was a good opportunity, though. I know this is a functional programming workshop, and I've pretty much shown you I've shown you a mix of functional and imperative code, but I just want to point something out about Fortran. The little double colon here, so, there's this kind of, nice overlap between Haskell and Fortran in using the double colon for typing, which I noticed after a few years. And people are always a bit confused when they meet me and I'm talking about Fortran. I thought you were a functional programmer. But yeah, that's something funny I noticed. So around this time, we thought a lot about, like, how do we do this kind of research going forwards? What's going to be useful? We wrote, Andy Rice and I wrote this position paper saying, basically we need to engage more with scientists. We kind of, in the early days, computer science in its infancy was kind of like a service to science. The computers that universities had were like these things that were helping the scientists, and there was a lot of interaction. And then, okay, naturally computer science developed as its own field, and it kind of pulled in lots of other things, but we sort of lost that interaction with the scientists. I mean, it's still there somewhat, and people do that, and there's things in high-performance computing, but it's not the same as it used to be, and we should really sort of talk to them more. Perhaps we could design new systems for abstraction and specification that are a bit more targeted towards what scientists need. So it's going back to kind of ideas like I'd been having in Hypnos and the things that we did in Camfort. And then if we can provide some tools now that help people immediately, maybe we can have a sort of evolutionary approach where future languages can be designed that sort of pull in some of these ideas from the beginning. Okay, it's really hard to make a new language, and you can't just sort of make a new language and say to people, use this language. It doesn't really work. I mean, occasionally it does, but it's very hard to sort of start a new language. But maybe if we have this evolutionary approach, we build some tools now that fit into the existing pipelines, we sort of gradually move towards some better tools for scientists. So we sort of had this paper where we kind of really set out some of the difficulties and then threw loads of like random ideas into the end of the paper of things we could do. So that was cycle 2. Then I went and did a bunch of other stuff like granular and graded types, but it was still lodged in my brain, and I had kind of started down this journey of working with scientists and was sort of feeling like this is really what I'd like to keep doing. I tried to get various bits of funding to have other projects with scientists, and that didn't work for several years until finally we did have this sort of big score in terms of funding, and were able to set something up, which I'll talk about now. I mean, for a long time, really, I'd been thinking about these problems as well. So if you haven't seen this before, this is a wonderful graphic by Ed Hawkins at the University of Reading, which visualizes the global mean temperature, the change in the global mean temperature over the last 170 years. So the color coding corresponds to change in temperature over an average baseline in this data. We all know that things are getting hotter and rapidly hotter, and we also know that this correlates with a very steep uptick in the atmospheric concentrations of CO2, which haven't been there for a long time, and then we've suddenly, due to our activities, have had caused this massive spike. And you could look at these two graphs and say, okay, it's a correlation, is it causal? But there's been all this amazing modeling work for a long time, and I love this graphic because it embeds so much of sort of human knowledge and human activity. This is from the IPCC, last IPCC report. There's this sort of observed line, so this is time on the x-axis, temperature on the y-axis. The black line here is the observed mean global temperature, and we see that going up along here. And then this kind of brown line in the middle is the aggregate average of all of these simulations of huge amounts of modeling work across lots of different groups, lots of different models, kind of aggregated all together, simulating the world's atmosphere, but including all of the sort of human factors, what we call forcings, inputs into the system from human activities, as well as the natural ones as well, volcanoes and geothermal heating and things like that. And we see that that tracks very closely. Okay, there's this sort of error margin, this level of uncertainty around here. But then if you do the same simulations and you take out the forcings from the human activities, well, then things just stay along here and you get basically not much warming at all. So this gives us sort of very kind of strong indicator that the warming that we're seeing isn't just some natural cycles. It's something that's being caused by our activities. And there's huge amounts of really deeply interesting computation that goes into these kind of graphs. Now, another thing then you can do with models is predict out into the future and sort of do these what called scenario testing. And so there are a bunch of, in IPCC land, there's these things called shared socioeconomic pathways, SSPs, where you sort of look at different scenarios that might going forwards. So net zero by 2050 is this blue one here, and this prediction says, well, if we do that, then our warming will go a bit above 1.5 and then slowly kind of go down towards the end of the century. Dark blue is, we make a really good effort by 2050 and then sort of maybe hit net zero later on in this century, and we go up somewhere about 1.75, and then, these are kind of progressively bad situations where we basically sort of business as usual. 2050, we kind of get really terrified, and then we make net zero by 2100, but that's already pushing up close to 3. Late Cretaceous period, where we've got palm trees at the poles, is somewhere around this region. So that's not a great place that we want to be. So what, as a programming languages person, could I do about this? Well, maybe I should try and help with the climate modeling. At least that's something I could do, and that's something I was thinking about for a long time. And I read this wonderful book which kind of captured it, kind of one of the problems we have, and by Simon Sharp, called 5 Times Faster. It's a really nice book, which I'd highly recommend. Actually, it's both motivating and a bit scary, but also sort of super positive in what it's suggesting. So Simon says, still, our appreciation of the risks of climate change is limited by the way our academic institutions encourage each researcher to focus on their own narrow area of expertise. And that really resonated with me, and this kind of the fact that we weren't talking with the scientists, and I was very fortunate then to be able to help set up this thing in Cambridge called the Institute of Computing for Climate Science. So lots of people are aware of this, that we need to have more interdisciplinary interaction and between lots of disciplines as well, because there's so much that goes into climate science. So we set this thing up to basically maximize the effectiveness of climate science research via all of these different disciplines and sub-disciplines. Climate modeling is a heavily computational field. It always has been. Climate scientists write code day to day, probably at least as much as I write code day to day. It's a core part of their jobs. Advancements in maths, advancements in data science, machine learning, all of these can be brought to help with climate modeling. And we were very grateful to receive support from Schmidt Sciences, who have been funding lots of university research in this area. They have something called the Virtual Earth System Research Institute, where they funded 6 large projects. These are all multinational projects as well, lots of groups working together on various different aspects of the Earth system, trying to advance the state of our understanding and the state of our modeling and the ability to sort of forecast and predict more accurately. So there's lots of really interesting bits of work captured in here, and we're sort of a bit of a hub between all of those projects, and we have a team of research software engineers who work day to day with the scientists in these teams, helping them with their programming, helping them build new models, write data analysis pipelines, have things that are reproducible, have things that are high performance, have things that are well described, that are more easy to share and plug together amongst all the different models. So with the Institute, I kind of see that there's sort of like multiple streams of work going on whose impact happens at different speeds. We've got the sort of immediate impact things with our research software engineers who are doing amazing work. Out of this, we find sort of common problems in which we try and then build sort of solutions like libraries or tools that can help across the different groups in the next couple of years. And then there's the sort of more like open research questions then where I sort of float between these layers, trying to, okay, understand what are the problems, and then think, well, what are the kind of programming language tools and systems that we could build that would help in the next sort of 5, 10 years and so on. So we'll come back now to our global circulation models, GCMs, also called global climate models, and as I said, at the core is the fluid dynamics. That's a big part of the core simulation. And of course, over time, we've been able to increase the resolution of those models. So these are from the IPCC reports. This was the first assessment exercise where the grid squares were roughly 500 by 500 kilometers. And in actually a different graphic here, but it's same kind of information. This is from AR6, so the most recent assessment report. You've got 50 models in CMIP, that's the coupled model intercomparison project. So 50 different models, and you can see the resolution in the atmosphere is sort of going up towards about 25 by 25, 50 by 50, and in the ocean, about 25 by 25. So they're sort of, you get, in theory, you get better predictive performance if you increase the resolution, and that's what people have been trying to do. And in some shorter runs, people can get down to sort of 5 or 1 kilometers now. So there's that kind of scaling up. But when you're doing your fluid dynamic simulations and you've got these sort of grid boxes, there's a bunch of stuff that happens below that kind of minimum resolution, right? If I've got 5 kilometers by 5 kilometers, there's still a load of stuff happening in that has a massive impact on the weather and then the climate. So ocean eddies and clouds. Clouds are a classic one. They transport momentum. They transport energy. They transport water in the atmosphere. And they are typically much smaller than the minimum resolution of our fluid dynamics. So a load of work goes into then writing these what are called subgrid models or parameterizations that recapture the physics going on in those small squares. But often that's a source of error, source of uncertainty, there's lots of approximation, and actually they can still be really expensive, and there might be hundreds of these in a climate model. So there's a lot of work now in trying to optimize those as we sort of add in more and more processes. Doing atmospheric chemistry is really, really expensive, and there's still just so much work to do on the land surface modeling as well, and there's just there's not as much data about that kind of thing as well. So as pieces of software, as I said, these are really interesting beasts. These are graphics that are from this wonderful paper by Naughton and Easterbrook. They looked about 10 years ago now at the software architecture of climate models. Have this really nice kind of analysis of the architecture of these things, and you can see they're sort of you can break them up into components. So CESM is this open source community Earth system model that's developed primarily by National Center for Atmospheric Research in the States, has a sort of big atmospheric component, ocean, land, sea ice, and then this coupler that sort of integrates things, and you've got some other subcomponents in here. So you sort of see how these things break down. But in each of these, you've got a lot of fluid dynamics. So where are people going in climate science? Well, there's been this sort of long talked about thing that, okay, we want to get better prediction, we want to understand what the kind of tipping points are, what the extremes are, and so we need to have more and more processes and higher resolution, sort of climb this ladder to get to this sort of golden egg of sort of very high resolution, everything we can think of in terms of the processes, do data assimilation where we take in observational data, work at multiple scales, and be able to do uncertainty and risk assessment. Now, of course, this involves scaling up computation. We have to sort of scale up the amount of computation that gets done. But I think this also breaks down into some other scaling challenges. One is scaling up collaborations. These models, the large ones, really involve huge amounts of expertise. You've got lots of different kinds of scientists with expertise in oceans and atmosphere, and they have to all come together and talk and build these things together. So that needs to be scaled up. And part of that is scaling up communication, and that's both communication between people and communication with the computer, right? That's programming languages. And programming languages are our medium for communicating with the computer, but they can also be a medium for communicating between ourselves. So, okay, we know that there's a challenge as we scale up the resolution. Okay, we have to do more and more and more work. If we just double the horizontal resolution, okay, then we need 4 times the number of grid points. Then we need to do, if we do that, we need to do 2 times the number of time steps, because we need to run things faster, so we're capturing the propagation of waves properly. So, okay, that's 8 times more computation just in the horizontal, and once you get the vertical in, okay, that's even more. So, you know, it's scaling up the resolution is difficult, and there's lots of really you know, so it's a big data parallel programming challenge, basically. And then you want to be able to try, basically what people do is something called ensemble runs, where they do lots and lots of runs of a climate model, but with lots of parameters tweaked, and like, oh, well, you know, just to kind of, because we know there's uncertainty in it, so it sort of gives us a nice spread of understanding of the kind of, the envelope of what might happen. So, okay, we're probably very familiar with graphs like this, and the climate scientists are well aware of this as well. This kind of slow down in scaling, which is more like the sort of Moore's law scaling, but it's more like Dennard scaling is sort of slowed down. So we've got this sort of single-threaded performance is tailing off. So there's a lot of thinking about how do we exploit the parallel architecture more readily? How do we use GPUs more effectively? I mean, the climate models have always heavily relied on parallel programming, but lots of MPI and OpenMP, and GPU is finally becoming sort of more and more used and exploiting that. But even then, there's a lot of work on actually trying to replace the approximations with something that's higher performance. So there's a lot of really interesting work, which actually seems quite effective, about replacing these subgrid models with something that's data-driven using machine learning techniques instead. So rather than doing some kind of approximate physical model there, you train a neural network on a very high-resolution simulation, or you train it on observational data, or on both, and you replace the previous sort of handwritten model in there with your neural net. And in some places, that has been very effective. You get something that has at least as good predictive power, and in some cases, actually faster to compute with the net than it is to do the original model. Of course, that raises up questions about the generalizability and the explainability. You know, it's trained on some data. How well will it generalize? Can it capture things that we haven't thought of? And how do we understand it? And then there's sort of a bunch of software engineering challenges, which we spend lots of time working on, dealing with building these things and then coupling them back into big Fortran pieces of code. So I think another part of this then, as I said, is about scaling the communication, and that comes down to this programming languages kind of challenge. I think we're all kind of familiar with this idea of there being sort of, in programming, like the inherent complexity of what you're doing, and then the accidental complexity. So I think, you know, I don't think that we should just stick with the current languages that we have in science. I think at the moment, the languages, they don't help us support, they're sort of inadequately supporting the inherent complexity of the models, and then they're making it too easy to introduce this accidental complexity as well. And that's the lesson that I learned writing that C code. You know, the thing that I was doing was inherently complex, and then when I was doing this MPI 2D decomposition, I was just making it more and more horribly complex with my 2D thing, and it was just too easy to then, and then all of those complexities were mixed together and difficult to separate out. So both of these hinder scientific progress. I think only one of these is truly necessary. Okay, sometimes a bit of accidental complexity is going to sneak in, But in the design of DSLs and languages, I think we need to be moving towards supporting this as much as possible and squashing out this one as much as possible. Now, as I think, sure many of you have thought of, and as I was talking about with Hypnos, one of the things was like avoiding the overcommitment to details. So instead, I wanted to leverage the comonadic pattern to let me hide the details and not just sort of make something really specialized to column major order in Fortran arrays with an MPI decomposition. No, let's have something that's more abstract that we can then overload. And this is something that scientists are becoming increasingly keen on and building their own tools for, in collaboration with computer scientists as well. So there's something called grid tools for Python, which is a kind of DSL for writing stencils that tries to give you just this kind of more abstract representation that you can then compile down to different targets. So they've got, they turn the indexing into just these offset vectors that you apply to things. And then they use the Python contextual operation with to do sort of with computation parallel and abstract some of this stuff. So, I'm sort of like greatly encouraged by the fact that these ideas are being used and people are thinking about them and people are really sort of starting to take this kind of thing seriously. And I'm also sort of itching to get a bit more involved because it's like, hey, this is my bag, right? So should try and get involved with these projects and help out. Another thing that's good about trying to avoid overcommitment to details by sort of leveraging overloading is that you can reinterpret bits of code as well. And this is something that people are increasingly doing. So, for example, Julia is becoming really popular in scientific computing. And actually, there's this whole project at MIT and Caltech called the Klima Project, where they're implementing a new global climate model from scratch using Julia, which is really exciting because it's a sort of new language that's got some cool ideas in it. And a thing that you can do in Julia is do dynamic multiple dispatch, which lets you do lots of overloading. So you can write a bit of code using just plus and multiply and things like that. Maybe like you would do using a Haskell num type class. But then you can redefine plus for some different numeric types. So in this bit of code, we're doing the dual number representation, and we're writing down what is plus and divide for, and you do all the other operations for this dual number representation. And so you can take a bit of numerical code and then just say, oh, the inputs are dual numbers, and run it again, and it gives you the automatic differentiation using the forward technique. So it gives you the gradient for that function. And so then you can use that in a machine learning context as part of your loss function to then train your neural net. And you just had to write your normal piece of code and then just overload it to the dual number representation. So I think, again, that's really about leveraging being not overcommitted to the details. And it's sort of, again, really encouraging to see that languages like Julia have sort of hit a sweet spot that people are starting to pay attention and say, oh, this is good. I can write code that I can retarget in different ways and recompile or reinterpret and have this one bit of code that I can do automatic differentiation on, and I don't have to write anything special for it. So this brings me on to the very last cycle, which I'm not going to spend as much time on, but this is the kind of the next stage, as I spent all this time working and talking to climate modelers and then really thinking about how do we evolve the languages? What's the sort of the revolution here that's going to help in the future? And I'm not necessarily thinking I'm going to make that language that everyone uses. It's difficult, that requires a lot of time, but at least maybe we can develop something that sort of by infection can sort of infect something else where there is enough engineering effort and momentum, like Julia or something else in the future, and these ideas can be picked up. And I think, the history of programming languages, you can see that lots of neat ideas get developed in academia, and eventually they kind of, lots of them do make their way into something eventually. And you look at the things that are in Rust, the things that have gone into newer versions of Python and Java and C++ and so on, the ideas make their way in eventually. So, okay, how do we solve this overcommitment problem? Perhaps we go back to the comonadic combinators as well. So I'm sort of thinking about that again. Can we go back to structuring something around these combinators? I think something that's really kind of unexplored there that we sort of thought about but didn't do was really working with lots of different kinds of spatial data structures and connecting those together with the arrays. So you can imagine having something like a quad tree representation, or like a tree of arrays, and this is also a comonad, so you sort of have this way of having different resolutions all within the same grid, and if this, the idea is you coarsen when things are kind of a bit less busy, a bit quiet, then you don't need to do as much computation there, so use this quad tree representation. I think that an idea that I'm sort of starting to explore again is whether you can write a single kernel, a single stencil computation on one grid, and then have this, what's called a comonad morphism, that maps from one representation to the other. So then you can turn this dA to B, maybe this is like a simple grid A to B, into a spatial grid, SA to B, and then lift this to work on the entire spatial grid. So you only have to sort of write something once, and then the detail comes in this comonad morphism that handles that mapping. So you can kind of give your stencil computation on the flat view and then have the spatial view mapped to it. So again, back to this hiding representation, but now we use the comonad morphism in here. So perhaps there's a bunch of different categorical abstractions we can use. So we've got the comonads, the comonad morphisms to go between grid representations. And actually you can see people are already starting to build models which have lots of grid representations in them. So this really neat little intermediate complexity model called Speedy Weather, which is written in Julia. And one of the things that it does is let you really work with different grids and different kinds of grid layouts and different resolutions, all within a single model. So I think this would be an interesting test bed to kind of try out some of these ideas. And there's other operations you need as well, like to do reductions and filtering, but I think those can all be captured by some other kind of distributive laws with a monad. Another problem I've sort of alluded to is this semantic gap, this sort of like problem in communication, and you can see this a lot where you have papers that describe this really abstract model with a load of PDEs. There's maybe some solution numerical analysis that's sketched somewhere, and then you've got the code. And connecting these things back together is really difficult. Often the code is not really clear which parts are related to the original equations and vice versa. Looking at the equations, it's hard to connect them back to the paper. There's sort of a semantic gap that you have here, and that makes it difficult to make progress. So, just to land on this again, sorry. So, one of the difficulties with that is that when you're trying to use someone else's model, and maybe you're trying to take one of these subgrid models and you want to move it into a different model, okay, I've got a really good model of convection in this over here, and I want to put it into this other model and see if it also performs well over there. And one of the problems we've seen, we do a bunch of projects like that, and an issue that I've seen is that there's just not enough information in the code. You sort of get things that look like this, and you say, okay, great, this convection model has some arrays of floats as inputs. Okay, what do those exactly mean? And okay, typically they have some comments, but then those comments can be a bit partial. So what I really want is to have a language where you can put together lots of bits of information within the type system. So say, this y_in thing, it's an array of floats in dimension x, it has unit meters, but particularly that kind of meters is an arc length quantity because you're measuring a distance of a column of air from the equator. So it's really a length across a sphere. And okay, if that's the case, and we have a refinement type that says that its value has to be less than 10 to the 7, because that's the half of the circumference of Earth, pretty much. And okay, this is a temperature thing, and it's absolute temperature in Kelvin, so it needs to be greater than 0. And here's static energy, and okay, it has this unit as well. And these are like semantic tags that then you can link to documents as well. So I'm sort of getting, okay, that's a bit array from arrays, as I was talking about, but trying to build languages where you can get a lot more information about your actual domain into the code via type system design. So to kind of then conclude with a grab bag of ideas then, so what could this language look like? What are the things that I think are useful to consider for such a language that could actually help scientists? Okay, it has to be sort of science-oriented, and we have to look at the actual kind of things that people are doing there. I think a big part of that is about describing the domain. Of course, it's got to work with arrays, and you can see all of the huge amounts of work that go into sort of array libraries in different languages. And I think one of the reasons that Fortran has remained popular, it has a lot of sort of sociological inertia behind it, but arrays are first class in Fortran. You can do A plus B on 2 arrays, and it does the pointwise addition of those arrays, and it parallelizes it for you automatically. That's great. That's what you do in MATLAB as well, and you can do it in Julia. There's lots of really nice libraries that people are building on top of Python, NumPy, Xarray, XGCM that embed lots more of these kind of array patterns with lots of information in them as well. So it's got to have things like that. Interactivity is increasingly important. REPLs, we know, are really cool, and people use those as well. Notebooks are very popular in science, and I could say a lot about notebooks. They're kind of useful for interactivity, but then they sort of push you into a corner where then you end up with code that's not very modular or reproducible, but that's another rant. Overloading, I think, is really important, again, for that retargeting, doing things like AD and symbolic execution, and core to that is, again, this low commitment to the implementation details. We have a project, which I'm not going to talk about, called the Fluid Language. That's in our institute, Roli Pereira, and that's all about having explainable and transparent visualizations and code. Go and have a look at that online. There's some talks on YouTube. Search for Fluid Language Pereira. So having sort of runtimes that then give you access to understand the provenance of the calculations and let you kind of really interrogate how the evidence was generated. Of course, it's got to be fast, though, right? And actually, I haven't really had any graphs today. Sorry that FProPer. I probably should have had some benchmarks and things like that. But people use Fortran because they can write fast code. And okay, in the future, anything we build, it's got to be high performance. And Julia is getting really, really good performance. We want heterogeneous compilation, of course. We want to be able to target all the new architectures and systems. And my favorite topic as well, lightweight verification, bringing some of these specification systems in so that people can just be more productive because they've got something that is checking things for them, using types, and that helps them communicate better between them. So one of these big problems is this semantic gap. We spend huge amounts of time discussing, what does this variable mean, and what's its units, and is it an absolute value, or is it a tendency? Is it, what's its resolution? Having these things specified and checked would be excellent. And yeah, program synthesis. Yeah, let's have things written for us when the computer can do it. Okay, so I'm going to end with a job, with an advert. If any of this sounds interesting and you'd like to come and work with me, I have a postdoc available at the moment for just under 3 years at Kent. It could be on anything really in this space. Could be about static analysis, could be about verifying critical libraries used by scientists, could be about these novel languages or extending existing languages. If you're in that situation where you're sort of looking for a postdoc or you know someone, then you've got until Monday. So I made the advert finish as late as I could, so it's just after ICFP. And of course, developing new tools. Okay, so I'm going to end with another quote from Simon Sharp, which is a sort of a challenge for me and for everyone, to think about this general problem that we have. We know the situation is a bit difficult, but Simon has this great quote: any actor should understand their points of leverage. We each have to understand the opportunities presented by our place in the system and do our best to exploit them. So whether that's at a personal level or a professional level or in your communities, whatever you're involved in, there's some way that you can have the most leverage. And so have a think about what that is and try and use that leverage. So thank you very much for listening, and happy to take questions. Thank you. Hi.
Really interesting talk. I really enjoyed, and I'm really excited whenever you apply here to some applications. So regarding the pattern matching for indexes question, I assume that that works really well for dense representation of matrices.
Yeah, that's a great question. So, you know, what about sparse representations where we have some sort of like indirection kind of arrays in the middle? So, I think our philosophy here is that you have the sparse, you can do a sparse matrix comonad, but then what you expose is a kind of dense view on that. So you still index it in the sort of the dense way, but then underneath that's mapped to the sparse via the indirection. So rather than exposing the sparseness, that's like an implementation detail that you hide inside the comonad.
So in that case, how would you interact with the libraries that are written with sparse representations?
So I think in something like Hypnos, you are really restricting yourself to certain patterns. So it is a bit like you can't do everything. It's sort of like, here's the things that you can do, and here's the things you can do fast and predictably. So it is necessarily restrictive. So there are things that you wouldn't expose, so it would reduce your expressivity, but gaining the kind of performance. And then you hide, you write the underlying implementation to deal with those libraries. So if you wanted to capture everything, then that sounds like a harder but interesting problem that I don't know the solution to. Yeah.
Yeah, that's interesting. And the second question that I have is regarding like the MPI stuff. So in the slides that you have presented, I suppose it's a very sequential style of writing programs. What happens when the parallelism, like message passing and stuff? How would you model that with comonads and this kind of stuff?
So you can hide all that stuff inside the comonad. So the comonad can do the domain decomposition. It can split things up. So in Hypnos, you statically know the size of your kernel, so you know the size of your halos, and then you do some calculation about how much you're going to split it up, and you know the halo sizes, and then it's all hidden. So in terms of an MPI or a GPU implementation or something, that's sort of all in this, I've chosen this particular comonad, and it does that parallelization inside.
Okay, thanks so much.
Thanks. Great. Ooh.
The kind of like scale of energy that we use is like orders of magnitude the whole country, right?
Yeah.
Globally.
Yeah. Yeah, this is a really great question about, energy efficiency. I haven't done any work myself about it. I suppose at a very coarse grain level, you could say, higher performance means less energy, using less cycles, less memory. So there's a relationship there, which has some subtleties to it as well, because it's not a one-to-one mapping, I don't think. There are people who are thinking about this. There's a group at Glasgow, the LOCOS, LOCOS group, who are thinking about this kind of thing. And there is sort of various sort of movements around sort of green HPC and green algorithms. So it's something that people in this space do think about, and there's increasing sort of, okay, what we could do with is more monitoring tools on HPC and clusters to understand how much energy did that job use, and estimate in the future how much energy something uses, and can we schedule it at certain times of day, like during the day in the southern hemisphere when there's loads of sun, or in the summer, or things like that. I'm not doing any work on that specifically, but I think it's really important, and there are people out there doing that. Suddenly got louder.
Any other questions? Thank you for the talk. It's very good. This question I'm wondering about is, well, I think you put a lot of emphasis on sort of abstracting things away and abstracting the raw level detail. So what tends to happen with that is you limit the optimization potential that's available, because it's a leaky abstraction, like you don't get to see the generated code often. And I think the common is like a really nice abstraction for this sort of thing, but like what is your position on like whether there exist abstractions where you can actually like the compiler can do the entire work and no one actually has to see the whole level code? Like do you have like positions of like how should expert programmer be able to optimize these things very efficiently?
Yeah, this is an important question. It's sort of it's a long-running question, isn't it? And that went back to my arguments with my roommate I want to write the C code because I can make it way faster. I suppose there's a bit of an axis, isn't there? Because it's about this almost like productivity and performance. You could see as kind of two axes. If I want to write some code really quickly and get 95% of the performance I could, but it took me a day to write it rather than a month, then that might be a good thing. And I can write a model. I'm a scientist. I can write a model. I can try out loads of things. I can try out lots of different model configurations and try lots of ideas. And okay, it's not the fastest, but I could explore the science more easily. I was more productive. So I think with Hypnos, that was our kind of trade-off in the space. We trade off some of that squeezing out every drop of performance for I can very easily write code and understand its performance. But of course, there is a time and a place for that squeezing things out. And if you go to sort of the high end of climate modeling, where we want to run as high a resolution model as possible, we want to simulate 200 years, and we want to try 200 different parameters or more, like tweaks, then okay, that maybe is going to take a year of computation. So being able to save a few days and a few megatons of CO2 is maybe really important. And I don't really have a good answer for you in the kind of things that I've been doing. I will say that something I've observed, which is interesting in Julia, is that it lets you inspect the compiled code at different stages. So you can use macros to sort of reveal what's the intermediate representations, what's the underlying LLVM. So what people do is they look at that and they learn really how things are behaving in the compiler, and then they tweak their code to squeeze that out. So they're not down doing the LLVM themselves, but they learn how to push things in the right direction to get the highest performance code. So in a sense, that's having a mechanism for inspecting all of those steps and understanding them. And so I think that was one of the things that we thought about earlier with Hypnos. Like a lot of the automatic approaches, or even these abstract approaches, a problem they can have is that they're just completely opaque. So if it doesn't do what you want it to do, you're just left saying, I don't know why that wasn't as fast. So I think having more explainability in compilers and these kind of things is really important. Say, well, I did this for this reason, this for this reason, and I couldn't do this for this reason, and therefore you can have things that you can tweak, and I think you'd probably do eventually need to expose some details, and okay, you could go in and tweak the comonad definitions yourself or something like that. But I think, I suppose, surfacing that to the user is really important, and that's what's happened in Julia, and I think that's one of the things that's also making it really popular. People are looking at the LLVM code it generates, or like then step up and go, okay, now I want to be a bit faster, so I need to specialize this thing, and okay, now it's done it. So there's a lot to be gained in those scenarios from explaining what's happening and exposing some of that representation underneath, eventually. And then that's that's in a different scenario when you're willing to lose the productivity because you want the performance.
Any quick final question? Maybe two quick, super quick questions.
I'm just curious about something confusing me, that is, how is it different from running a specific language and then organize by some optimization process with MLI or something like that? How is it really different from this approach, from the PR or this compiler approach? Like exposing a very specific language, for example, specify the more specific from kernels to anything. The optimization process just apply those optimization or rewrite custom on for that library process.
Mm-hmm.
How is it different from the PR approach computations?
So how is the approach of Hypnos different to that kind of thing, or? I'm not sure I fully understand the question. So you like a comparison between?
Type system approach. It seems from a type system approach and try to expose the concept to the users with some specification for checking.
Yeah.
And how is it different from directly writing a domain-specific language for the kernels, and then to let all the compilers recognize to the optimization on that domain-specific language?
Right. So, I mean, perhaps they're not kind of mutually exclusive. So, Yeah, I think a nice thing about type systems is that they're an intrinsic mechanism that's about a kind of dialogue between you and the language. It's sort of telling you the things you can and can't do, and it's encoding lots of information. And with Hypnos, what we wanted to do is really get as much information available to the compiler. And you know, a lot of compilers, what happens is you take a language, you throw away a bunch of information, and then you do static analysis to try and recover that information. And maybe it does or doesn't get that information back. So we're like, let's cut that out. Let's capture as much information statically as possible so that the static analysis is very easy. And I think part of the kind of program of types, or at least the way I think about it, is sort of exposing that information to the user and having it be like an intrinsic part of the thought process, rather than, well, you write some code and then some analysis happens on it later and then maybe some good stuff happens. So I think like, yeah, having DSLs to write down some kernels versus like a typed approach, those things aren't mutually exclusive. You know, Hypnos was trying to put those two things together and sort of use the types to let the programmer communicate to the language and to the compiler. This is what I'm doing. This is the shape of this thing. These are the boundaries. This is the dimensionality. And then go and use that information to compile. So, and then having, you know, the type checker kind of force you to do things in the right way and say, well, your stencil looks one to the left, so you need to have a boundary one to the left as well, rather than letting something fail later on. And I spent a week letting things fail later on and couldn't understand it. So it's about the understandability, I suppose, with the types.
Thank you very much. I'm afraid we have to take it off.
Well, yeah. I'll
Thank
be
you very
around.
much again.
who's a researcher at INRIA, and he's going to start off, well, he's going to give both of the talks, and he's going to start off with one on language support for asynchrony, and it's titled Tail Modulo Async Await. So please take it away.
Thank you. Let me try to put that. Okay, maybe not. All right. Okay, my slides are not connected. Yes. They were connected before. Okay, very good. All right. So this work comes from sort of an interesting place. Is that Ludovic, my co-author, really likes concurrent languages, and I like functional languages. And at some point we got together and said, why doesn't this work? And a master's student later, this is the result. And so, I mean, you're a functional programmer, and the best friend of the functional programmer is recursion. And so if you do a normal recursion, as you know, you will have some stack, and some stack, and some stack, and some more stack. And at some point, you might have an issue if it grows too large. And naturally, the nice solution to that, you tweak a little bit your code. For instance, you move to an accumulator style implementation, and then you use tail calls instead of normal call, which means that the recursive call is the last call, the last operation of the function. And in that case, we don't have any more stack issues, because tail call will not have accumulate stack frames. And so we get a different calling convention, which is a tail call, and it worked nicely. And then, when you have a recursive function where all the calls are tail, you can do more things, and you can do, this time, a compiler transformation, not just runtime support. And you can derecursify your function, and then you have a nice loop, and then performance people are very happy because it goes fast. Okay. So that's nice. Now, let's say I want to write asynchronous code. And so here I want to write this read all function. So for this, the purpose of this talk, I'm going to assume that I have a let async, which just means that the function is asynchronous. It's going to run in some green thread and return a feature. And so you can see the signature at the top, this read all function, an integer, and it's going to read n files and return the concatenation of the content as a future. And since I have asynchronous I/O, I will need to do some async, some await. And so here I await for a file to be read, and then I concatenate by awaiting on the recursive call. Is that clear enough? Yes. All right. So again, I would have lots of stack trace and so on and so forth. Well, actually, not completely. So again, I can move to an accumulator style thing, where I have some accumulator that is going to contain the strings that I accumulate. And then I do the concatenation here, and so on and so forth. Probably should be the reverse, but oh, you get the idea. And if I do that, then I don't have so much problem on my stack, but I have another problem now, which is that I'm going to do a chain of await, where I read all at this point, and then I await on a future at this position here. And then I await on the next one, and so on and so forth, until I reach my final value. And so I'm going to have I don't have a long chain on the stack anymore, but I do have a long chain in my futures. Which means I still have exactly the same problem as before. And so our contribution in this talk is a new notion of tail asynchronous calls that I will try to detail, which is sort of an alternative calling convention, just as scale calls, and a code transformation, which I will call destiny passing style. I will explain why later. And an extension to tail modulo cons, which was recently introduced in OCaml, semantics, some proofs, we'll see, and a partial implementation, and we will lots of discussion on that towards the end. All right, so the first key idea is to use promises instead of future. So a future, usually you introduce with async, and then you access it with await, and a promise gives you, on top of that, a write once pointer that allows you to fill the future. And obviously you should not try to access this pointer several times. It's only write, it's write only and write once. And so concretely, I have my future. If I took the previous example, I had a riddle. It points to a box, and this box I will be able to use an operation, which is called fill, and we put the value in the box and be done with it. And so if I go back to my previous code example, I will transform it in several steps. The first step will be to add what we call a destiny, a new argument D, and the destiny is the future result, the future position of the result. Where should the result go eventually? Or the destiny of the computation, if you want. So this idea of destiny, it's been used quite a while in concurrent languages. If you want to look, there's a very nice paper called Forward to a Promising Future, with lots of puns, which introduces this notion of destiny more formally. And so we add this destiny argument, and then we pass it along to the recursive call, because we're interested in the accumulator, and it will contain it will be put in the destiny. I have put some holes here, so let's see how we can fill that. When we reach the bottom, then we fill the destiny with the accumulator. Okay. And then we need to start somewhere. And so we now have a notion of promise creation, which gives us both a future and a destiny. The future is read-only when the computation is ready, and the destiny is write-only and write once. So this notion is present in quite a few future and promise library. In OCaml library, we tend to call it a resolver. In other various libraries, it has different names. And now with this transformation, my read-all function doesn't return anything anymore. It's just a unit, because at the end it will perform a side effect to fill the destiny. It still can do some await here and there. And interestingly, I can return the future directly. Actually, it's missing something here. It should be an async here additionally. So we can launch the computation and give the future directly, and when the computation is finished, the future will be readable for the consumer. Okay, so I've done this code transformation, and now I have recursive function that doesn't return anything, and the call here is tail. So, okay, I'm happy. If I do that, I will have a small call stack, and my chain of future is short as well. And so I've gained in both the stack and the feature. Nice. Okay. So this worked well. You can implement that pretty easily. It's a simple code transformation that is very similar to the tail recursive transformation. Now, what about constructor? I told you at the beginning we would look at tail modulo constructor, and this is the real purpose of this talk, in fact. The previous one was just a bonus. So, we recently got in OCaml tail recursion, tail modulo cons, and it's an old technique from the Scheme and Lisp days, which is that we can write a function that is recursive and whose last recursive call is under a constructor. And in this case, we can use tail modulo cons, which is to turn into a DPS, destination passing style, where we give a destination, and the destination eventually will be written and will correspond to the cons of the thing. And then we make a pointer to the whole. Okay, let me do that again, sorry. We first allocate the cons before doing the recursive call. We get a pointer to the whole, the part of the list that is not yet written, and we pass that pointer to the rest of the computation. And the rest of the computation will eventually write the value inside this whole. And so that's exactly here. We have a cons here which is allocated with a whole. We get the destination, and we pass the destination here. Okay? And so this is taken directly from the tail modulo cons paper. And so this destiny passing style, you might notice some similarity, right? It's like you have this mutable variable that is that you can put your result in. It is write only. It should be written once, and so on and so forth. What about functions on trees? So here we were very careful. We only have one recursive call, and so this only recursive call can be turned into a tail call. But if I have a recursive function on trees, then this map here will be tail modulo cons, but I cannot have two functions that are two calls that are tail modulo cons at the same time. That doesn't make sense. I'm in a sequential context. What am I going to do? Which one am I going to use first, and so on. So that doesn't really work. But in an asynchronous context, I don't really care. I can do both calls at the same time. And so if I consider this asynchronous function, which is still a map on trees, if I get a node, I call v, so it is an asynchronous function like last time, and I can await on both map and launch both map concurrently, and eventually I should get a result. And so the idea of this work is basically to take functions that look like this and do exactly the same as tail modulo cons, which is to allocate the cons first, launch all recursive functions, and figure out how to pass things so that at the end we get our value back. Okay. So the key idea here is basically the destiny is half a promise and half a destination. It's sort of a mix of these two ideas. And so a destiny is a whole where we are going to place the value to be computed. But unlike the destination that we used previously, we can have multiple write once pointer in the structure at the same time. And the value is ready, which means the computation is fulfilled when there are no more holes. So if I take this function on the left, which was a map on trees from before, we are going to turn it on the thing on the right. So don't try to read it too much now. I'm going to come back to it later. The thing that is interesting is that we have some functions that work on destinies, and then we have a forking call at the end, which is going to call the recursive function by doing a fork. All right, so what's those destiny things? So here is a sort of API for destiny. It's actually not a real API, so those are not real ML type because it doesn't type. And it shouldn't, it's internal to the compiler, so it doesn't need to type. So we have a type. A destiny of an alpha destiny is a hole in a value, which will be filled by a value of type alpha. It must be used linearly, because otherwise we would try to write several times in the same hole. We can create a new destiny, and it gives you, as before, two views: the destiny, which is write only, and the future, which is read only. And the future will only be ready later. And finally, we can refine a destiny. We take a hole, we take a value with some more holes. Well, sorry, we take a destiny, which is a pointer. We take a value with some more holes. We put the value inside the destiny, and we obtain more destinies pointing to the inner holes. Okay, let's look at that graphically. So we have this pointer pointing to a big value with two destiny, D1 and D2, with some holes. We have a context here, which is basically a value, a cons. Refine will put this inside D1 by returning two new destiny, D3 and D4, which point to the new holes. And so we can propagate the computation like that by keeping track of all the holes in the value. But at some point we got to end. And so we have this value here, which we want to put in the destiny D. And we notice that this value does not have any more holes, and this one only have one hole. And so when we put the value in the destiny, then we lift a flag saying, this is it, the value is ready. Because we know that once we reach 0, there are no more holes available. Remember, the destiny should be used linearly, and so the number of holes can never grow again. We can never reintroduce holes in the value. Okay, so let's look at this, the code that is generated now. We're going to start from here, and at the we're going to allocate a new destiny. So it gives us a future and the top level of the value with a destiny inside, the destiny D. It has one hole and it is not ready. We start our computation. So for example, we're going through the node, and so we are going to allocate the node with some values, and the destiny D here is not available anymore. We have refined the destiny, but we have two new destinies, DL and DR, that correspond to the holes that are available right now. And we can keep going. So for example, I can use DI and fit it with a leaf. I update my counter as I go on, and so on, and so on, and so on. And now I've reached 0, and so now I know that my value is ready. So I lift my flag, and I update the future to point to the value. All right, so that's pretty much it. So we've defined the semantic for destinies and forking calls on paper. There is a work in progress proof of simulation. Unfortunately, the internship was a bit too short, and so we didn't got time to exactly finish those, but we're working on it right now. And we can implement those destinies in unsafe OCaml, and it works fine. So it's a nice proof of concept. The problem right now is that we sort of have a dilemma. I cannot experiment with this just in source OCaml because I cannot express forking calls. So if you look here, I have this fork call function, and I cannot explain to OCaml, please stop caring about the stack for this call. That's not an operation that is available, and it probably shouldn't be. So in source OCaml, I cannot write that. But on the other hand, in the OCaml IR directly, there is no notion of asynchrony. So I cannot really explain all this to OCaml either. Because in OCaml, async are effects and they're user side. So there is sort of a question, how do we actually put all this in OCaml? And where exactly should it sit in the compiler stack? So I see Pierre doing some back and forth. So yes, so that's pretty much it. And if you have any question or remarks or propositions, I'm very welcome to it.
Yeah, I have a question at the very beginning.
Okay.
So in a way, I was wondering, why would I want this? And then my suspicion went along the lines, aren't you just, and it's not just, but isn't this mainly creating an opportunity to make explicit in the high-level language how to do task parallelism?
Yes, and so sort of, yes. But also the real reason is to do this. It's basically to have function over branching structure that are stackless.
Well, if I look at it purely functional semantics, I say, oh, there's two recursive calls. Surely I can do them independently. So shouldn't my compiler be doing this for me?
Well, no, it is.
Well, yeah, this is precisely the point. So in a way, this would give the programmer the ability to make this explicit.
Yeah.
So do you have in mind that, or is one of the motivations of your work that you want to take an ordinary functional program and then translate it into something like this as an intermediate code so that you get more transparency about what is going on when it comes to performance or not so much performance? Or is it a general observation that for recursive data structures with more than one branch, this is something that you would love to have?
I think it's more of the like that. Like it's just like if you have a recursive branching structure, and you're okay with having the computation being concurrent, then you don't need to pay the price of the stack, basically. You don't need to be limited by the stack, should I say. That's really the observation here. Now, could it be transformed into more of a task-based thingy? I mean, it is task-based, clearly. I think it's a good idea as well. I'm not sure, but I think so as well. As I said, at the end, it's not exactly figured out how to really make advantage of this idea. So, maybe?
And if I may put it another question. So you said, oh, in OCaml we can't do this because we can't fork a new thread. So if I think about Haskell, then they have this par thingy,
Yes.
which in principle you could abuse, maybe?
Maybe. I think it would be the same so in Haskell it would be inside the compiler, definitely, as well.
So OCaml doesn't have something like a par construct?
Not really.
Not really, yeah? Sounds ominous.
No, but the async and await in OCaml are going to be library side,
Ah, okay.
which means I do not have access to them inside the compiler.
I see.
So, yeah.
Thank you.
Yeah, I'm curious about how exactly you define the semantics for this, because I look and to me it's like a really strong parallel with the process calculus, where you have like your holes and your destinies are like channels, and I feel like if you model this as processes, you could infer this automatically, do this in a much more general way, probably, because this is like a very simple transformation over processes. Right?
Probably. The slightly tricky thing, well, tricky, I don't know. The point of this is that you can do that in the middle of a general purpose language that has a traditional style semantics. Mm-hmm. And so I do not know if we have process-based semantics or semantics that look like process calculus for, you know.
I don't know exactly how
Yeah.
async works inside of OCaml either. So.
But so yes, and I mean the formalization we have is sort of a bit like that, really, and the proof is by simulation, so it's pretty much like that. So a little bit, yes.
Should we proceed?
Yes, we are early, but we can.
So maybe I'm missing something, but regarding the integration with OCaml,
Yeah.
since like all the concurrency future stuff is going to be provided as libraries,
Yeah.
couldn't you just for any function where you want to apply this transformation, pass it, I don't know, like a module that contains the functions that you want to insert, and then arguably, I mean, probably this function needs to work properly, but then you just insert them and pass a correct module. And
I mean, the problem is that the transformation has to be inside lambda.
mm-hmm.
And I do not know how to expose that kind of interface from lambda.
Yeah, like an annotation in the tree, an attribute as an attribute to the definition.
Ah, that's true. I could do that.
You already have to do this when you do tail modulo cons, right? So
I'm not sure I would get that merged. I'm
Okay,
pretty sure I would not get that merged. But,
would that work in principle?
Hmm?
Could that work in principle?
Probably.
Okay.
Probably, yeah. But it would not be usable by people. Because it would need a fork compiler.
I mean, okay. Okay, thanks.
Okay, let's thank the speaker.
Either we do a break or I continue. Up to you. All right.
Maybe we do a 5-minute break and then...
Yes, just to get me rest. Okay, welcome back. um, so, um, so I'm going to present a work with my PhD student, Thaïs Baudon, and Laure Gonor. And so this is a sort of follow-up work of something that was presented last year at ICFP, which is the quest toward custom memory representation for algebraic data types. And so, okay, a quick sort of recap. So we have lots of algebraic data types. So here is an example of one. So this talk is going to be in a Rust-like syntax. Why not? So here we have an enum color, which is either red or black with two constructors. And when we have an algebraic data type, RBT for red-black tree, which is either a node with 4 fields and or empty. And we have an example of a value on the right. And the nice thing about algebraic data types is that, well, we can write pattern matching. And so we have this cardinal function here, which is simply a case analysis. Either it's empty and it's 0, or it's node and we can count the subterms. And with some nice typing, we can check for lots of properties, including, for instance, exhaustivity, non-redundancy, and so on and so forth. This is very nice. Now, what happens in the real world? Oh, okay, no, before that, another thing that is pretty nice is that we have access to lots of tools, and so we can write complex pattern matching in a pretty compact way. So this is a balance operation on red-black trees. It's a bit of a mess, because the operation is complicated, but it expresses exactly what we want, and the exhaustivity and non-redundancy are going to check that we are doing a good job. Okay, all right. Now, what's going to happen in a traditional language is that we're going to have a memory layout for our representation. So here is an example of a fairly naive memory layout for red-black trees. A node is going to be a pointer over 64 bits. And then we have 4 fields, and so we will have a header, probably, in most languages, and 4 fields. The black is a 2 value, but here it's very naive, so it's going to be represented on 64 bits. And at the end we have an empty, which is a null pointer in practice. Okay, good, excellent. Now the problem is that in many performance-intensive representation or performance-intensive code, they do not want representation like that at all. So there are red-black trees in the Linux kernel, and they are represented like this. You have a node, which is a pointer, and then they have a parent pointer, so a pointer to the parent of the node, where they use one of the bits to encode the color, because this pointer is aligned, so the first bit is always 0, so they can hide something here. Then you have a first child, the second child, and the value. And now you have a much more compact representation. You have an additional pointer, and so on and so forth. So you've seen, for those who've seen the paper on double-ended bit stealing, you can see how far we can go with this kind of representation. So if you look at the Linux kernel code, you can see this kind of code, which is basically a mess of pointer shuffling to figure out exactly where to put things. So for example, here we have a code which is half a case of the rebalancing operation, and which is already a page long. So our contribution is a custom memory layout for algebraic data types. We will have an input language where we can specify exactly the layout of the memory representation, and we will check that it is indeed a good representation for the algebraic data type. And then we have a bunch of compilation algorithms for pattern matching and for data constructor and accessor, and this is a new bit compared to the last paper. If you want to play with it, you can go to this link here, where you will have an online demo with example where you can play with the code. And it will show you lots of graphs. Okay. So I will go progressively. I will start with the high-level type and the for the algebraic data types, and how to express memory layout for an algebraic data type. So let's go back to red-black trees. We're going to try to build with Ribbit Linux-like red-black tree representation. So this is going to be our representation for this talk. We have a color. It's going to be on 1 bit only. Red is 0, black is 1. And then a red-black tree is going to be either empty, which is going to be a word of 64 bits, where 1, the lowest bit, is 1. And we don't care about the rest. It can be whatever. And then the node is going to be a pointer to 3 fields, which are the value, the left, and the right trees. And then the color is going to be sneaked in one of the lowest bit of the pointer. And then we're going to keep 0 at the lowest bit. So that's our representation. So you notice we don't put the parent pointer that was there in the Linux representation. That's just because our small language is pure, and cyclic pointer in a pure language are annoying. So it's not a real limitation, it's just we didn't do it in the small prototype. All right. So, any question at this point? Okay, let's go. Now, for each type, we will have a high-level type and a memory type. And so, for example, for the red-black, for the color, we'll say represented as to express the low-level type. And the first construct we have for low-level type is what we call a split. A split expresses the fact that we have several choices. Here we have a split that says that the memory representation depends on the current value, the value that we have at the root right now. And if it's a 0, we say it comes from the red constructor, and we sort of repeat the fact that it's 0 on 1 bit. And it comes from 1, it is 1 on 1 bit. So here we have various pieces. We have a discriminant value on the split that say how we are going to differentiate the various cases of the representation. And we have what we call a provenance that says, okay, this case, this particular representation is there because of this constructor. So here I am in this case because this was a red value. And so this is shown graphically on the right. Either it is red, black, 0 on 1 bit, or 1 on 1 bit. Okay, so we have a simple enum. So obviously, like, if it was just an enum, we wouldn't need anything like that. This is a bit over-engineered for the representation here. So we could just express that directly. But it's going to be more useful when we move to bigger representation.
Sorry, if I look at this and I would just specify this,
Mm-hmm.
then what would your code generator do if I just have one enum color value? How is that going to go into memory?
What do you mean?
I think this is meant to specify how this is being mapped into memory.
Yes.
But so this specification is yet incomplete, right? You just say it is 1 bit, but you don't say where the bit is, what is the minimum allocatable unit, and how.
So you're right. So you can have yes. So you can. So far in Ribbit we sort of don't really mind that part as well. You could have in your language a compiler deciding that everything that is smaller than 64-bit is going to get put in a word. The reason we have 1 bit here is for composition. If it's going to be put in something else, then it's going to be 1 bit, and that's the goal. But yes, if this value is unboxed in a computation, then you need additional rule on top of that.
Sorry, it is redundant because since you have 2 constructors, you can easily understand that you need just 1 bit, right?
Yes.
If you have 3, you need log.
Yes.
Stealing of log 5.
Yeah. We're going to, and we're checking for that.
So why do you need to specify this?
Because I want to introduce split to you, and this is the simplest example ever. But yeah, as I was saying, this is really over-engineer for enums, definitely. And generate this for me, and I just do the thing, and it will work. Yes. All right, so now let's move on to a more interesting type. So again, we have an alternative. We have either an empty or a node. But this time you notice that the way I'm going to distinguish an empty from a node is by looking at the lowest bit of the word. And so it's not just the whole word I'm going to look at because, well, there is a pointer, so I don't really want to look at that. But I'm only going to look at the lowest bit. And so I'm again using a split. But this time the location say, please look at the lowest bit of the current value. So I have my split, and then I need to do the various pieces. So at the lowest value, at the lowest bit, I have either 1 or 0. I mean, it's a single bit, so anyway. I can give the provenance, either it is empty or it is node. So now let's look at the empty case. The empty case is pretty easy. We don't care. Like, it can be whatever, because there is nothing of interest in the empty case. And so we just have a wildcard that's going to be on 64 bits. And just for consistency, we sort of repeat ourselves with what we called a bit word specification. Let's say, in this last bit, so the range here, please put a 1. So again, this is the whole purpose of example. In practice, rebit infers that part. You don't really need to repeat yourself. But here, for the purpose of the talk, we will be very explicit. Okay, so the empty is any word of 64-bit whose last bit is 1. Excellent. Okay. Now, in the node case, I told you the node is a pointer to 3 fields. And so this is a pointer here. And we're going to have a bunch of stuff as a pointee. But first, we have to specify what are the lowest bit of the pointer, because we are going to steal the lowest bit. And so one of them is going to be a 0, again, here. And the 1 here is going to be the color. And so here we have to point out the fact that, okay, the color, which is at this point in the original value, is going to be placed here. So we call that a fragment. It's a fragment of the bigger type. And we are going to verify that, this color is on 1 bit. It does fit inside this place. And it will work okay. Okay. And then we have the content of the pointer to look at. And it's going to work exactly like a struct. And so we are going to have several fields, 1, 2, 3, that correspond to the value, the left-hand side of the tree, and the right-hand side of the tree. So we are going to have 3 fragments to represent that. I have lots of time, so I can take questions during the talk, if you have questions at this point.
Everything is not boxed in this talk, right?
Yes. I mean, boxing is explicit. You will put a pointer. So, yes.
Why do you need to specify the types of everything?
Aha. Good question. It's not the type, it's a representation. It just happens to be the same name because we only have 1 representation for the types in this talk. But you could give another representation, and you can have several representations for the same type.
Will we see polymorphism later?
No. Okay. Sorry.
Are the memory representations kind of separate? Are they always used like homogeneously? Or can I have one representation that has as like sub-representation of the recursive parts with another one? Is there any use for this kind of thing?
Yes, it's later in the talk. You can be as non-uniform as you like. You can do whatever. You can inline two level of trees if you want in one node and make a big flat node. You can shuffle around the fields. You can, go banana. Like, it will work. And we actually have a proof that it works. Well, it's not in the paper, but it's in Thais' thesis. Right. Okay. So now we have a full representation. Cool. What can we do with it? So we can verify that it actually works. So we have formal criterions that are going to assert that this is indeed a good representation. And so there are several of them. I'm going to highlight two of them. One of them is distinguishability, which means that, I mean, we have encoded some type. The primary purpose of some type is pattern matching on them. And so we should be able to distinguish, based on the representation, the various cases of the sum type. And so here it's pretty easy. We have only one split to look at. But you could have various pieces in the value that indicate one case or another, and it could like be a compounded information. That would work. The value, we need to find all the pieces of this value. Otherwise, it's not a good encoding. And so here, I mean, by color, it's correct, but there is an actual formal version of that. Here we have both cases, and we have all 4 fields of the node case that are in the value.
Now, they give the full powers of the programmer.
Mm-hmm.
The question is, can you specify these descriptions in a hardware-specific way? For example, I may have an architecture that does not support 64-bit pointers but 32-bit pointers. I may have an architecture that doesn't take it lightly if you mess around with the newest 2 bits because they have implemented some weird stuff on the architecture.
Yeah.
And you need to have an alternative representation. Can you do this?
So far in Ribbit, we haven't done it in the prototype. There is no reason we cannot, because, I mean, I gave you a notion of pointer here. I can give you another notion of pointer. The pointer are size dependent, so you can change the notion of pointer. You could also decide, okay, my pointer, you do not have the right to mess with the higher bits, for instance, if that's forbidden in your case, and so on. So
the question is, can you check this?
Yeah, yes, it will not change much about the checking of the validity. But no, we haven't implemented mostly because it's a question of how do you present this diversity to the user, and I do not have an answer to that. Like, it is a very complicated amount of things to present to the user, especially if you start talking about embedded, where like everything is weird, and so I don't have a good answer to that aspect.
Just want to confirm those are all curly braces.
Yes.
What does that mean?
Those ones?
Yes.
It's a struct.
It's a struct.
It's just a struct. It's like several fields unboxed in a piece of memory, and that's it.
But it appears to be an address, a reference to that.
The pointer is outside, so there is an explicit pointer to a struct. But yeah, if we go back, the struct, the double bracket represents this part here.
I just want to have, do they only have 62-bit left for this word?
No, I'm not sure I understand the question.
So the whole word is 64 bits?
That's the size of the pointer.
Yes.
The size of the struct is deduced by the size of the content. All right. Okay, now, so this, so if you were here last year for the previous talk, there is nothing new here. It was all there previously. Now I'm going to show you another example of representation, which might be slightly surprising in a way, is that let's look for a moment at the RISC-V instruction set assembly. So if we look at RISC-V instruction set assembly, here is a representation of the store word instruction, and it has, in the assembly, it has 3 parameters, x0, x1, 42. So it's the address of the word, the address of the content, and the offset. And it's going to be represented like this. The x0 is put somewhere in the middle. The x1 is put somewhere here, so before the other argument. The fact that it's a store word instruction is split into two parts. One bit is here and one bit is here. So we have two pieces. And the offset is also split into two parts, 5 bit at the sort of beginning and 5 bit at the end. So you've seen like this representation is a bit weird. We've split various places. Our constructor, the store word, is also split into two pieces, and so on and so forth. And so the new thing is that nowadays we can actually represent this kind of thing exactly as a layout of an algebraic data type. So let's look line by line. At the beginning we have the name of the register for RISC-V, so they're x0 to x31. And as I said before, we can explicit that representation, but we can just ask Rebit to do it for us, and I just ask, okay, please give me exactly the representation of C, and it will do that for us. And then I have the representation of a 32-bit instruction in RISC-V. And so it's just a constructor with some register and a 12-bit integer, and then I can have other things. And then I can fully write exactly with all the ingredients that I gave you in the previous example, this representation. And so if I took a concrete piece, for example, from the bit from 7 to 5, so this corresponds to this piece here, I'm going to have the second field of the SW instruction, and I'm going to take the bits from 0 to 5 as a 5-bit integer and put them at that position. So it's very tedious to write, but you can write everything pretty precisely, and it will exactly have the expressivity that you need to encode this kind of splitting of various pieces.
Sorry, when you write I5, it is signed integer or unsigned?
In this case, it's unsigned, because in the representation there is no notion of signedness.
So it's all over.
Yeah.
And you have little engine all over the...
In this case, yes. It is sort of related to Sven's question. We could have both. Making it parametric would be difficult, and again, I do not know how to expose that to the user.
With the code that you are showing, it looks like we are only looking at the 7 low bits for the constructors.
You are right.
And completely ignoring the 3 bits.
Yes, that's because it's slightly too simplified for the slides.
Okay.
You can have a split inside a split. So you can have, you can even have multiple arguments in a split. Like you can say, I'm going to split on this position and this position and do list all the values. So yes, yeah, it's simplified a little bit for the slide. We do specify that there is a constant, the right constant here and here. Yes. But yeah. Okay. And so now I'm going to. So we have a type that is pretty nice. We can do this weird type with lots of pieces. Now I want to compile code. So here is an example of code that uses the RISC-V instruction. It basically tests if something is compressible or not. So 32-bit instruction RISC-V can be compressed to 60-bit instructions, some of them, not all of them. And so here it looks at my assembly language and it decides, can it be compressed or can it be not compressed? And so in my input language, I'm going to have various ingredients. The green part is the pattern matching aspect. So I'm going to have to compile my pattern matching so that it works. The blue bits are, I'm going to take pieces inside the representation, and so I have to be able to extract those pieces and use them. And the teal, I don't know what's its color in English, this color represent constructors, which means that I have to be able to construct values, of course. And so there is one more complicated at the very beginning. So this is the big piece I will have to compile, and so let's try to give you a hint of how it compiles. Any question at this point before I move on?
Yeah, so this is a small one. If you have multiple, you said you could have multiple representations show at the same time.
Yes.
So you would have to do all the possible
Yes.
combinations.
Yes, we can do that. Here, in this specific case, implicitly you're choosing one here.
Oh, okay.
Yeah. We don't specialize the code. You just give us one, and we do it.
So when you write code, you have to say this is a function that applies on this specific representation.
In our prototype DSL, yes. In a real language, I don't know what's the best solution for that. I think it depends a lot on the language. Okay. I have expressed my memory type. I have associated my nice high-level data type with a memory type, and now I need to do my compilation. And so, as you've seen here, the code is completely standard ML-like code with constructor. With algebraic data type. There is nothing special in the code whatsoever. All right, so let's first go quickly over the pattern matching. So pattern matching, if we look only at the pattern matching, it looks like this. You have a bunch of cases and maybe some nested constructor. And so for this, we're going to output a layout-specific decision tree that's going to look directly inside the representation to the specific bits. And so if you want the details for that, you can look at the paper from ICFP last year. I'm not going to go into much detail on that. But yeah, we can output the decision tree that does everything for us. You notice that in this pattern, I remove all the binders. That's not by accident. The decision tree is only going to tell us in which case we are, but it's not going to extract the values for us. So we need to do more work. So before we do more work, we're going to move to a slightly nicer intermediate representation. We start with this. This is the same code from before. And we're going to move to something like this, where all the binders are extracted and moved to the code as accessor. And so if we look at a specific accessor here, we have x, which is the original value, in the SW case, and we access the zeros field. It would not be a nice surface language, but for an intermediate representation, we are guaranteed that we are indeed in the SW case, so this is fine. Now, let's look a little bit how we might compile this kind of code and the work we have to do. So if we are looking at an instruction, a particular instruction, so this one here, and I call isCompressible on it, first I will match. And when I match, I will look at the two places in my type that I have marked as criterion to distinguish values in my memory representation. And that gives us which case we are looking at. And here we are looking at SW. And then I have to extract various bits. So if I want to test this expression. And so I have an accessor x SW0. It's coded at one thing here. So I can access it directly. This is easy. Same thing on the other side, x.thesw.1, this is this bit here, I can access it directly. And so I just need to do an access inside my word and do as the appropriate mask. Okay, excellent. Here the constructor are simple integer and I can find the right integer and do that. Okay, so this is still pretty straightforward. And finally, here I have another test which look at the value of the offset of star word. And in this case, this is split over 2 bits. Now there is the 5 bits at the beginning and the 7 bits at the end. And so I have to fetch both, glue them together, create a new value that I can then use. And so on integers, this is pretty easy. In practice, this can happen over arbitrary representation. So I can have an arbitrary representation on one side, another arbitrary representation on one side, combine them, and then expose a value. And so what we sort of realize is that basically we have to combine arbitrary morphism from one representation that reorder everything inside to another representation. And this is necessary to compile this. And so we have an algorithm that synthesizes the code for this kind of arbitrary transformation over representations. And so the compilation algorithm, I'm not going to show you. It's in the paper and you can look on the link on the ICFP website. It's a bit too complicated to fit into a few slides. But the key idea is we're going to go back and forth between 2 states. One state is I am building something in memory of a given shape, and I know this shape because I have the memory type. And so I will try to build all the structure, allocate the stuff in memory, and so on and so forth. And then at some point there is some bit that it's not known, and so I need to go look for it. And so I'm going to move to a second state. I am looking for something in memory of a given shape. And then I'm going to look inside the various pieces that I have, my different binders and all that, find the pieces and put them at the right position. And so we emit code in destination passing style. You saw destination passing style in the previous slide, conveniently. And we emit code with explicit casts and allocation on the different memory representation. So for the example, it looks like this. You don't have to read it. The important bit is that the bit in purple here is the pattern matching stuff. And here in green is the SW case, which gives a pretty compact code in practice. All right, I'm going to stop here. I think this is enough talking. So we have an expressive DSL for custom memory representation. It can capture lots of weird representation. We can encode what I showed you on RISC-V instruction, on NAND boxing, and so on and so forth. We had to invent new compilation algorithm for this. In practice, they are pretty powerful. They can do arbitrary transformation on memory layout. For instance, if you have a given type and you give 2 memory layouts, we can synthesize any transformation between the 2. We have a formal semantics and formal agreement, and all the compilation algorithms are proven correct, either in the paper or in Thais' thesis. So Thais is defending next month. So if you're interested in this kind of stuff, you can look at the manuscript as well. And that's it. I will leave you on a final funny representation, and I will take questions.
Thank you very much. I am going to. What is the target of your compilation?
Okay, good question. So we used to target LLVM-IR, And by doing this last bit of work, we realized LLVM-IR is too high level for us. It doesn't give us the right casts. We can do cast on memory representations that LLVM does not agree with because we have more type information. And so right now it's custom. We would like to go back to LLVM-IR shortly. But right now it's just, we have a custom target and interpreter for that target.
It looks like from this presentation that this language is good potentially for the description of the decoder types of use. So I'm planning to target system Verilog. It's Verilog for FPGAs because there will be a problem with timing, of course. So you cannot assemble combinatorial logics, which is very
we could do that. Well, okay. It's probably a good idea to do that. Personally, I have no expertise whatsoever in doing hardware emission. I'm very wary of the timing issues and all that, and I must admit I don't know much about it. So I'm not planning to investigate that in the immediate time. But yes, you're not the first one proposing this. Yes.
The future benefits seem to be very, very high, right?
Mm-hmm.
The benefits seem to be big, large.
Yes, I hope so.
You can see this pattern matching and understand.
Yes. So, I mean, it's a very low level, so it should work well at that level, at the hardware level. But yeah, as I said, I don't know well. I don't know much about it, so.
Have you tried to use this in the context of Linux kernel codes to verify the Linux kernel codes that use different representations? Because I would assume if this has been hand optimized, and yes, they have a library that they trust, but it would be nicer if you have kind of a verified code generator, right?
Yeah.
So they could write an abstract algorithm, have a ribbit specification, and get the highly optimized version out of it. Is that an avenue that you have looked into?
Not really. One of the reasons for that, I mean, this is definitely designed to be inside a programming language. If you want a verified toolchain, D'Argent does that very well. It does exactly what you would suggest. You write code, you specify some memory representation, which are slightly less complicated than that in many ways, but more interesting in other ways. It's not exactly the same expressivity. And then it emits C. And so, yeah, D'Argent does that very well. So I think Ilya Sergey also has a thing where it does a verified compilation of C to C. So yes, this is like, maybe you can do it with that, but this is definitely designed to be inside the programming language, which means that we don't try to go too far with, for example, size constraints or this kind of thing, checking that this field is exactly the size that you expect, or this kind of thing. We don't try to go too far because we want to be, we want everything to be decidable. But if you drop that part, then you can go the D'Argent route and discharge to a solver or a solver or a proof assistant and emit verified code. So.
No, I was not trying to go that far. The idea was just more to say, okay, if I have a specification in C that is more high level, and then I have my records there, and I have my types, and I write the algorithm like a textbook algorithm, and I'm kind of happy with it. Yeah. And then somebody comes along and says, "Ooh, but we have a performance problem here. You have to map these into this structure."
Yeah. So we can do that. Yeah. Yeah.
Do you have a system for that where I can have a C program, say, and then I add a ribbit specification on how to map the data structures into memory, and then I press a button and out comes a refactored C code?
So I would like to have a C output at some point, which would, I guess, help with that. Yeah, I would have to. My ultimate goal would be to put that into Rust, and then you would have that as well. Yeah.
Do you have like a nice way of representing all these memory information? Did you look or think about how to kind of automate, like, oh, I have a data type and maybe have some code that does stuff, and I would like to find the best memory representation for some definition of best for this code or this data structure?
Yes, so this is an university project. So yes, I would like to do that. Do you have 3 PhD students worth of funding to give me? No, my idea is twofold on that area. First, we could do a pretty decent job at doing it piecewise, like for example, looking at the algebraic data type and trying to generate a memory type that is decent, for some definition of decent. The difficulty is that it's a very complex set of trade-offs between, size, indirections, sharing, preserving sharing or not preserving sharing, these kind of things. So complicated trade-offs, so difficult to automate. The second route is doing what you do in Gibbon and local, which is to do a whole program analysis to figure out the right representation. So far, I'm not fond of doing that because I will never be able to put that in Rust. Or in any kind of normal language. And the last solution would be to be profile guided. And I haven't tried. I think it would be amazing, but it's definitely at least a PhD, at least a full PhD to figure that out. So, yes.
So, is there a reason that polymorphism isn't supported?
It's yeah.
What's the particular reason?
There are lots of reasons. It's difficult to fit polymorphism in that. There is a simple notion. If you put constraints such as every polymorphic type is boxed, it is a pointer of 64 bits, and whatever is underneath is whatever. You can add polymorphism, it will be fine. If you need polymorphism with unboxing across polymorphism, then you need a whole kinding system. So you end up with something that sort of what is in GHC really, and what is going to be eventually in OCaml if Jane Street wants to add it. So you get lots of complication. What we need to know is the size of the data. If we don't know the size of the data, then it doesn't work.
Yeah, so it's more of a, let's say, separate compilation for this whole compilation thing then.
Yeah.
Because you need to preserve types across module boundaries to figure out.
Yeah, and of course there is another solution, which is the Rust solution or the C++ solution, which is to monomorphize everything first and decide later. It's like a shoot later, ask question, shoot first, ask question later kind of approach, and then that would kind of work.
I just curious how is endiness a concern here, or do you assume certain endiness?
Sorry,
endiness. Yeah, the ending of the architecture.
Yes. What's the question?
Do you assume certain endiness of the architecture, or?
So far we did it everything traditional way, so it's little endian. If I can never figure out which it was.
Intel's little. So
Yes, exactly. So we do everything in little, but it doesn't really matter to us really, as long as we know. So we could vary it. But again, going back to Zen's question, I don't know how to expose. I don't know how to make it parametric, and I don't know how to expose that to the user. So, yeah.
Would it be possible to have sort of a parameterized representation? So for example, I can represent any size of floating point number, and then I do like calculation with the parameter so that I ensure that the correct properties are always...
So we tried very hard in Rebit not to have to do any kind of integer arithmetics.
Okay.
Because decidability. That's the main reason. Could we add a little bit and have a solver on the side? Maybe. If it's only like linear constraints, then we could do it. But I expect if we put a little bit in it, people will want a lot more. Yeah. But the good thing is that so far we haven't needed to. We haven't really found a very good example where we would need that kind of power for what we do.
I imagine it would be kind of useful for example, doing machine learning with mixed precision operations, things like that. So you can use a single program representation to have like automatically converting between the different like specific representations with different sizes and always ensuring that they are equivalent.
I don't know. I would need to see the example. Yeah, I would need to see the case. But one thing I need to add is that we don't have arrays. When we have arrays, which is the next thing we want to add, then we might need a bit more arithmetics.
Okay. All right. Should we wrap?
I think so.
There we go.
Okay, welcome back everyone to the afternoon session, first afternoon session of FProPer. I hope you're all well caffeinated and wide awake. For the first talk by Carl Henriksen, and he's going to talk about actually pretty amazing work because he did a lot of footwork, I think, which is very, very useful for many of us who work in this kind of, in the field of area languages by analyzing performance differences and the reason for performance differences of OpenCL, CUDA, and HIP as compilation target. So, please go ahead.
Right, thank you. So, yeah, this talk is going to be about my experiences targeting GPUs from a compiler using 3 different APIs. So I'm not going to assume too much GPU experience here, so I'm going to mention some very high-level details, and as necessary, I will explain some more details. There will be a lot of simplification here, so if you actually are a GPU expert, you may think that I am leaving out some things, and that is correct, I am. And partially that is because I am not actually, in my work, I'm not actually exploiting the full capability of GPUs. That is kind of I'm using some kind of a common denominator features, so not only am I leaving them out of my work, I'm also leaving them out of my presentation here. So just be aware of that if you are a GPU expert yourself. Okay, so how do GPUs work? The most important thing is that they don't just directly execute code the way we do with the CPU. We can't just do a few instructions on the GPU and then continue on. It's a completely separate instruction stream. Specifically, GPUs are coprocessors. They are a separate computer inside of our main computer that we send orders and data and such through various complicated APIs with the CPU itself in charge. Now, that is not strictly true. You can also just have the GPU in charge, which is the case in some weird architectures. But from most programmers' perspectives, this is how it works. And maybe you have multiple GPUs. That's not going to be my focus here. But they are coprocessors. They're not in charge. They receive orders from the CPU. They are also not directly part of the instruction set architecture or anything like that. They are just these opaque PCI Express devices somewhere on the bus. And the GPU vendors don't really document in detail how they work, and when they do, they change the details frequently. So you don't directly access them using the lowest possible level interface. You access them through various complicated software APIs that the GPU vendors provide. Some of those are pretty well known, like OpenGL, Direct 3D, Vulkan, whatever. These are pretty common, and they are all for graphics. And that's not what I'm going to be talking about here. My focus is not on using GPUs for graphics. My focus is on using GPUs for computation. I think the most noble GPU is the one that doesn't even have a monitor output, because graphics, of course, are, I mean, that's not academic enough, right? Also, GPUs for compute have, of course, become very popular since, I don't know, past 18 years. And if you look at NVIDIA's stock price, it's was a pretty good idea. So GPUs are interesting because they are a very affordable way of getting a lot of compute very easily. There are more efficient architectures that are more powerful architectures, but they're also much rarer and more difficult to program. So GPUs are now and in the immediate future, and also kind of medium-term future, going to be of interest to most people who care about high performance. So the main GPU API and the first kind of real high-level general-purpose programming API was CUDA, released by NVIDIA in 2007. There were a few attempts at doing general-purpose computation using the graphics APIs before then, where you had to kind of express your computation as if it was some kind of texture operation or whatever, which some people managed to do and get good performance out of, but it was very difficult to program. But NVIDIA could see that people really wanted to use their machines, and, well, why not let them? So they made CUDA in 2007. It's completely controlled by NVIDIA, so it's proprietary, not just the software, but also the spec. So, which is great for NVIDIA, because that means when you use CUDA, your programs will only run on NVIDIA GPUs. And again, NVIDIA's stock price is a pretty good indicator of the success of that strategy. So today, CUDA is pretty dominant for various reasons. Some technical, some societal. NVIDIA also spent a lot of time donating GPUs to researchers, which was also a very excellent investment. But of course, the other companies producing GPUs and accelerators and hardware didn't really like the idea that NVIDIA controlled everything. So they came together and created OpenCL, which I think was originally by Apple, but then donated to Kronos, which has maintained it ever since. So that's an open standard, and it's still being maintained by Kronos. It has been implemented by NVIDIA, AMD, Intel, and various other people as a part of the universal standard for programming accelerators. It's not really GPU specific. I'm going to treat it as if it were GPU specific in this presentation. And I would suspect most of the users of OpenCL use it to program GPUs. But it can also be used for CPUs, FPGAs, and other weird things. It's a high-level accelerator API, they call it. It's not nearly as popular as CUDA for various reasons. One is perhaps that the API is a lot less friendly than CUDA. In CUDA, you have this combined single-source C++ dialect that is maintained by NVIDIA, where you can just mix CPU and GPU code in a pretty nice way. OpenCL is just a pure library, no language modifications, so the API is a lot more verbose, and you have to do manual online compilation and so on. So it's not nearly as popular. There's also HIP, which came out very recently. It's still developed by AMD, and is a strategic response to the fact that CUDA is controlled by NVIDIA and is used by almost all GPU software. It's essentially a re-implementation of the CUDA API, where they just did a search replace and replaced CUDA with HIP. So it's almost entirely identical, with a few improvements where they simplified some of the historical baggage in CUDA. But the idea is that you can take your CUDA software and translate it to HIP software, and then HIP is implemented both on top of AMD hardware and NVIDIA hardware, and on NVIDIA hardware just directly mapped to the corresponding CUDA operation, so it will run with no overhead. So that's the idea, a single way of programming both AMD and NVIDIA GPUs, and even provides some tools for automatically translating CUDA programs to HIP programs. I haven't evaluated that part of it, the automatic translation. AMD claims that it works great because, of course, they claim that. I have tried it a little bit, and it does actually work surprisingly well, but that's not really what I have been working on. Now, what I have been working on is that, well, we have this situation, 3 different APIs. Which one should you use for your GPU targeting compiler? There's a lot of superstition around these APIs. For example, OpenCL has this reputation for being slower than CUDA. Maybe NVIDIA's implementation is even sabotaged to be artificially slower, because of course NVIDIA, as the big evil company, wants that proprietary API to work out. There's lots of suspicion about that. Is it true? Who knows? Does HIP have any overhead compared to CUDA? Well, who knows? Which are easiest to use, and are there any real fundamental differences between these APIs? The reason why I think there are a lot of superstitions here is that it's actually really hard to have an opinion, or an informed opinion, I should say, about the differences. Because these APIs are all super low productivity. It takes forever to write anything with them. They are low-level APIs. So very few people have substantial experience in more than one of them. And of those who do have that experience, usually will only have worked on 1 or 2 programs. But no one has experience writing a lot of very different programs using these APIs, or at least without their own experience changing along the way. If you start out writing a CUDA program, learn a lot of experiences, then write a corresponding OpenCL program, those programs are not going to be equivalent. They're going to be very different, probably, unless you just learn absolutely nothing in the first time around. And no one is going to then re-implement an old program just to see if there's any difference. That's not really realistic. It's very boring and it's very time-consuming. So there has been work on investigating this stuff. In particular, OpenCL versus CUDA is a very popular subject of study. But they look at just a few applications, because there are not really that many applications that are equivalent but implemented using multiple APIs. Because again, it is super boring, and it is sort of an offense to human dignity to actually do that, because it is really a waste of human time. So what I have done in this work is that, well, we're working on this compiler for Futhark, which can generate GPU code. So this is a machine wasting its time, not me. And we have implemented backends using these 3 APIs. So we do have a source of equivalent programs, because they come from the same original high-level specification, that are then turned into code using these 3 APIs in a way that is, in principle, equivalent. And I'll quantify a little bit how I mean that they are equivalent. So then the question becomes, well, how do these programs perform? We can actually look at it systematically without any real noise, because they are the same programs, just using different APIs now. So this is Futhark. It doesn't really matter as a language for this presentation. It's a high-level functional language where you can do things like map to apply a function to every element of an array. You can use reduce to combine an array to a single value, and then you can also map a parallel function over a 2D array, so it has nested parallelism. It's a pretty conventional language within this area. There's lots of similar languages and libraries, so the observations that I make here are probably going to apply to all of them. It's not really a very FProPer-specific presentation. The way you program parallel code in FProPer is that you use a vocabulary of parallel second-order combinators called SOACs, which again are pretty conventional. So you have your map that where you apply a function f to an element of an array. This might look different in different languages, but the concept is usually there in some way. You have a reduce, where you use an operator to reduce elements of an array. You have scan, which computes with the prefix, the reductions of the prefixes of the array. This is also sometimes called a prefix sum. And then you have some things that are a little bit more exotic, like the histogram operator here, which, can I check this? Which kind of does a reduction per index. So in this case, it says, take the value 2 and add it to whatever, to the bucket at index 1. And you see, and also here, it will add the 3 to the bucket at index 1. And you see at index 1, you have the 5 here, so that's the 2 plus 3. And here for 1, you have the 0, it goes here. So that's just a kind of, it's a special case of a certain kind of reduction, which turns out to be implementable more efficiently than if you just use the other primitives to construct it. So FProPer has a few kind of a little special constructs for performance reasons, but mostly it's a very standard kind of programming model. And then the compiler, the backend, has a recipe for turning each of these into GPU code. It's a lot like these skeleton-based libraries, where there's just a complicated recipe, where it actually looks in detail at what's going on, and it knows how to turn like a reduction into an efficient GPU reduction program. I can return a little bit to exactly how that works. So we have 3 GPU backends. The first one was OpenCL, which we developed in 2015. Then a few years later, partially based on this paranoia about whether OpenShell was maybe sabotaged or a few things that CUDA made possible that is not possible in OpenShell, which I'll return to. We made a CUDA backend 4 years later, actually done by a student. And then 4 years later, last summer, I added a HIP backend because I had an AMG GPU that I could not take proper advantage of through OpenShell, and also return to that. So we have these 3 backends, and while you might think that the OpenShell one is maybe have an unfair advantage because it's older, more mature, or maybe a disadvantage because it's older and more mature, it turns out that the way we did it is that we created a GPU abstraction layer that we came up with for ourselves. It's not really a reusable one, that the compiler really targets. And then the CPU code, the code that runs on concurrently with the GPU, is very similar, no matter which abstraction layer that you use. I should also mention that we're going to be looking at some performance results, and these performance results are what we actually observe using the real FProPer compiler, which is not a perfect compiler. It's just what we managed to construct over the past 10 years or so. So it is possible that some of the differences we see could be removed by having a perfect compiler. And I would very much suggest that someone write such a perfect compiler and then write a follow-up to my paper. That would make me very happy, especially because then I can use this perfect compiler and save a lot of time myself. So just remember, this is a kind of a practical experience report, not a kind of final theoretical answer to what are the differences between these APIs. Okay, but let's look at how they work. So these GPU APIs at the level that the FProPer compiler takes advantage of them are very similar. You need some kind of way to allocate memory on the GPU. It's a separate computer, remember? So it's a separate memory space. You can actually map it into the CPU memory space, but we'll pretend you can't. You need a way to compile GPU programs, which are called kernels, into GPU machine code. And then you need some functions for submitting work to the GPU. Call this kernel function, copy this memory somewhere, and most of these are asynchronous operations. So the program model is that a GPU kernel, a program, consists of tens of thousands of threads that are essentially running a sequential C program, plus some functions for synchronizing, if they actually want to communicate in some ways. But it is kind of a C-like language. And they're surprisingly very similar between all of CUDA, OpenShell, and HIP. So you run this kernel compiler provided by the vendor, access through the API, that turns these C programs into GPU assembly machine code. And this is typically done at runtime. You can do it ahead of time, but because GPUs vary so much in the actual machine code they use, you typically don't know which machine you're going to run on. You have to do runtime compilation. And then you can cache it and all that stuff. That also means you have a chance to specialize very late during program startup based on the specific GPU you're encountering, which can be used for good and also sometimes for evil. I won't go too much into that. The paper mentioned some examples. So this is a slide full of C code, because everyone enjoys that. This is really just the prototypes for the abstraction layer that we're using. The point here is just to show that it's not very large. So there's some kind of abstract context type that contains a bunch of state. Then there's a type for GPU memory and a type for GPU kernel. And then there are functions for allocating memory, freeing memory, and copying memory. And we just have to implement this interface for all of the APIs. So in CUDA, in OpenShell, and in HIP. And then there's a whole bunch of initialization code, which is actually the lion's share of what the backend implementations actually look like. There's maybe 500 lines of initialization for CUDA and similar for the others, which is very bespoke to the specific backend. Then there's a few other functions, 2 more. One for getting a handle to a named GPU kernel, so a GPU function or program, and then one for launching it. And there's a bunch of parameters you provide about how many threads and so on, which are not super important, but this is just to show how small the interface actually is. So if we can implement these, 7 functions, then we can add a new backend. At least if that backend is conceptually similar enough to the existing ones we have. Okay, so then the question becomes, okay, so is there any performance difference? They do the same thing. We can run them on the same hardware, at least to some extent. So is there any difference at all? So the idea here is that we just take the same FProPer programs, compile them with the various backends, and then see how they stack up against each other on the same hardware. Specifically, I've run this on an NVIDIA A100, where I have compiled with the OpenShell and CUDA backends, and on an AMD MI100, where I have compared OpenShell and HIP. So specifically, I have not run the HIP backend on NVIDIA, even though it's supposed to work, because for reasons that are not super interesting. But HIP is not supposed to perform differently than CUDA on NVIDIA. And there are other papers that investigate that, so I've kind of left that out. So each of these benchmark programs have different workloads. I mean, you can think of them as input sets that can behave differently. And the way my metric here is that I take the average speed up over all of the workloads per benchmark, and then that characterizes the benchmark. And as we'll see, if you have a high standard deviation for a benchmark, that doesn't mean the individual runs, of course, also do more than 1 run per data set. That doesn't mean that they differ a lot. It means that the different workloads have a significant difference in the speed of when comparing the two backends. It's actually a bit tricky for me to figure out how to characterize such a large data set in a way that makes sense, because every single data point is interesting, so I can't just take the average. You'll see in the next slide that it's surprisingly difficult to get a grasp of what's going on. I have 48 benchmarks, which is pretty large. It's an order of magnitude more than most papers of this kind, because no one is going to write 48 programs by hand in multiple APIs. But writing 48 FProPer programs, or asking your students to write 48 FProPer programs, that is more achievable. Okay, so these are the benchmarks. They are all from published benchmark suites. Originally, they are written in, well, one of them is Accelerate, the others are usually handwritten CUDA and OpenShell programs. And I will say that the FProPer performance is pretty close to the original performance. Some cases better, some cases worse. So these are not pathologically bad programs. They're programs that kind of behave as well as you would hope to. Okay, so let's look at what the differences are like. So this is actually a condensed form of the unreadable graph in the paper. What this shows is a speed up of OpenShell versus CUDA and HIP respectively on the 2 different GPUs. So higher numbers means that OpenShell runs faster than the other API. So for example, we can see that on the A100, on the n-body benchmark, on average we get a speed up of 1.43 when using OpenShell compared to when using CUDA. But you also see this huge standard deviation, which suggests that it actually varies a lot based on the data set, how much the speed up is. So we can see for some data sets it's actually slower. OpenShell is slower than CUDA, and on some it's faster. So it's data set dependent, which is, of course, the worst kind of dependency. Whereas for others, I mean, the standard deviation is pretty small, which shows that the difference is not really data set dependent. And we can see that the differences range from about 40% slower with CUDA to 43% faster, and sort of similarly on the MI100. So they're all within a factor of 2, almost, except this one. So yeah, it's not a disaster, but it's not also kind of weird. So let's look at, I could leave it at that and say, yes, there are differences, but of course I didn't do that. And then I went in and did some very tedious work looking at each of these and trying to figure out what is the cause of this performance difference. So that's what I will try to give you an idea of now. And this is extremely time-consuming, because we have to look at every single program, use low-level tools to figure out what's going on, inspect its actual operational behavior, and then try to figure out why it does the way it does. So it is difficult, but in most cases I've been able to figure out why we see these differences. So one interesting difference that was almost a little bit depressing to discover is that by default, OpenShell actually allows programs to be wrong. It allows the kernel compiler, remember the thing provided by the vendor that compiles the kernel code to the actual GPU as machine code, to incorrectly round floating point, single precision floating point numbers. Probably this is for historical reasons, because all of this is originally based on graphics, compilers, and so on. So you actually have to pass a flag to OpenShell to tell it to actually don't break my program. And this is the reason for these performance discrepancies where OpenShell outperforms CUDA and HIP. So this is why the n body here is much, much faster, because it has a square root and such in its innermost loop. And apparently NVIDIA's OpenShell compiler is really aggressive about not doing a good job here if you don't force it to. So yeah, that was something I hadn't actually realized before I did this study. Yeah. So did I check whether they produce the same output? No, and the reason I didn't is that they are all validating. We do have a notion of correct output, but there's a tolerance to it because all of these do things like do parallel open point, floating point summations, which is not deterministic. So there's a tiny bit of tolerance, and this apparently sneaks in under that tolerance. So that's why we haven't noticed. Although in retrospect, maybe some of the mysterious failures I've seen in the past have been because of this. I don't really know. Yeah? Sort of. The reason for the tolerance is that people want to do things like sum up floating point numbers in the programs they write. And if our testing tools don't allow that the small error that accumulates or the small variance that accumulates, then it's just really annoying to test the compiler because you end up getting false negatives all the time. So it's just a decision we made at some point to allow some tiny tolerance when comparing against the reference result, which may or may not be what you prefer. So another source of major differences is due to prefix sums or scans. And the reason is that the best known implementation or algorithm of scans on GPUs is the so-called decoupled lookback scan developed by NVIDIA researchers. And the way this scan works is that it really kind of goes against the way you program GPUs. And the essence of GPUs is that you don't communicate between threads. But the decoupled lookback scan algorithm sees a GPU sort of as a concurrent machine and does communication between threads in a tricky way to avoid manifesting large intermediate results in memory. So you end up having significantly less memory traffic than the kind of standard way of implementing scans. And this works on NVIDIA hardware. Essentially, the NVIDIA researchers made this work, and then NVIDIA realized this is important, this works, so then they basically phrased their memory model such as if you do exactly this, then it is guaranteed to work. But it wasn't really supposed to work originally, and it doesn't work in OpenShell. OpenShell doesn't promise that it'll work, but even when you run OpenShell on NVIDIA hardware, it doesn't work for reasons I'm not super clear on. Maybe the NVIDIA compiler will make assumptions that are true by the OpenShell spec, or do things related to cache behavior or progress across the entire chip that are not really that this algorithm depends on. It's not really clear why it doesn't work, but I have not seen anyone being able to get the decoupled lookback scan to work on OpenShell, on either NVIDIA or AMD hardware. So when you're using the OpenShell backend, the FProPer compiler will use a less efficient scan algorithm, and that results in these performance discrepancies for programs that are very scan intensive. Now there's one interesting case here, convex hull, where the kind of inefficient scan is actually faster on the MI100. This is probably because our implementation is tuned for NVIDIA hardware. We should probably look into that. So that's one difference between the backends. Now for the next difference, I'll have to explain a little bit about the GPU execution model, which is that, yeah, GPU kernels are split into threads, but then they're further split into thread blocks, which all must have the same size, bounded by some hardware limit, usually 1024. And together the blocks form a grid. And these blocks here are what is actually sort of scheduled at a course level by the GPU. At the hardware level then, each thread block is executed by a single streaming multiprocessor, which is called something else on AMD hardware. And what is interesting is that these streaming multiprocessors, they are an actual existing piece of hardware. They're not an abstraction. Have a small bit of scratchpad memory on them called shared memory by NVIDIA. And that means with the thread blocks on a single streaming multiprocessor can communicate with each other using this small scratchpad shared memory in a very efficient manner. And some algorithms depend heavily on being able to do that. Things like reductions and scans make heavy use of it. So balancing how many thread blocks you launch and so on, and how big they are, can affect how many of them can fit on the GPU at the same time, which can affect how much concurrence you have, and so on. And this is exploited by the FProPer compiler in a kind of tricky way. So typically these are very, very small buffers, like 48 kilobytes used to be common. I think on the newest NVIDIA GPUs, you have 192 on the entire streaming multiprocessor, which has to be shared between all of the thread blocks. So the more resources you use per program, or per thread, the fewer threads you can actually have resident at the same time, which has all kinds of implications for performance. It's very tricky to balance these parameters. And we don't really do a very thorough job of investigating the best trade-off in our compiler. But we do make tricky use of it. So if you have programs that look like this, where you have an outer parallel map, and then you have some parallel stuff going on in here, there can also be a loop on top or an if or whatever, there's just some parallel function here, then one way the compiler can generate code for this is to create one thread block, not thread, per outer map, and then the threads in the thread block will collaboratively do the parallel operations in here. The big advantage of this is that all of the intermediate results here, these are scans, but they could be whatever, the intermediate result will be stored in the shared memory, this fast on-chip memory, which is much, much faster than the actual GPU memory, which by itself is actually pretty fast, but the shared memory is even faster, but very, very small. So this only works if this parallel workload in here, including the data, will actually fit on the GPU within one thread block. Otherwise, there's another way of compiling this. And actually, the compiler will generate both versions, one where it fully flattens this out and does it all in global memory, and one where it does this kind of thread block-based compilation, and then runtime, based on the observed sizes of the data, it will pick whatever it thinks will be best. Basically, it will always do the thread block version if it fits, unless you tune it otherwise. So this has an impact on OpenShell, because on AMD GPUs, OpenShell thread blocks are limited to 256 threads, whereas on NVIDIA, they are 1,024. Originally, this may have been a hardware limit, because if you use HIP to target the exact same AMD GPU, this limit doesn't exist. It's 1,024, like it has always been on NVIDIA. So the hardware is clearly capable of running larger thread blocks. And there is some fine print that applies to why this restriction may still exist. I won't go into that. It just means that if you just write a straightforward, naive OpenShell backend that just asks, well, what's the biggest thread block I can launch here, or even just try to launch one that's bigger, then you will be affected by this limit. You have to be really tricky in order to get a higher thread block size on OpenShell. And that means that some benchmarks that depend a lot on this this thread block level parallelization, they really suffer because they have to use a much slower global memory code version instead. Essentially, you get worse locality. So you can see we get these slowdowns with OpenShell compared to HIP, which is tragic because the hardware clearly supports what we need. It just doesn't expose it in the way that you would expect. Similarly, on OpenShell, you cannot query the level 2 cache size. OpenShell does specify a hardware thing you can query for called mem cache size, but it doesn't specify what that cache is supposed to be. So it's a level 1 cache in AMD, and usually it doesn't matter so much, but we have some adaptive algorithms, especially for these histograms, where we do multipassers and such based on the cache size to do some locality optimization in a complicated analytical model. And this doesn't work if you don't know what the cache size is, so we'll just run slower. And if you think this, you get the level 1 cache, if you treat the level 1 cache size as a level 2 cache size, then you get very bad performance. So instead on OpenShell, on MD, we actually query for that in the runtime system. It just has a heuristic guessing at what the cache size might be. But it doesn't get it right all the time, as you can see. Similarly, OpenShell doesn't provide a way of querying how many threads are needed to fully take advantage of the GPU. So again, we have a heuristic, which is usually smaller than the correct number and has performance implications. Now, what is interesting here is also that the performance is not always worse with our guess. It's actually sometimes better, because there's no reason to think that the max capacity is actually the optimal capacity. The optimal number of threads to launch for a given GPU program, when you have a choice anyway, is pretty difficult to determine. Usually you need to use some kind of auto-tuning technique, which we don't. We just ask the hardware or make a guess, and then we run, and then this is what shows up. But the important thing here is that we cannot make the same choice on all of the backends, because OpenShell simply doesn't provide the information, so we just have to make a guess. We could, of course, make the same guess with CUDA. After all, it's just something we made up. Another cause of performance differences is what I call API overhead, because that's for some benchmarks where I can clearly see that there's a difference in how fast they perform. But when I look at the actual performance metrics, I can see no difference in the performance or in the time taken for the actual GPU operation. So the kernels, the memory copies, all of that stuff take essentially the same time. So the time is spent on something that is not measured by the GPU profiling information, which means it must be CPU side work. And since HUDAC itself does very little CPU side work besides calling the APIs, these performance differences are due to the APIs themselves into having overhead. Because putting things in a queue, of course, is not free, and in some cases it is pretty costly, especially if your actual GPU workload is very small. For example, for in-body, we have a very large variance here, which is almost entirely due to a single very tiny workload with, I think, 1,000 bodies or something. That takes almost no time to run, and is almost entirely overhead. And apparently, that overhead is greater with CUDA than OpenShell on that machine. Sorry, no, other way around. It's higher with OpenShell than CUDA. That's why we see this large variance here. So for some data sets, OpenShell is much faster than N-body. And similarly here for the M100 for some of the data sets. That is, of course, not really great. Generally, OpenShell is slower, but there are exceptions. And I don't really know, maybe we're just using OpenShell in a very bad way. But I don't really see what we're doing wrong. But again, if someone writes the perfect compiler, then I can figure that out by looking at your code. Another thing is that FoodDoc actually does bounce checking, as you should do in a high-level language. And that's done with a pretty complicated program transformation discussed in another paper. That it's essentially based on inserting certain go-tos, so that when a thread encounters a bounce checking failure, it shouldn't just terminate itself immediately, because the GPU APIs do not provide a way for a thread to terminate execution of the kernel. A thread can terminate itself, but then if there are synchronization things like barriers inside of the kernel, you end up with undefined behavior, so that you might just deadlock the entire program, which is not a very good way of reporting an out-of-bounds error. So there's a complicated program transformation that ensures that even in the case of errors, all of the threads will just kind of wait until they get to a consistent control place in the control flow, and then they will check whether anyone failed, and if so, they will all bail out collectively. The way this is done is essentially by introducing certain go-tos to jump out of nested loops and control flow. It's kind of equivalent to returning from a function, really. This is allowed according to the specs because it doesn't induce, the way it's done is in a way that doesn't induce unstructured control flow. It only jumps forward in the execution. But the control flow is very weird compared to what normal GPU code looks like. So some of the compilers clearly choke on this kind of stuff and probably disable some of the optimizations or do a bad job at register allocation or who knows. I just see that they do a much worse job generating code when this fairly benign control flow is present, but only for some programs. It's specifically only this program, a lattice-Boltzmann method, which is just got a big stencil, which for some reason just goes completely nuts when bounce checking is enabled. And interestingly, on the NVIDIA platform, OpenShell becomes much slower. OpenShell becomes slower with the bounce checking enabled, and on the AMD platform, OpenShell becomes relatively faster, meaning HIP becomes slower when bounce checking is enabled. So yeah, that is just some kind of black box compiler that doesn't like the code we generated in this specific case. And it's a little bit unclear why LBM is such an outlier. Which leads me to the final course, which is sometimes the code is just cursed or something. There are some programs where I simply was unable to figure out why they got slower. And that's partially due to time. I could look at the disassembly for these programs and figure out what the difference is between the machine code generated by OpenShell and the machine code generated by HIP, but that's a lot of work, to put it frankly. The investigation I did do suggests that this happens for kernels that are very compute bound, and I suspect are very bounded by how many registers that they use. So if you use more registers inside of a GPU kernel, that means fewer of them can actually operationally run on the GPU at the same time. And so I suspect these are just small differences in register allocation strategies between the two compilers here that for some reason have a significant impact on performance. Like Tunnel here, for example, it's not a real program. It's taken from Accelerate. It generates very nice images. It simulates the Doctor Who intro, I think. It barely touches memory. It's just floating point arithmetic. It's super compute bound. And so this kind of performance difference is very difficult to explain. The other programs also do some kind of very fancy, very highly optimized things. These are programs that actually run really fast. So I don't really know why OpenShell and HIP behave so differently on the MI100 here. Right, a final course, which isn't really a course, but I want to mention for completeness. None of the programs I've been looked at for this paper encounter this, but OpenShell does not expose floating point atomics, although CUDA does, and so does HIP for that matter. You can simulate them using compare and swap operations, but that is, of course, slower. So if you have a program that depends on this, it will run slower with OpenShell because these operations have to be simulated. And this is a bit tragic because, again, clearly AMD's hardware is capable of doing something here, because HIP does support this, but they don't expose it in OpenShell. And I think that might actually be a limitation in the spec itself. I think OpenShell say that this is even supposed to be able to exist. All right, so the question is, can we solve this? What can we as a compiler implementer do to fix this? Well, one thing is we can pass the flag to OpenShell, telling it to actually compile the code correctly. So I've tried to do that. The other thing is that we have a lot of problems that are related to OpenShell not telling us that much about the GPU. So we can, of course just pass that information. I mean, query it using whatever tools we want and pass in some tuning parameters to the program saying this is actually how many threads you should use, this is how big the cache is, and so on. And then at least we will make consistent choices. So I tried that, and then I get these results. So I don't know if you remember the original graph. I don't think so, but the kind of span has narrowed significantly. We still see OpenShell is a lot slower for programs that depend heavily on scans, because this doesn't solve the problem that we're using a different scan algorithm. But we don't have so many of these cases where OpenShell is just much faster for reasons that are not really fair, because it generates worse results. There is one interesting outlier here, which is that quicksort with OpenShell on the MI100 is much faster than with HIP. And this is interesting because quicksort is actually a scan-bound program. But the way this quicksort is written is with a really nasty scan operator that has like 8 operands, which doesn't work at all well with the decoupled lookback scan, which is some register-based locality optimization. It assumes much smaller operands. So in this case, the 2-pass classic scan is actually faster than the decoupled lookback. So probably we should teach the compiler to think a little harder about what the operator is actually doing and not use a decoupled lookback in such strange cases. All right, so this managed to narrow the gap somewhat, but there's still some really weird differences that are kind of unfortunate, despite these APIs in principle being equivalent. So my conclusions based on this work is that it's actually not difficult to target all of OpenShell, CUDA, and HIP. They are conceptually very similar, especially if you don't need any fancy features. So CUDA in particular has lots of things that we don't take advantage of in the compiler. We don't do dynamic parallelism. We don't have things like tensor calls or do warp level operations. We might want to do that. And these are mostly things that happen inside the individual GPU kernels. So we can also perhaps do it without modifying the host side abstraction layer. And with respect, it's also pretty easy to target the other related APIs as long as they have full support for computation. But performance portability remains tricky. Part of that is that the different kernel compilers have different defaults. Also, that OpenShell does not expose some hardware features, and the kernel compilers themselves are millions of lines of code. They all have LLVM with hacks inside of them, so who knows what's going on? I mean, for AMD, you can actually figure out what's going on because it's a full open source stack, but again, it's millions of lines of C++, so it's kind of, you can ask the question, but you also have to find the answer yourself. So if you only care about targeting standard NVIDIA and AMD GPUs, I would suggest that targeting OpenShell is probably not worth it, because most of the problems that we talked about here are, in some sense, OpenShell's fault. Now, with OpenShell, you can also target Intel GPUs, which you might find important. And Intel also has their own family of APIs that I haven't investigated, so maybe there's another way of doing that. So I would suggest just doing CUDA and HIP, because they're very similar, and then you can run on AMD and NVIDIA GPUs, and those are the most important ones for HPC anyway. All right? My setup is available if anyone wants to take a look, and I hope I didn't go over time.
And I think if I got it correctly, the reason that you say it's not that much work to write backends for your compiler for all these different architectures is simply that you don't use many of their features that make them different?
Partially, it's also because here you have, so if you use this abstraction layer by hand, when you wrote a program by hand, then it would probably also be easy just to switch out the implementation of the abstraction layer. But that's not how people write programs. When you sit down and write a program, you don't start by writing your own little abstraction layer. So you could have done so, but no one has actually done so. The exception is people who do things like Cocos and the other high-level libraries. In principle, they could also do studies like this. They just haven't.
So a lot of the pressure on the GPU market these days comes from people working on these very aggressive, large-scale LLM workloads, transformers and stuff like that, and various variations on those architectures. where a lot of the pressure is to try and hit like the speed of light computation speed available from the hardware. And I'm curious if like any of the stuff that you're working on here gets near that kind of speed of light limitation on the GPUs, and like, what would this look like if you like there was like a Thunder Kittens kind of style benchmark in the middle of this?
So most of these are application level benchmarks where it's not often clear what the speed of light might be because they are large and complicated. There are two of the benchmarks where I know we get pretty close, and that's matrix multiplication. It doesn't beat cuBLAS, but it's kind of competitive. No, it's not competitive. It's slower than cuBLAS, but it's not, an order of magnitude slower. And scans, where we are close to the memory bandwidth, also for reductions and just plain maps. So all of the primitives are actually close to the peak memory bandwidth. When you need to do things like tiling, we are okay. I mean, with a factor of 2, definitely. But no, this is not. This doesn't really approach the speed of light in general. Which again, what I mean that this is kind of what you get when you write a compiler for application programming and you don't have NVIDIA level resources to spend on every single application. This is, 2 or 3 people working over years to create a compiler for a very rich language compared to what you see in machine learning.
So on your intermediate language, on your abstraction layer, I saw that you have explicit memory transfers.
Yeah.
But in particular, CUDA offers like 3 or 4 different memory models that you can use. Yeah. Have you investigated any things there? I mean, I don't think OpenCL offers that.
So by memory model, you mean things like shared virtual memory?
Well, like they have this unified memory, they have memory that is pinned or not pinned.
Yeah,
and that has all implications on the bandwidth that you can get between host and GPU. Right. It has implications on the maximum memory that you can allocate and things like that.
No, so the short answer is no, we haven't investigated, and that's partially scar tissue from our original backend, which was OpenShell. So we treated the GPU just as a completely different world. The memory is way over there, it's opaque, it's abstract. We have to manually copy back and forth, and that has become part of our abstraction layer. Now, we have actually enabled what NVIDIA calls, I think, unified memory. You can enable that, and then through our Futhark's external API, you can get one of these abstract arrays and turn it into a pointer and directly interact with it. So it works. I have observed that for the ways that Futhark actually uses memory, it becomes slower. So it's not really worthwhile. And it is something that we are not really able to take advantage of within the abstraction layer as it is right now, which is unfortunate. And especially for multi-GPU applications, this will be a problem. So we will need to extend it when we start worrying about that.
Mm-hmm. Okay, thank you.
Hi, thanks for the great talk. How would things be different if Futhark supported tensor cores? And you could encode maybe some of the not obviously matrix multiplication computations as to use tensor cores, and also would you imply that cuBLAS doesn't use tensor cores if you get comparable performance?
I don't think cuBLAS uses tensor cores, at least not for everything, because tensor cores also sacrifice performance and accuracy. And that's a very weird thing to do in a general purpose matrix multiplication. So they probably have some functions that do. If we want to use tensor cores, so those only really happen at the kernel level, so inside the device code that I didn't talk much about. Which means we could actually support them without modifying this abstraction layer, which is entirely about resource management. And we are actually starting work on that. So I think that will just work, but obviously will only apply to the CUDA and HIP backends.
Any other questions? If not, then let's thank Troels again. speaker is David van Balen, and he's going to talk about work he did on basically having a very aggressive fusion algorithm, kind of optimal fusion algorithm using integer linear programming.
Thank you. Yeah, so I wanted to kind of jump right in with an example to show what I was talking about. So in this talk, I'm talking about languages very similar to the one Truls was also discussing. So a functional array language where you have combinators like map, for example, to work on these arrays, which compiles down to, for example, parallel GPU code. In such a language, one of the very important optimizations you need in order to generate efficient code is fusion. So the idea with fusion is taking multiple of these combinators, doing something with them, and in the end generating a single parallel loop or a single kernel that evaluates all of these combinators. In this slide, I'm showing one function which has 3 maps, and there's 2 different ways in which you could fuse this function. So there's these first 2 maps, A's and B's. I'm going to refer to the functions by the name of the array that they produce throughout this talk. So these first 2 maps, A's and B's, both take the same input array x's as their argument. So one of the things you could do is fuse those 2 passes over x's together to write a single loop which consumes this array and then produces both of those outputs. Another thing you could do is combining A's with this final map, where you're kind of fusing away the intermediate array A's completely. So the idea here is that during your loop, you're reading an element from X, multiplying it by 2 to get an A, and then immediately using this A in the function argument of the last map. So in this case, you're accessing the arrays B's at the place, at the index indicated by this element A. I hope everyone's with me so far. So these are kind of the 2 ways I would say you could fuse this function. The reason you can't fuse B's with the final map is because there's this explicit indexing operation. And kind of the assumption I make here throughout this talk is whenever you have this explicit indexing, that means you don't know anything about the structure, so you need this array B's to kind of be manifest to be able to read from it at some random index. So aside from map, these are some of the other combinators that I'm supporting in the language I described in the paper. These might include some combinators you might not know yet, or not include some other combinators which you did expect. If there's time left at the end, I can elaborate a little bit on exactly why I chose specific versions of these combinators. The most important one of this list that I wanted to talk about a bit is gather, which is also the one mentioned in the title of this paper. So the idea with gather is that we've got, it's got 2 arguments, i's and x's, and this first array contains indices into the second array. So kind of computationally what a gather would do is loop over this first array. Every time it finds one of these indices, it looks it up the corresponding element in the second array at that index, and then generates an array with this new list. So it's kind of reordering x's, or part of x's, maybe. So if you squint a bit, that's kind of exactly what this final map is doing here. So you could also, if you know this pattern, you could rewrite this into gather A's, B's, instead of map with B exclamation mark. Once you do this rewrite, then we'll see in the talk that it is actually possible to fuse all 3 of these combinators together in a single loop. But I'm going to talk a bit about the intricacies of when you can and can't fuse gathers. One other small thing I wanted to mention here is that specifically for this gather, you see that it's got this weird L label. Really all this means is at the start of this whole analysis, we're going to give each gather in our input program a unique label, and we'll need those labels later. Okay, so the key ideas that we're I'm going to talk about are first we're going to formalize this array fusion. So when can you fuse arrays and what's kind of the output of fusion as a binary operation. Of course, you might want to fuse more than 2 of these combinators, which just means you're going to have to apply this binary combinator multiple times. Second key idea is that in order to figure out when we can fuse these gathers, we're going to have to think about the order in which we're consuming or producing arrays. And then in the end, as the title already implied, I'm going to extend one of the existing interlinear programming solutions, which did not support combinators like gather, to also think about gathers. So this is not quite formalization slide, but this is kind of the intuition between 3 sort of categories of fusion that I will use, mainly to introduce the terminology. So whenever I say vertical fusion, I mean this pattern where we've got 2 combinators one after another, and in this case we're vertically fusing over the output of this mapg function, which no longer needs to be manifest at all. So this array can be completely fused away. So horizontal fusion is just when 2 arrays take the same input, and diagonal fusion is very similar to the vertical case, except we actually will need to manifest this intermediate result as well, because it's going to be needed for some other computation, or maybe the output of our program. In my fusion thing, I'm going to be considering each cluster of arrays, or each combinator, as purely 2 sets, namely the set of input arrays and the set of output arrays that it has. So of course, for an unfused program, each cluster is just going to be a single combinator, and for a fused program, maybe there will be more. So in this case, we're talking about a program, or a combinator or a cluster, which takes as its input arrays all the arrays in I1 and produces the output arrays in O1. And then this is my kind of fusion judgment. It says, okay, given a combinator or a cluster of combinators that turns I1s into O1s, and one which turns I2s into O2s, then we can fuse those 2 together to create this I to O cluster. So this is kind of the notation I'm going to use. So applying that notation to the first example we saw, here we're specifically looking at the first of these fusion assignments, so a horizontal fusion between A's and B's. This translates into fusing A's, which was a cluster from X's to the array A's, and the cluster from X's to the array B's together to create a single cluster which reads from X's once, and then produces both the arrays A's and B's. So that's kind of, this judgment is representing the oval. Then these are sort of the boring part of the inference rules. So this is all the inference rules where no actual fusion happens. We've got a base case. You can fuse 2 empty clusters to create a new empty cluster. And these 4 intro cases are all if one of your 2 clusters is going to produce or consume an array that the other cluster does not care about at all, then this input or output just gets propagated to the final result. You'll notice that some of these have an additional constraint at the top where something should not be an element of a certain set. You can assume that all of these arrays are not a part of any of the sets, but many of these implications are kind of transitively implied if you only assume these few. So these are the more interesting cases where we actually have the vertical, horizontal, and diagonal rules. So let's just look at the first case. Given that we can fuse the rest of the arguments of these two clusters, then we'll have the first cluster have an extra output, x. The second cluster has an extra input, namely the same x. And then we can fuse these two together where the final result will not mention x at all anymore because it is completely fused away. You'll notice that there's an asymmetry here between the left and the right clusters that we fuse. The intuition behind this asymmetry is kind of if you're fusing imperative loops, you'll have to put the body of one loop above the body of the other loop in the resulting thing. Again, diagonal completely mirrors the vertical case, except we're actually still keeping this intermediate result around. So we've got an extra output. And in the horizontal case, we'll have two clusters that both read from the same input, which means that the final fused result will only read from this input once. So far, this is, I would say, not too difficult yet, but it also does not support the kind of gather programs that we've seen in the beginning. So to look at how we can fuse gather, I'll first have a small example here. So here we've got a single program which has first a map and then a gather. It's possible to fuse this into a single loop, but some weird things happen if we directly do the translation. We see that the body of the map itself does not change at all. We still produce an A by applying F to some X. But the gather kind of pushed its index transformation through the map. So at the bottom here, I'm not sure if you can see my cursor, the actual code generated in the place of this gather does nothing. We just take an A and name it as a B. And this index transformation is pushed all the way to the top of the function where we're accessing a different X for our map to work on. So in other words, we're kind of doing this map in a different order, and we're going to write that down in our judgment by kind of annotating each array in both inputs and outputs with some order. In the paper, I chose, I think, 0 for left to right order, 1 for right to left order, and any other number corresponds to this unique label that we gave to each gather. So in this case, our fuse cluster is going to consume this input i's at order 0, and it's producing its b's also at order 0, but it's consuming its input x's at the order kind of directed by this gather. Here's a slightly different example. The only thing that changed between this example and the last one is that we're actually returning both of the arrays, so also the intermediate result. And if we do just blindly apply the same translation as we did last time, that means that in our generated code, we'll also need to write the output to the array A's. Sadly, doing this, I mean, of course, you have to choose, okay, which index in the array A's am I going to write to? Given that we've read our X from index I, it might make sense to write our A to index I as well. This kind of works. The problem is that we have no guarantee that this array I's actually contained all of the indexes to array X's. So after evaluating this loop, it's possible that we haven't actually written to all of A's. So for that reason, I'm saying that this is not a valid fusion. And the way we can see it's not a valid fusion is that one of the outputs of this cluster is not in order 0 or 1. So in this case, the output A's is in order L. And we're going to impose a restriction that each kind of top-level cluster, so a cluster which we're not going to fuse with anything else anymore, needs all of its outputs to have either order 0 or 1, because that ensures that we're actually going to evaluate the entire array. So here are kind of the updated inference rules. This time we're actually annotating each array in these rules with its direction. Nothing fundamentally changed here, but there's a little subtlety about the fact that these arrays are annotated with their direction. Namely, for example, for horizontal fusion, you can only fuse two operations horizontally if they're both reading from the same array in the same order. It's still possible to fuse two operations that both read from the same array in a different order, but then they won't get horizontally fused. So the resulting loop is going to read from this input array twice. Which is exactly this example. So in this example, which is the one we've seen all the way at the beginning, we've got our two maps and then a gather. It is possible to fuse this into a single loop, but then this resulting loop is actually going to read from our array access twice. Once at order 0, in order to determine what the corresponding A is, which will be used as the index for a gather. And then this gather will use that index to figure out at which place we're going to read the second X for this B's function. All of this works out, but it means that we're going to have to read from the array access twice. So that was kind of the rules for when programs can or can't be fused. But that doesn't really get us anywhere yet. So in order to actually find an optimal fusion assignment, we formalize this into an interlinear program. So the idea with an interlinear program is you've got integer variables, linear constraints between those variables, and some cost function which defines a metric on them. So these variables are going to model our search space. Constraints restrict the search space to only the valid solutions. And then the cost function is going to define the quality of each of these solutions. And we use any existing IOP solver then to find the optimal fusion assignment. There already exists one of these IOPs. It just does not support combinators like gather. So these are the variables it uses. For each two combinators that have an edge between them in the graphs I showed so far, we're going to have this variable x. Whenever this variable is 0, they're fused, and when it's 1, they're not fused. We're also going to define this pi variable for each combinator, which gives a numeric label to each of the clusters that combinators can end up in at the end. So this pi variable is going to be needed to ensure that we don't have any cyclic dependencies. And finally, we have a variable m, which describes whether or not an array is completely fused away. So these are the constraints imposed on these variables. So from top to bottom. For this first one, we've just got some reasonable bounds for pi. If we have n combinators in our language, then no pi will ever need to be bigger than that. Then this second constraint defines an ordering between all these pi variables. So anytime there's a dependency edge from A to B, whether it's fusible or infusible, that means that we're going to need to compute these two combinators A and B either in the same cluster, or we need to make sure that the cluster for A is earlier than the cluster for B. Then our fusion variables are binary. Our fusion variables for infusible edges are restricted to 1. This one means that whenever an edge is fused, so x is set to 0, this restricts the difference between the two pi variables to the size of 0. So it sets them to the same number. This second to last restriction encodes the fact that an array, whenever an array is not manifest, all of its outgoing edges need to be fused. In other words, whenever we're going to need the result of this array outside of the current cluster, the array has to be manifest. And finally, these m variables are also binary. So given that existing work, this is kind of what we built on top of it. We decided that the only real new variables we needed were these d variables to keep track of the order that each array is produced or consumed. So superscript, we have an I or an O for either the input or output, and subscript are the labels of the combinator. So this first restriction, give me 1 second, says that whenever, so G here is again a constant, which is the number of gathers we have, so it's kind of the maximum label that each gather can have. Whenever an array is manifest, that means that the output order of the combinator that produced this array has to be either 0 or 1. That's encoded by this restriction. So this is the restriction. This prevents the problem we've seen before, where we're going to write to only parts of an array. And the second restriction encodes that this is very similar to the one we've seen here, this one. So where this one said that the pi variables of two combinators need to be the same if they're fused, this restriction says that whenever two combinators are fused, that the output of the first one needs to match the input of the second one. And again, it's bounded by these G times binary variable. Then finally, we've got like the combinator specific things. So any scan from left to right, we're restricting its input and output to 0. Any scan from right to left, we're restricting it to 1. For most of the other combinators, we're just restricting something like the input and needs to match the output order. And for any gather, we're saying that the input order of the gather is always equal to its label. The output order of the gather can be anything. So all of the things we've seen so far kind of describe the search space, which is the main contribution of this paper. Of course, in order to actually use an ILP, you need a cost function. We didn't write any great ones, in my opinion, partly because we don't have any static array sizes in Accelerate, which is the language we implemented this in. But we wrote some kind of dummy cost functions to be able to run this and to get some benchmarks. So we can minimize the number of clusters, we can minimize the number of edges that are not fused, arrays that are manifest, etc. These are the results. There was also a graph, which I didn't put in the slides, to compare the unfused arrays, the unfused programs with greedily fused programs with the best ILP result. That graph was slightly disappointing because, probably because of these admittedly mediocre cost functions, our actual best ILP result might not be the optimal clustering. Anyway, these are kind of the comparisons between the different cost functions that we ran. So one thing we noticed is that optimizing for purely the number of clusters, it tended to be the worst, whereas most of these other goals tended to perform much better and mainly similarly. I have not been able to find exactly what in flash attention made one cost function be worse than the rest of them. So for context, these are programs which we also took from a benchmark suite where the size of these programs, once kind of elaborated to the intermediate language that this optimization works on, was in the order of 50 to 150 combinators. We use a couple different IOP solvers for this. Disappointingly, the commercial closed source IOP solver was able to solve all of these in like less than 100th of a second, and all the open source ones timed out depending on which cost function you used. So one thing we're still looking at is, it seemed like specifically the number of reads, so also reads and writes, cost function caused most of these timeouts. So it could be that in the IOP that we're generating for those specific cost functions, there's some pattern which the open source IOP solvers are not able to figure out. Okay, so to kind of sum up what we've done. What time is it? To kind of sum up what we've done, we've formalized this search space for what all the possible fusions are. We've extended one of these existing IOP solutions to support, in my opinion, most of the actual combinators that the languages in this space use. The main limitations we have is the cost functions that I've already mentioned. Also, I guess it's more of a design decision, but in order to generate this whole IOP, we're only looking at the actual combinator itself. And as far as the function arguments to the map, for example, the only thing we checked for there is whether it contained array indexes. But we did not do anything special like analyze more patterns within them. So the idea here is really to take the static guarantees that are imposed by these combinators. So we're kind of relying on the programmer using the right combinators and not writing everything in terms of generates and explicit indexing. Another kind of limitation is that this is only a program analysis. Afterwards, you still need to do a transformation to actually generate this fused code. We do have a somewhat working implementation of this, which is where I got my benchmarks from, but it is not production ready. It was barely enough to get these benchmarks. So that's still a work in progress. So again, we're currently working on code generation for these fused clusters. We're considering trying to figure out a way to either calculate good cost functions or maybe learn them through some data techniques. Finally, there's also a bunch of other optimizations, such as in-place updates or work duplication, which seem to really depend on fusion. So depending on which fusion assignment you choose, there are opportunities for in-place updates which may or may not be available. So ideally, we would also take all of these other optimizations into account when deciding on our fusion assignment. Since I think we still have some time, I'm quickly going to say a few words about the combinators that we did choose. So one of the things some of you might be thinking about this gather function is maybe your language does not support gather, but it does have something like a back permute, or similarly for the scatter, you might have like permute and accelerate. The reason that I ended up writing this paper with gather and scatter instead of those other versions is that it kind of turns out that every program you write in those other versions can be rewritten into these versions without using any fusibility, whereas the other way around, you can't. So if you some of the programs you can write with this gather interface can only be translated into the backcommute interface by introducing explicit indexing. So that's kind of, there's a small proof in the paper where I do the translations. So that's kind of the argument for why these are better combinators. Thank you.
So how do you think this work relates to systems like Halide, where Halide has like a programming language in which you write your calculation, and then a kind of separate language for like scheduling, which is meant to control things like tiling and fusion and stuff like that, where I think a lot of the experience in the Halide world is instead of like, we will just throw like some optimizer at it, what you actually are trying to do is mostly enable like performance engineers to kind of iterate on, like look at benchmarks, understand the behavior of the code, and then kind of tweak the schedule kind of manually. I'm kind of curious, like, have you thought about like various kinds of like hybrids where you kind of expose this kind of space of possible fusions as something that like you can both generate via optimizer, but also humans can directly try and modify?
Yeah, I think both approaches kind of stem from the same basic idea where kind of the motivation behind this work is also that within a certain design space, which is the one that's often used by these array programs, you've got relatively a lot of programs that are somewhat small, but are still intended to need to have a very high performance because maybe they're ran on like huge data. And I think both my work and Halide kind of focus on those programs where you can afford to throw either a lot of human effort or a lot of machine compute effort into finding really the optimal solution because you're going to run the program so long that it makes sense, and because the program is small enough that this effort is valuable. But yeah, the difference is that in this approach, I'm trying to take more of a automated line. We did add force to the list of combinators to give the programmer a little bit of control over, no, I know that this thing shouldn't be fused, but that's the only thing here. So for the rest, I think my ideal is to have everything be automated. In practice, it might not always be good enough to only do this by the machine. Thanks.
Cheers. Thank you for the talk. So I guess I'm interested in some of the technical details of the fusion, which I'm not sure how, maybe they're not super relevant, but either way. So my first thing I was wondering about was like, did you like think about where like your methods like improves over, I understand, accelerates like heuristics for fusion? Like what sorts of specific scenarios, like where are you able to find better fusion sort of situations?
I mean, the current fusion engine that Accelerate uses is really just based on purely local rewrites. And one of the main downsides of many of these approaches is that, let's see, it can't do horizontal fusion at all, for example. It's only looking at this kind of vertical pattern. So that's, I think, a very concrete example where anytime you have this horizontal fusion, then already my approach will probably be better.
I see, thank you.
And yeah, other than that, I think the thing I noticed, so at the start of this work, it was really motivated by, oh, can't we add horizontal fusion somehow? And then after adding that, working on it for a bit, found out that, okay, now that we've added all these different kinds of fusion, suddenly the problem is NP hard. And then I stumbled on this existing ILP work and decided to expand it to also work on the other combinators we have.
Cool. it's a, yeah, maybe I'll ask another one later.
So one of the challenges with Fusion is the tension between duplicating work, which can be very expensive, but sometimes it allows much better fusion. So is that something that you have interacted with in here?
Yes, so this current ILP basically doesn't do any work duplication. But at the end, I quickly mentioned that one of the things we plan to like elaborate this with is also look at work duplication, kind of incorporate it into the ILP to make explicit choices about it. Because indeed, in any kind of like local rewrite-based fusion system, it's often somewhat implicit about when work suddenly will or will not get duplicated. And I kind of wanted to make a more informed decision about it. Does that answer your question? Okay.
Yeah, my question was actually on a similar tangent. So you said yourself the cost model is still very much the focus of attention just now. And I think it's great that you have a formalism to talk about this fusion. And actually, I think this might give you leverage to do something like the halide thing, ultimately, because you could express a complex fusion that you really want. But a simple experiment that you could run, and I was just wondering whether you did actually run this, is you showed us these performance figures, and I assume that this was for a multi-core, or where?
This is parallel CPU code. Parallel CPU code.
Yes, but it would be interesting to repeat the experiment with the GPU and see whether you have a similar answer or not. Did you try any of that?
No, because the backend that this runs on only has a CPU backend so far.
Ah, okay.
So it's just engineering work we haven't done yet.
Because I would imagine you might see very different behavior there, just because the ratio between memory bandwidth and compute capability is very different there.
Yeah, definitely. I think optimal cost functions between CPU and GPU will have a large difference between between different GPUs or between CPUs. It will probably be more a small difference with like weighing whether you have a little bit more memory or something.
Yeah, thanks.
Right, so I had another question. Also, I wanted to add to the discussion that sort of is forming. I think automatic fusion is like extremely important because like in applications like XLA, which you have like in all of Python deep learning, there's no notion of like either indicating something should be fused or like having a scheduling language or anything of useful of that sort. So this is like really cool, I think, to like at least talk about the search space that you have. And I was actually wondering, so you showed this judgment, and the judgment is, I understand it's on two like different operators you might want to fuse, but is it's not immediately obvious to me, but maybe it actually is. Is the judgment like, do you have to like backtrack through it to figure out whether like a pair of operators satisfies it, or like I don't quite yeah, what is the by which how do you judge which things should be marked in the ILP as like fusible?
That's a good question. So these. So like this judgment kind of just says it's possible to fuse these two clusters and make the third one. But these rules themselves are in no way like syntax directed or even unique, I guess. No,
I don't think.
Let me rephrase it. I think given, in our implementation as well, this is true. Kind of. The fusion here is a binary operation, right? And the way it ended up being, given that you're putting all your operations in like topological order, it doesn't actually matter in which order you keep combining these operations, as long as you just keep appending them to each other with this binary operation, you always end up with a like functionally equivalent cluster. And combining two operations with each other, because they're sets, right? These sets of input and output arrays are unordered. You can apply these rules in any order, but also it doesn't really matter in which order you apply them. You always end up with a, what I'd say, functionally equivalent cluster.
Yeah, that makes sense. And so I actually, on that note, what do you think are the, I don't know if you discussed this in the paper, but what do you think are the limitations of like considering fusion to be like binary? Do you think like this limits the ways in which the ILP can reason about its cost function or anything like that? Yeah.
No, I mean, I guess this whole judgment being binary is something which is kind of isolated to this inference rules part. As soon as we move to the ILP, we no longer have a binary thing there.
Well, there's the edge, right, which says like...
Yeah, sure. I mean, in your graph, of course, you've got edges, and the edges have...
Okay, yeah, sure, sorry, yeah,
Yeah.
right, yeah. Okay. Cool, thank you, yeah.
Okay, if you have no more questions, then let's thank David again. And we are back.
just wait for the noise to die down outside. Yeah. Of course, with the tiny big cups of coffee, there should be larger cups, and people will have more energy.
No, but you know, when they are small, they make up on strength.
Not insufficient. All right. Okay.
You think that's it?
Yeah. I think people, yeah, let's just begin. All right, welcome to the last session of FProPer. It is my pleasure to introduce Shide of Edinburgh University, who will be talking to us about functional sparse tensor compilation.
Hi. Would it be possible if you close the door? Okay, sorry. Thank you. Okay. So, I'm going to talk about functional sparse tensor compilation. And tensors are important in general. We have seen them in lots of applications such as neural networks, signal processing, and social network analysis. And let's see what dense tensor computation by itself looks like. This is an example of the code that computes the dense matrix multiplication, which looks really simple, and it's open to lots of optimizations such as flatten array as a data structure optimization for dense data, and also loop tiling and parallelization. But what about sparse data? For example, this is a document representation used in natural language processing applications that has lots of zeros as values in the matrix, which makes it sparse. And this is an Amazon product we use, which also is really sparse tensors. Wouldn't it be efficient that we use dense tensor algebra, the dense tensor computations, because they're really optimized for tensor computations? But the problem would be that in this way we will allocate all zero elements inside that tensors. And also we perform the computations on all those zeros elements. So we need for sparse specific data formats and algorithms. What would sparse specific data format would look like? This is a sparse tensors represented in dense representation. And this is a COO representation for sparse data, which is the basic representation is used for sparse representations, which have three arrays, one associated with rows, the other for columns, and the other one for values. And it basically stores the non-zeros, rows, columns, and values accordingly. But what's the problem with CO representation itself is that we allocate multiple rows in the row array, which could be eliminated, but by compressed sparse row representation, which basically compress the row array and use it as a pointer to the associated index and values for that specific value. Should I continue? It's okay? So, should I? Oh, okay. Okay, good. And what about sparse-specific algorithms? Let's say we have the same example of matrix multiplication, and we have dense B and C. This would be the same computation that I showed you before. But what happens when B gets sparse? The code gets more complicated. And what about when C gets sparse? Even more complicated. There are lots of ifs and while loop inside there. So it's not easy to make it optimized. There are some sparse frameworks like SciPy and JAX that basically use the fixed function algorithm, which means that they use the algorithm designed for each computation separately based on the underlying data formats. But the problem is the generality is challenged with using using that method, because we have lots of tensor expression and lots of storage formats, and it's not possible to write down the optimized algorithm for each of them. So there are sparse tensor algebra compilers trying to generate the optimized code for kernels without regarding the exact computation and the underlying data formats. This is a row major tree representation first introduced by Taco guys to represent sparse data as a tree representation. Having the same example, this would be the this would be the row major tree representation of the same matrix, which basically first points to the rows and then points to the columns and then the associated values for each row and column. And that's the same M2 tree represented in the tree representation. And why we are using that? Because it's really easy to convert that tree representation to the CSR representation, the basic representation used for sparse data. And the benefit of that is by this representation, we could represent every tensors with any order because we just say the tensor is sparse or dense in each dimension. And this is an example of matrix vector multiplication when both B and C are sparse. And in this example, B is sorted in row major, meaning that we first store the rows and then columns. And as we see, we first can iterate over the i's and then iterate over j, which is the first and second dimension of B. But what happens when B is stored in column major format? We don't have access to I directly. So we need to introduce a loop reordering as an optimization to just change the order of loops. And this is the example that Taco introduced previously. So we first iterate over j's and then iterate over I, which is different from the previous loop order we had. All I talked about was about sparse input and what happened when the output gets sparse. Having this example, which is basically a column summation of a sparse matrix, we basically need to iterate over each rows and add the associated column and the value to a sparse vector representation. But when we are going to the next row, what happened is we need to insert the column 0 with its value 2, which means we need to insert before the previous inserted values into the array, which is not easy to do. And another thing is when we are when we are reading row 4, we need to insert column 2 with its value 4, which already been there. So we need to keep track of the columns in the output and update them. But how efficiently we can do that? An intermediate workspace was first also introduced by Tacos, which means that the idea is to use an intermediate dense result instead of computing the exact sparse output and then convert it to the sparse output that we wanted to. And this is the general Taco architecture that I explained till now. And by pure compute schedule is basically inserting that intermediate workspaces, and reordering is the loop reordering. But still, Taco is very limited compared to what we want from a sparse tensor compiler to be. When the output is dense, everything is okay for all these kernels that have an application. But when the output gets sparse, we can see that Taco generates wrong answers. But why is that? Having this previous example, this is what the sparse output we expected to be generated. But this is what we get from Taco. Because they cannot insert that intermediate workspaces automatically, the user needs to identify where the workspaces need to be inserted, and they cannot detect where to update. So they basically just insert whatever they see as columns and values. And when the output gets more sparse, the code they generate cannot be even compiled. So what's the problem with the architecture that Taco has is that it has monolithic design, which means that they do everything in one step of transformation. They do all the recomputation that's needed in scheduling, and they just use the data format at the end. What we want to do is to introduce a compiler that is able to actually compute every single of these kernels with sparse output. So this is the architecture of the compiler that we introduced, and I'm going to explain how it works. And the key point of that is separation of concerns, which means that we tackle each problem at each level of lowering instead of having all of them in the same transformation. And this is how Taco is compared to our architecture. And for example, I'm going to use MTTKRP, which is a well-known kernel in tensor algebra computations, and going to explain how the compiler works for this example. First, we're going to see what's the inputs of the compiler. This is tensor algebra expression, and the index order identifies which order we want to iterate over the inputs and computes the output. And data format specifies if the data input and output are sparse or dense in each dimension. In the tensor lowering, we're going to lower the tensor algebra expression into H-scene intermediate representation, which basically identifies what's the loop order and how we can get those indices from the inputs. For example, we can see that I has been appeared as the first index of B. So we translate it to for each I in IB, which denotes the index of B. And what happens when we have two occurrence of same index in two inputs is that we do the intersect of those index spaces. And we do the same, and this is how we compute the output in general. And then we use STQL as the next intermediate representation, which was firstly introduced, which is a functional programming language to query against dictionaries, semi-ring dictionaries. And these are the key construct of it, which dict K is how we can define, how we can access key K of dictionary dict. And the next is how we can construct a dictionary from which has key Ks to values B. And the sum construct basically fold over key and value pairs in dictionary and compute the F over each values and sum them up. And this is an example of vector Hadamard product using the same, using STQL representation, which we iterate over V1 and then construct a dictionary from I to the value which is V1I, and we get the associated value for I in V2. But why we want to use STQL, a functional language, as intermediate representation is, getting back to the example we had, the true representation for sparse output, it's really similar to what a dictionary would look like. And this is a dense sparse representation for the outputs to be consistent with the CSR. The first column is a dense array, basically pointing to the dictionary for each row's values. And the reason we want to use dictionaries is they have a one lookup and update, which would make it easy when the output is sparse, as we've seen the problem previously. And now I'm going to say how we do the HSyn lowering, which is basically going from the HSyn language to STQL. The key point is how we translate for each I in IB, and also we construct the dictionary associated with that key whenever we are iterating over that key. Like here, we are getting key I inside B, and the output has key I. So we construct a dictionary from key I to what is computed in the future. And whenever we have an intersect of two index spaces, we choose the one which is sparse. For this example, both B and C are sparse, so there's no difference between iterating over each of them. So we iterate over B and do the code motion for CK, so in the future we wouldn't look up for the same value multiple times. And now I'm going to say what LLQL as an intermediate representation is. LLQL is basically closer to low-level language. It's similar to STQL, but it extended its type system. STQL only had one dictionary type, which was unsorted dictionaries, but LLQL can express sorted dictionaries, unsorted dictionaries, which was the hash, and list map for intermediate workspaces. And it also has constructs for optimization. The reason we wanted to extend the type system of STQL was that the sparse tensor data are sorted. So we iterate over them in order, which wasn't as fast in unsorted maps because it wasn't used cache locality, which sorted map has. And also, we extended the construct to express data-specific optimization for sorted dictionaries. And the keynote to just mention from when we're going from STQL to LLQL is that we identify what's the type of the output. And this notation means that the output is sorted dictionaries of sorted dictionaries, basically nested sorted dictionaries. And we also apply code motion for the output because we define the variable for that, so we don't access the same variable multiple times. The problem now is that when we converted from unordered map to ordered map, iterating over them became faster, but lookup complexity time is O of log n, which was O1 previously. To solving that problem, we use hinted dictionaries, which is a functional ordered construct to optimize the operations over sorted dictionaries. And what they do is basically having a hint which points to the beginning or like anywhere in a list and hints the lookup or update to start from that point. And if they weren't there, it starts to look of O log n. And this is how we look for the place and insert the hint variable, which needed to be exactly before the loop we starting to update that variable. So it would consist with the order that we are iterating over that. And this is how the lookup became hinted, by passing the hint object to the lookup function. And this is how hinted updates works. We are passing also hints for updates to start from the place that we know the update would be happens in. The other optimization is workspace reasoning, as I mentioned before, like the workspace that Taco used. Here we are updating AI with key J multiple times with the same key because we are updating it inside two other loop. So same key J may occurs multiple times. So we define a list map variable to compute the AI and then convert it to the representation we had, which was sorted map, and then clear the intermediate workspace. And the code generation is basically simple as translating everything we had in LLQL to the C++ code that computes the same thing. For evaluation, we are going to see the evaluation result for sparse general matrix multiplication and tensor times matrix. This is how unsorted dictionaries compared to Taco performs. which is way slower because of that, because of iterating over an unsorted map, which was really slow. And then we converted to sorted dictionaries, which is even slower than unsorted dictionaries because of the lookup and updates time. So after we applied hinted dictionaries, this is how faster we can get, which is kind of as fast as Taco. But when we are applying hinted dictionaries and workspaces, it gets faster than Taco's 1.5, which really depends on the amount of update with the same keys. It could be cases where inserting workspaces would increase the time because there's not that much updates with the same key for each value. And for TTM kernel, we evaluate over real-world datasets, which are NIPS2 and NEL2. And these are the results compared to Taco, which we are faster. And the star is the one that, and there is no need to use intermediate workspaces here. There's only there's only optimization for hinted dictionaries because Taco, as I mentioned before, wasn't able to compute other kernels automatically. And to conclude what I've said, star is a robust modular compiler for sparse tensor algebra, which use multiple functional intermediate languages to go from the tensor algebra expression to the C++ code that computes that expression. STQL was previously also used for forward mode automatic differentiation to automatically compute differentiation for sparse tensor algebra expressions, but it was limited to forward mode. So the future work could be implementing backward automatic differentiation on top of the star that I just introduced. That was it.
I will actually use my prerogative as chair to ask the first question. So what about parallelization? This was sequential code, right? And these hints seem like stateful objects. Have you put any thought into how that, what you might do in a parallel setting?
Parallelization for the whole computation.
Yes. Yeah.
For the compilation or for the computation?
For the computation.
For the computation. For the computation, one parallelization would be we know like using dictionaries. Each keys that that's stored in dictionaries is basically the data that we have. So by passing each of those like indices to one thread, we could parallelize the computation, but I haven't done any job on that. That's just the thought I have.
All right.
Was it okay? Okay.
Any questions from the audience?
Yeah, it seems that a lot of the performance gains here come from using the hinted dictionary, right? Mm-hmm. Like, what is the complexity compared to a regular dictionary? Is the amortized complexity smaller, or is it just like a constant gain from using the hints?
It's constant time because like the only difference between hinted dictionaries and the normal dictionaries, you mean hash maps, right?
Yeah, the sorted maps.
Oh, okay, the one that we started with.
Yeah.
Iterating over those is really time consuming compared to the sorted one. So like that's the only difference.
Okay.
There is. So, yep.
Thanks very much. When you showed us the Taco times, I was not quite sure what kind of array representation were you dealing with there? Is that a dense format or?
The same representation, the CSR representation for matrices. And for the other one, it was sparse in every dimension. So let me
So the memory consumption of these algorithms, at least in the long scale, is this roughly the same?
Yes, because we are, okay, to just, let me, just, can I just, I can find it. Yep, here. Like, what Taco is just basically these ones, which has one array for positions of each indices, and one for the columns, and one for the values. And the one that we used is
I guess the question that I'm
is
really
this one.
itching to ask
Okay.
is the space complexity of both algorithms roughly the same or not?
Yes, exactly. It is.
Okay, thank you.
I have another question then. So it's pretty clear to me that forward mode will just sort of work out here. But reverse mode, that reverses the dependencies, so things that where reads become writes and so on. And how does that fit with these hinted dictionaries? Because you have some state there. Have you looked at what that might entail? I know you haven't done it yet, but how might that work out?
By like reverse mode AD, we are
Yes.
computing from, we define the hints in the computation pipeline. So whenever we are computing the reverse mode AD, we are basically computing some tensor algebra expressions, if you put it that way. So you basically, for that tensor algebra expression, you define the hint where it needed
All right,
to be.
so you actually differentiate at a very high level originally.
Yes, exactly, before coming to the down level computation.
So one thing this allows you to do also is experiment with when things are sparse and dense, because it is actually a bit unclear when it's worth, how sparse it should be before it's worth using a sparse representation. And right now I think that's usually done manually. You just try out things and see what sticks. Have you given any thought into automating the exploration of this space about which vectors should be sparse, which matrices should be sparse, and which should
That's
be...
also another thing that could be done on top of that, basically learning how we should see each computation. Let's say we have like that's where I started from to this project, because I had lots of tensor algebra computation which had lots of intermediate tensors, and it's really important how you order them and how you see each of them. So it can be learned on top of that, I guess.
Yeah, kind of following his question, I was wondering how does it compare to Taco? Depending on the density of your input matrix, does it scale the same way?
If we use the dense?
No, if depending on the sparsity of your matrix, right? Because obviously here you're using a dictionary which is a bit slower. So I imagine that for denser matrix, it would get slower than Taco. It would start to grow a bit more.
Yep, it start to grow more if you use the basic hash dictionaries, but still sorted dictionaries are faster. I didn't mention that in here because it was a part of a journal paper that also was submitted to somewhere, so that's the reason I didn't mention that.
Any more questions? Otherwise, let's move on to let's congratulate the speaker. I thank the speaker again, and then move on to the next question. And our next speaker is Enrico from the Higher Order Company, who is here to tell us about what I think can easily be called a radical new suggestion for how we should compute functional programs. Well, yeah.
hopefully you guys can see that okay. Let me make sure I can move around. Yes. So yes, my name is Enrico Borba. I'm here with the Higher Order Company. We're going to be talking about interaction combinators, our runtime for evaluating them. And this is a joint work between a lot of people. Me and Nicholas, we're here at the conference today to talk about this. So the main ideas that we want to bring this around. The main things we want to talk about today are an efficient interaction combinator runtime. The reason that matters is we can encode the computational models that we're typically familiar with, like lambda calculus, inside of interaction combinators. Additionally, our design for this runtime is mostly hardware agnostic, and so we're actually able to port these ideas to both the CPU and the GPU. And because it's so abstract, there's an opportunity for compiling higher level languages from a variety of domains into these interaction combinators. So since it's such a non-traditional model of computation, I'm going to be giving a brief introduction on interaction combinators. The general idea here is a graph rewrite system, and if you can imagine, we'd have a graph that's sort of the initial state of the program. According to some rewrite rules, we're going to change the graph over time, eventually ending up with a graph where no more rewrite rules can be applied. And hopefully by the end of this talk, it'll become clear that the graph here on the left represents a lambda calculus term that's applying the identity function to itself, which you would expect in sort of a sane evaluation environment. You should get back the identity function again. Yes. So the specific system that I'm going to be introducing today and then extending on later in the talk was developed by Matza and Lafont, sort of work building up on top of each other. So the general building block for these graphs starts with some nodes, like the typical graphs that you're probably familiar with. However, these nodes have sort of special edges that come out of them, known as their principal ports, and the binary nodes additionally have two auxiliary ports that come out of them. While we're talking about these, typically the way we choose to refer to them and how they've also been seen in the literature is the white node is the constructor, the black node is the duplicator, and then we have an eraser node as well. And you'll notice the eraser only has a principal port and no auxiliary ports coming out of it. So that's the first step of the graph, and you can imagine those nodes are all wired up together. The sort of second part of the system is the rewrite rules that govern how the graph should change over time. And depending on how you count, there's 4 or 2 rules. They're sort of generalizations of 2 basic rules. So we have here on the top, these rules are known as commutation. If you have 2 nodes that are different types interacting with each other, they will commute. And what that sort of looks like, if you can imagine, one node will go through the other along its auxiliary ports. So here we have the constructor node interacting with a duplicator node, and you'll see that the duplicator node moves down the 2 auxiliary ports of the constructor node. Similarly, the constructor node will move up on these 2 ports up here. And whatever these 2 ports are sort of connected to in the rest of the graph, it's meant to still be connected to after the rewrite rule is applied. Like I mentioned when I was first introducing this rule, this happens when 2 different types of nodes interact. So you can extend this to erasers, which are these nulary nodes, and binary nodes. And sort of, since the eraser has no auxiliary ports, there's nowhere for the binary node to go, but the eraser will move up into the auxiliary ports of the binary node. So that's commutation. The second rewrite rule is annihilation, when 2 nodes of the same type interact. So you can imagine this rule also being instantiated for the duplicator nodes. And what happens is the auxiliary ports cross over. In a degenerate case where 2 eraser nodes interacting, that sort of part of the graph disappears. You'll see that that's meant to represent computation of sort of variables that are thrown out. If you imagine a lambda term that takes in 2 parameters but only uses 1, and the other one sort of gets thrown away, that's typically how erased computation ends up being represented in these graphs. Additionally, you'll notice that this rewrite system is symmetric. It's sort of up to the labeling of the nodes of one of them as being black, one of them as being white. They're identical in behavior and how they change the graph as it's rewritten over time. Does that make sense? Any questions so far? Cool. Now, I've given us sort of some nodes. I've given us the rewrite rules. How do we do the typical lambda calculus computation over these strange objects? So what we want to do is we want to take existing lambda calculus terms and transform them into these graphs. And in the lambda calculus, there's the two typical operations that we're familiar with, where we abstract a variable inside of a body, and we can also apply a lambda calculus function to a variable. Perhaps less known operation, at least it doesn't really matter when you're writing these lambda calculus terms, is duplication. This occurs when you have to use a variable more than once. If you think about sort of a variable existing in this graph representation as a wire, you can't use it more than once. That wire only has to connect to one place. And so duplication is the way in which you can reuse terms. So let's go through these one by one, because it's kind of a strange way to compute. Abstraction, the way to think about this is this left wire here is going to be the variable that you're going to use in the body of the lambda function. The body of the lambda function is the y, and the term is what comes out of the principal port at the top. So if you want to make use of this lambda term, that's an abstraction, you would connect this principal port elsewhere in the graph where you want to use it. A very simple case is the identity function. So when you take in the parameter you're abstracting and just use it in the body and nothing else, that would just be connecting the input parameter to the body. And then you would use that identity function by connecting the principal port elsewhere. Now, for abstraction, the sort of output of this syntactic construct comes out of the principal port. For application, it's slightly different. When you apply a lambda calculus term, you need a function and a parameter. And so those will come in at the top and at the left auxiliary port respectively. And the result of that application actually comes out of one of the auxiliary ports. The reason for this sort of encoding you'll see in a moment is, like I mentioned at the beginning, or early in the talk, the way we have these nodes interact with each other or be rewritten is only when they're connected through their principal ports. And abstraction and application are only, basically when you need to do a beta reduction in lambda calculus, it's when an abstraction meets an application. And because the applications take in the function through the principal port and the abstractions output their functions through the principal port, when you go to abstract or apply an abstraction, the rewrite will occur through the principal ports. And I'll go through a more detailed example of these constructions in a moment. Duplication, like I mentioned earlier, if you ever need to use a variable more than once, you can duplicate it. The principal port is where the variable comes in, and these two auxiliary ports are now how you can use that variable more than once. Please go ahead.
So how do I know if I see a triangle with these three
Yes.
keys, whether it's an abstraction or an application?
That's a fantastic question. In general, if you construct a random network, you can't necessarily read it back as a lambda calculus term. However, when you're constructing it, the rules are pretty sort of explicit. Intermediate networks, as the graph is being rewritten, can't necessarily be read back or interpreted as a lambda calculus term. Does that make sense?
In the standard literature, abstraction and application are different nodes.
Sorry?
In the interaction nets literature, abstraction and application are different nodes.
It depends on what you mean by different nodes. Some literature has them as the same nodes. However, they have a property known as polarity, where this wire is positive and these two are negative because they're sort of consuming values and this is outputting one. And this one here has a positive wire and two negative wires. If you want to walk a network and infer the polarity, you can sort of see them as different nodes. However, this is a fine way to encode lambda calculus terms.
Interaction combinators, we represent both of them with the same node. And if you can imagine, you could polarize, this is
But not intermediate readback. You can't read back like an intermediate network necessarily. Yes.
Could you give an example where,
Yeah, the next slide will give an example, yes. And the last construct, just before I go to the next slide, is just erasure. Like I mentioned earlier, if you don't use a variable, you can't have these open ports sort of not connected to things, and so this is a way you throw away a piece of computation. So here's an example reduction going from the left to the right. We're going to start off with the same term that I showed in the beginning of the slides, where we're going to apply a function that takes in a parameter and applies it to itself, to the identity function. So I've colored the active pairs or the reducible expressions in red, and additionally, they're sort of drawn in a way that's meant to make reading this a bit easier. This left-hand side of the first step is this term here. So this is an abstraction with a duplication and then an application of the x to itself. And the result of that is the body of this lambda expression. So again, this is an abstraction with one parameter that is duplicated, applied to itself, and the result of that application is this term. The identity function, like I mentioned earlier, is down here. And this extra construct is to apply the first term to the second. So this is an application of this function to this term. This R here is the port that we're holding on to essentially to keep the computation. We need a free port. You can think of this as like a combinator in lambda calculus, but if there are no free ports, essentially the computation can result in like a void net. And so holding onto this free port gives us a result value to refer to later on.
But since that R seems to be like the output of the application of the first lambda to the second, would it be fair to say that that is the result of the whole?
Yes. Yes. So the first rewrite rule, or the first reducible expression that we reduce is this red active pair here. That's going to be an annihilation because two nodes are the exact same. And these wires cross over. And you're going to be left with this R is going to end up down here. And this node is going to connect to this node through the active pair, which is what I've represented up here. And I've drawn it just to save some space where the identity function came up to the top here. This net, I don't think is interpretable. If you wanted to read this back, to give you an example of a network that intermediately doesn't make much sense as a lambda calculus term. Which I'll show later in the talk, we have the syntax to describe these, but they're not lambda calculus terms. Yeah, so the second rule we apply here is a commutation rule. As you can see, these two nodes are different. And so this node and this node will commute. Hopefully that is somewhat clear here. You can see the duplicator node moved up into the auxiliary ports of the constructor node, and the constructor node moved down into the auxiliary ports of the duplicator node. And then we have one annihilation of the two duplicator nodes. Yes, that's right. This port here goes through and connects to this one. This port here goes through and connects to itself. So this node came down here, and this node became that one. And there's one more active pair to reduce, and again, that's another annihilation. This port here ends up just going through and connecting back to the principal port of this function, or of this constructor node, excuse me. And as we expected, that is the same representation for an identity function, which is what we expect if we were to reduce this expression. That is a so if, okay, there's a few things to this question. If the network you have represents a valid lambda calculus term, you can read it back by inferring the polarity of the nodes. Because you know the polarity of the output, and so you can basically walk, and there's a fixed, there's constraints on the positive, like if you think of these nodes as being directed, or excuse me, if you think of these edges being directed, you can infer the direction of every edge in a network. But that's only, again, assuming you have a term that's a valid representation of some lambda calculus term. If you have a network that represents a valid lambda calculus term, you can infer this polarity. So both in the start and in the end case, we can infer that. In the intermediate cases, we can't. Now, I think perhaps this will answer your question. This does not soundly reduce the entire lambda calculus. All right, so this reduces a subset of the lambda calculus. Specifically, you can't duplicate a function that is non-affine, because that would end up resulting in two duplicator nodes interacting with each other, which would result in a destructive computation, which really isn't what should happen. A function that uses every parameter at most once. Does that make sense? So a linear function would be one that uses their parameters exactly once. Affine uses at less than or equal to once. Correct. It's a function with no duplication nodes, or a lambda term with no duplication nodes. That is not trivial to infer. It's not clear, just given a lambda calculus expression, if you will end up duplicating a non-affine function.
Well, the first, then in that case.
This is not affine?
This is already not affine, but this is worse. Yeah, but this is not.
No, but you're not duplicating a non-affine function.
It's duplicating a non-affine function.
Yes, it's a strange constraint. But essentially, you want to say that you don't have two duplicator nodes interacting with each other.
Basically, the problem is if a duplication duplicates another duplication. Yeah. And then you get an annihilation when actually the behavior that you wanted was the computation.
But that's not the modular property, right? I can't, for the whole program you can say that or not, but it doesn't mean that I can't write functions and type check and check them one by one. And it's only when I have the whole program I will find out that I can't compile it to an expression.
So you can't compile to this presentation of interaction combinators. You can imagine one where for every function you create, you actually create a new type of node. Like every function has its own duplicator node, its own special label. And so whenever two duplicator nodes meet, they'll never be the same label. They'll always be different. At least when applying functions that are different. But yes, correct. In this system, there are like this reduces soundly only a subset of the lambda calculus. Any other questions on this reduction? Yes, please.
Figuring out if a function is affine is not like a resident answer. I think you were saying it's floating.
Affinity is checkable. Yes.
So you have to look at the whole program.
No. You can check if a function is affine.
Yeah. Okay. So like the identity function then is the other one isn't.
Correct. That's a syntactic check. But to ensure that I think that a whole program never duplicates a non-affine function, it requires the entire program.
So you can check only when they're affine, but whether a non-affine one ends up in a position where it will lead to them being duplicated is a real property.
Yeah. Yes. Figured.
Okay. Some quick important theory that we're going to make use of that the HVM depends on. There's two important points here. Interaction nets have a very interesting property such that the actual order in which you apply the reducible expressions is irrelevant. The number of reducible expressions, or the number of reducible expressions that you will end up reducing as you're evaluating a network is always the same, independent of the order of which you decide to take those operations. And that ends up being extremely useful for a parallel evaluator because you can sort of, it doesn't matter, as soon as you see a reducible expression, you can go and evaluate that. And you won't sort of get penalized for happening to pick some specific order. Additionally, the nets that we care about are these networks that have a single free port and have no vicious circles. Vicious circles are essentially a network whose wire eventually, like if you can imagine a tree of nodes, if a wire ends up connecting back to its principal port, that is a vicious circle. It represents a computation that at least we're not interested in. It's not in the surjection when encoding the lambda calculus terms, and it'll never be an intermediate net either. Please.
I'm not sure if you actually want to say the first line. Strong confluence means that the end result, when you can't do any more interactions, that end result is independent of the order of reduction.
So, yeah. The Wikipedia page entry for strong confluence, I think, agrees with what you're saying. In the Lafont 1997 paper, the way he defines strong confluence is the fact that if at any point we have some network here, N0, and you can do one of two reductions. You can go to N1 or N2 as a result of applying either reduction A or reduction B. There is always, for each of N1 and N2, you can always take another step to go exactly to an equivalent third state. So if you ever have the choice between two reducible expressions to reduce, if you can pick one or pick the other, it says that among those two choices, I can always return to a third shared state. Does that make sense what I'm saying? Perhaps I'm not explaining it well.
Yeah, but I'm not sure that those arrows, correspond to,
Yes. What I'm saying is, in the Lafont paper, his definition of strong confluence is that these arrows are single steps.
Is it the case that you get the property because the iteration is optimal regardless of the path you're taking?
The property that the amount of work is independent is due to this definition of strong confluence, which I agree with you disagrees with like the Wikipedia page entry, but the way when Lafont is like presenting this, the way he states strong confluence, which I don't have a, perhaps I should call it stronger.
Definition of strong confluence, yes.
But his
contention is with the amount of work claimed.
The amount of work being dependent is it derives from the property of
strong confluence.
Yes, and the fact that each path is optimal, right? Yes. So that's the missing bit there.
Because if this is the terminal state, but that duplication would have happened regardless.
Yes, but the thing is that you see then the amount of work is different. If you let the erasing node optimize on the erasing first, then there'll be less work.
No, I think the amount of, so independent of the order, the number of interactions that occur is constant, always. At a minimum, we have empirical evidence of this, but it's also like a theoretical result. And one of the effects of choosing which reductions to happen, or I guess one of the penalties of perhaps taking some order of reductions versus another is the amount of intermediate memory. You're correct if you go and do all of the commutation rules first, your intermediate network is going to be much larger than it would otherwise be if you did all the annihilations first. However, the number of interactions is constant. And again, it's due to this property.
Maybe there's a confusion that in here, in this system, we are always executing every single interaction that exists. Right? So, for example, if you want lazy evaluation, then you don't need to do the interactions that are not actually important, like that are disconnected from the value that we want to execute. And then under lazy evaluation, then yes, the order of interactions will matter, right? Because you do work that will be discarded. But in here, we are always doing every single piece of available work, including erasing things that are useless.
That is true. If some part of the net ends up being disconnected from the main network and essentially won't affect the end result, it's still reduced all the way. And that's included in my count of like the total number of interactions. Sorry?
On a CDD system, like all the parts of the program are going to be reduced. So the total amount of reductions is always the same.
Yes. But you might do some reductions that you perhaps wouldn't need to if you were doing an optimal evaluation because of these part of the networks that were disconnected.
So with the translation, you start from that term, and then you do the interaction at reduction, then you read back. But if you want to do lazy evaluation, like how is it easy to
Yeah.
tell when you can read back the result that corresponds exactly to the lazy evaluation?
That's a good question. And that gets into sort of the extensions that HVM2 does and the sort of how it builds upon the symmetric interaction combinators. And so I'm going to go through the implementation details of HVM2. First thing is the fact that we need like a textual representation for these networks, both as a way to sort of reason about them, or at least to have a computer reason about them and to have them be a compilation target. The idea behind the textual representation is that we want to represent parts of the network as trees, and I feel like I'm going to have a hard time explaining this, but there's different kinds of nodes, and these binary nodes have two different ports, And the way we represent that textually is we have different grouping operators or different symbols of grouping to represent the different kinds of nodes. And there's two different terms you can put in these binary nodes, whatever the left auxiliary port is connected to and whatever the right auxiliary port is connected to. We also have a concept of variables, which means we have to label the wires. This is a key difference between the graphical representation. The graphical representation has no labeling of these wires, but we're sort of forced to do that in order to encode this textually. Essentially, variables, as they're encountered from left to right, they are matched up as wires. Variables have to occur exactly twice because a wire needs to connect from one thing to another. So these two examples here are two examples of simple binary nodes where the auxiliary ports are connected to themselves, or connected to the same node's auxiliary port. Here's a more complex one where we have a constructor node, a duplicator node on the left. So you can see there's a duplicator node on the left. And then on the right of that duplicator node's auxiliary port is another constructor. And you can see the wires, if you just match up the X's and the Y's, they connect as they're shown in the graphical representation. The additional syntactic construct we need is to connect these trees through active pairs. The way this is done is a collection of active pairs. And so you have some main tree. In this case, it's just a wire, so a degenerate tree, and a collection of active pairs. Perhaps I should have written the BNF grammar here, but essentially you have an ampersand symbol, a term, tilde, term, and then perhaps an optional ampersand symbol with more term, tilde, terms. You have a collection of active pairs and the main tree that is going to be the port, the free port of the network. So here, this could be any variable. I'm just picking R. R is going to be the free port in the net. And we have one active pair here. On the right-hand side, we have a constructor node with two erasers connected to the R that ends up being the free port of the network. On the left-hand side, we have this other term that I've shown here. Does this make sense as a textual representation? It's very, perhaps, unintuitive, but go ahead. Correct. It's ampersand term, tilde term, ampersand term, tilde term. If you wanted to add another active pair, we would do ampersand and then some tree interacting with some other tree. Cool. Yes, so the networks that we're concerned with, and they take this shape in general, which is some free port connected to a tree, and then a collection of active pairs, and they're wired up in some way, right? And so every network that you're going to be able to assign to an identifier in HVM syntax has a free port, because that's what you're going to use to, if you apply that identifier to another one, if you, essentially like, if you imagine, exactly, you need a way to interface with other networks and to compose them. And so you need this free port.
But that also means that like, of course, that thing can only be connected, only one end of this can be connected internally. So
Yes.
Like it's somewhat redundant because you could figure out that what is the one variable that, or one wire that only.
Yes.
Okay, then it makes sense. Okay, thank you.
The reason we want the free ports, though, is because we're going to assign them to identifiers, which is another extension we have. You can name the networks. One of the key points of being able to name your networks with identifiers is the fact that this introduces laziness. You can have a self-referential network, which is not representable in like the vanilla interaction nets, because you basically have an infinite network. As Nicholas mentioned, the environment we're working with here is complete like strict evaluation. Any active pair that exists will be reduced. It doesn't matter if it's connected to the main program or not. And so this allows you to introduce laziness. It's essentially deferred computation until this reference is interacted with. It will not be evaluated. So.
Can we understand the ampersand as a binder, like it's binding the variable R?
No, the ampersand is just prefacing a reducible expression. So. Yeah.
You have an array of things that you can execute, right? And the ampersand is like adding a new entry to this array of executables.
It's kind of like a comma. Yeah.
Okay.
if you have variables on the left-hand side of the ampersand, or let's say, like, for example, the R wasn't referenced on this right-hand side here, that would be sort of a net with two disconnected components, which doesn't make much sense. And so the idea is you're going to end up connecting the different parts of the network through these variables. Please. Sorry? Yes.
So ID is lambda x dot x.
No. ID is, this is all HVM syntax. So this is a constructor node with its auxiliary ports connected to itself, which is what's represented up there. Unfortunately, it also, if you were to write like a lambda calculus syntax, this looks like.
We don't care about lambda anymore. Well, now this is a graph. Like, forget about lambda. Right? Like, this is now.
It's just a graph. So I mean, how am I supposed to make sense of? I mean, I can't use any of my lambda calculus intuition to evaluate this.
Yeah. That is an unfortunate I mean, we're faced with a task of being able to textually represent a graph that can have wires connecting very distant portions, right? And so we need these variables to connect those distant portions. Unfortunately, if the variables are very close to each other, yes, this also looks like a lambda calculus term. But what I hope is somewhat clear is the grouping operators form a node, and they have two arguments, which is the left port and the right port. And the variables, the names themselves, just like in a lambda abstraction, don't really matter except with the other variable it's paired with. So this x is just saying as soon as you see another x, connect the wire together. And so it represents that node up there, which has two auxiliary ports that they're connected to each other. This iter reference here is that term over there, which again is a constructor node with a duplicator node on the left auxiliary port and a constructor node on the right auxiliary port of that duplicator node. And this term here perhaps is the most confusing among the already confusing terms. Essentially what it's saying is the main network is identified by some free port, which we're going to give a name, and a collection of active pairs. The active pairs are going to be this constructor node, which is this one here, whose left auxiliary port is connected to a reference, whose right auxiliary port is connected to R, which is this variable here. So again, this is the free port of the reference. And it's interacting with a reference node. And so that's why this is connected to the principal port here. Okay, any questions? So this is the first extension of the interaction combinators where we have references. The second extension is, yeah, no, go ahead.
Because you just said something that's interesting. So you said references. So when you write, like, it's not grafting the net or like the identity net. It's not grafted into the main net. It really is just by reference. Like, is it just a textual shorthand?
It's a new kind of node. So previously when I introduced these, we had three kinds of nodes. We had two binary nodes, the constructor and the duplicator, and we had an eraser. This is a new node with no auxiliary ports. And it's a node that...
It's not just grafting.
Yes.
It's not like, I don't know what the right word would be. It's not macrosemantics, basically.
No, it's a new node in the interaction nets, exactly. And it's a node with no auxiliary ports. Okay. And so we now, in some sense, have like a family of nodes because references that have different names are different kinds of nodes.
So when this reference node interacts with something else, the result is that you copy this reference net. So you can have like this collapsed view of the network as a reference, and then it's only expanded when you actually interact with something.
And the copy is not atomic, right? It's like an actual deep copy.
Yeah.
Yeah.
So in the text representation, if I wrote like at main, it would replace where I put at main with the free port R.
Only if it's interacted with. Only if it ends up being on like the left-hand side or the right-hand side of a reducible expression are they expanded.
I have a question about the variables. So the semantics here is that the variables on, like, let's say at ID, it mentions x, and at iter it also mentions x. Those are completely
Yeah. So variables are first scoped to references, and so you can't have like one variable in one reference refer to a variable in another reference. That's already not possible. And they're paired up, just reading left to right. So when you see an x, the next time you see an x, we're going to increment some variable counter, and that's like variable 1. If we see, go ahead.
Essentially, there is a binder, like the reference itself binds all the variables.
Yes, but yeah, but if you see x like 4 times, then it's just the first 2 x's are paired, the second 2 x's are paired. Cool. So this is the first extension. Again, we're adding a new family of nodes, which are reference nodes, and we're adding some rules, which Nicholas alluded to, which is if you ever interact with a reference node, you do a complete copy of what that reference refers to. This extension adds like numeric primitives, and this is, as it perhaps is obvious here, the most complicated extension. The actual details, I mean, they're detailed in the paper if you want to see them. The intent here is to be able to have a node that represents a number, and additionally be able to do operations on those numbers, like the operations we're familiar with, like addition, division, multiplication, etc. There's a few immediate problems with this. One, our ports, or our nodes have 3 ports, right? There's a principal port and 2 auxiliary ports, and so you have to store the operation somewhere. And you have to additionally have the result of the computation exit somewhere. So there's a few immediate, perhaps, options, right? You could have 1 node per operation. You could have a multiplication node, a division node, et cetera. Unfortunately, because of the constraints of the environment we're working with, which I'll explain a little bit later, we have exhausted all of the space we have to represent nodes. And so we cannot store, at least not in a binary node, we cannot store additional information. So the route that we have gone with, which is kind of nuts, is the numbers themselves will store the operation. The numbers are typed, and so you can imagine a 24-bit, or like you can imagine some like bit string of numbers where 3 bits are reserved for a tag, so a 32-bit number, a 29-bit value, and the low 3 bits are reserved for essentially describing if it's an int, a float, or unsigned. We can also use those bits to store operations. And so essentially what ends up happening is numbers end up storing, they end up becoming partially applied, right? When a number encounters an operation, it replaces its type with that operation, and now you have essentially this untyped number that's like partially divided, and when it encounters another number, it'll encounter a typed number, and you'll know what the type of both numbers should be, what operation it should be, and what the result should be. Yeah, we have rules which are not displayed up here, which again are in the paper, that order, like we'll swap the order of the numbers if you have the operating number on one side when it really should be on the other. But yes, one number will carry the operation, the other will carry the type. And additionally, what we wanted to add as well is case matching. We wanted to add like conditional execution. If a number is 0, sort of reduced to one thing. If a number is something else, reduced to another thing. This essentially captures that. The structure of this reduction perhaps does not seem obvious, or like doesn't make any sense really. It's quite convoluted, but the idea essentially is that x is going to carry a pair or a tuple where if n is 0, we're going to erase one side of x. If n is greater than 0, we're going to erase another side of x. That's the intuition behind this reduction. The details aren't that important, but the idea, again, is that we're able to represent numbers in a primitive way.
So this breaks from sequence,
Sorry?
This breaks from sequence, doesn't it?
No.
It does if you pass something that is not a number.
Okay.
And then we...
Sure.
By construction of our programs, we ensure that they are like type correct, and then the properties of your system remain. But these are not like actual interaction net rules.
Okay, I see. Yeah, no, sorry. But the thing is, you're erasing one side of it.
Say it again?
You're erasing one side of it, right?
We're erasing one side of x in one branch and another side of x in another branch.
But you're still computing that side that you're erasing.
If it has any active pairs, it will be reduced, yes.
Okay.
Yeah. Again, you can refer to the paper for this exact same diagram. This is just the encoding of the interaction net rules with our extensions, but on top of the textual syntax. So these are like the interaction net rules, instead of written graphically, they're written as a rewrite system on top of the textual syntax. Yeah. Okay, so this will go to, this is sort of what I was alluding to earlier about the memory constraints of our, the design of our evaluator. I guess before I go into the details, I'll preface this with the fact that like the limiting factor, one of the limiting factors is the fact that we need 64-bit atomics to do certain operations, essentially to ensure that that there's no like thread contention, because the reducible expressions are stored as 64-bit values, and when you want a thread to work on a reducible expression, you want that thread to atomically grab it. The memory layout that the HBM2 uses is we have a list of nodes and a list of reducible expressions. The nodes themselves don't know what their type is. They just know what their auxiliary ports are connected to. A node's type really only matters anyways when it's going to be as part of a reducible expression. And you can see in the reducible expressions here, they contain the type of the nodes. So this memory layout is meant to represent this interaction net here. We don't have to go through all of it in detail, but you can see here in the red X bag, we have a constructor node at index 2. What this essentially is saying is that this red X is interacting two constructor nodes, the second and the third one. So these two nodes are interacting, and you can see BA is interacting with XY eraser, and that is what's represented down there. Some other consequences, since the ports are storing the types of nodes, they need a tag. We have 8 nodes, and so 3-bit tag. That means that they have a 29-bit value, which means that since ports store the sort of address of the node, that gives us a 29-bit address space, which is 4 gigabytes worth. And so if you have a GPU with a lot of space, we can't utilize all of it, which is unfortunate. Ports, additionally, for nilary nodes, nodes that have no auxiliary ports, they store the node like in line. For example, here, the node, this is a reference node to the first reference, which is the only one in the program, which is foo, for example. Yeah, this is the memory layout that we have gone with. This is 2 components of the memory layout, at least. The main sort of contribution and insight of this that allows us to scale the evaluator onto a GPU, which runs like 16,000 threads, is the fact that the linker is lock-free. Let me back up real quick. One interaction we have, which is not at all present in the graphical representation, is essentially like substituting variables, right? You have these variables in the graph, and if you go and interact with a variable, you need to sort of see or replace that occurrence of that variable with the actual term that it's connected to. And so we need a mechanism for essentially, if you have 2 reducible expressions that are making use of some variable, eventually we need this node to interact with this node here. The way essentially this works is an atomic map. The first time the variable is encountered, it's inserted into the map. And since we know the variables occur only twice, the next time that variable is seen, it will be retrieved from the map. And now that second thread that had access to the variable will have access to both of the nodes and will appropriately push that reducible expression to the stack of reducible expressions that's getting worked on by the other threads. Again, because this extraordinarily heavily relies on the fact that, or whatever the maximum width atomic integer support the platform has, that is what allows us to sort of have nodes of different sizes. The reason we chose 64 bits, like I mentioned, is not all GPUs have 128-bit atomics. Not all GPUs have 64-bit atomics either. But that felt like a good enough compromise given the fact that we'd have to give up a lot of addressing space already to go just on 64-bit nodes. Yeah, go ahead.
Do you ever get the scenario where one node encounters the first occurrence of X, and then one thread encounters the first occurrence of X, and then the second one encounters the second? Like, how do you stop that from causing problems? Because do you need to...
Sure. So because the map that's sort of holding the variable substitutions is a map of atomic integers, one thread will insert the node into the substitution map first. Variables are just indexes into an array. And so some thread will insert this node essentially into, if R is the 5th variable, it'll insert this node into the 5th position of the array. This second thread will go and do a swap. It'll insert this, this node into the substitution map. If it receives something, essentially, if what it got, this is pseudocode, of course, but if it receives something back from the map that was already, that means something was already there, some previous thread had already inserted it, then the current thread actually has ownership over both nodes, and it can go and take it back out and interact both of those nodes. Does that make sense? The second thread, if it attempts to insert another node and it sees that it didn't get a 0 value back, it knows that it has ownership over both of them, and it can go and retrieve that node it just inserted and push that redex into the stack. Yeah, so as I've been mentioning, right, the atomic operation support limits the addressing space. 64-bit atomics imply 64-bit address space. The memory just isn't fully utilized. One additional sort of trick you can do to limit the amount of memory usage is the fact that annihilation deletes 2 nodes, so you reclaim memory, and commutation creates 2 nodes. And you can use that both to your advantage to share work and to reduce memory pressure, right? If you're running into memory limits, you should probably do as many annihilations as you can. When you're spinning up the interaction, though, you probably want to do as many commutations as you can so the threads can have work to do, because you know that work is going to be done anyways at some point. Yeah, this is essentially what I was saying earlier. The GPU is especially difficult to schedule work for. You have all these threads that want to go and operate on things, and ideally the threads are all taking the exact same execution paths. And so we have, specifically for the GPU, a mode for the runtime that does, it prioritizes commutations to grow essentially the bag of redexes. It'll switch to a work mode once it feels that the number of redexes has grown sufficiently. Additionally, because of the sort of hardware structure of a GPU, threads are in blocks that can share memory. And so threads will share memory with the block of threads that they're a part of. However, you really want to share work sort of globally. And so periodically, what we'll do is we'll take the entire bag of redexes and do like a transpose, essentially shuffling all the redexes together, and now GPU threads will look at a totally different set of redexes than they were looking at before. This is, again, just one of the example strategies we have to unfortunately do due to the platform sort of specific architecture. One of the things we're lacking, in my opinion, is some benchmarks, but for the paper, I essentially benchmarked HBM2 with itself. Ideally, we'd also have comparisons with other platforms, but the main thing that I find interesting here is the fact that we have a single language that can run on both the CPU and on the GPU. Obviously, you get the same results, and we can immediately see that the GPU, just by nature of having more threads, will execute these computations much faster. The specifics of these operations are essentially just sorting like these large trees or lists, or summing across a tree. Of course, these computations have like a closed form. If you sum a tree of like some integers that are computed based on where it is on the tree of this size and this breadth, of course that's like a single number, and so a compiler that knows what the value of that operation is could just return that, and that could be a program that has the same sort of semantics as this that obviously is much faster. But the point is that we have an interaction combinator evaluator that the design is the same both for a GPU and for the CPU, and it just runs faster when it has access to more threads. Yeah, so in conclusion, there's a few things I want to mention. We're also in the process of developing like a higher level language that is meant to compile down to HVM. Here's an example like Fibonacci program, and here's the example compilation of HVM. They coincidentally fit on the same page. And we think this is an interesting sort of avenue to explore for other higher level languages or to be transpiled to HVM, especially for like pure functions. And the primary selling point is the fact that we have this sort of hardware architecture agnostic runtime. Yeah, go ahead.
I assume in this language, like the whole point of having this
Sorry, say that again. The whole point of...
So, you know, like 30 slides before, there was this remark that there is only a certain subset of lambda terms that can be turned into regression.
Yes.
Yeah, so my question, or I would hope that if you have your own language, like mine will have a different language, the only reason I can see for that is if you can tell from a banned program entity whether it is translatable, whether there, and if there are ways of managing that problem when you're writing a banned program, because otherwise, so what does it give you, like, yeah.
Okay, so if I understand your question, yeah, not all sort of terms in, let's say, Python or some other high-level language can immediately be encoded into this because of the reasons we talked about earlier about it not soundly evaluating all lambda calculus terms, right? There's a few avenues for this. You could have, in the case of Python, a decorator that does the syntactic checks necessary, right, for that compilation. But you're right, it's not sort of like a target for every language or for every program. Like it's not sensible to evaluate many, many terms.
But that's not my question. My question is that the problem that having your own surface language solves? Or like why do you need...
Why do we need a surface language?
Yeah, why does it...
Sure, that's a good question. As a proof of concept for transpiling a higher level language, right? Because we can't sort of, hello, everyone that wants like to program, please write your programs in HVM seems unreasonable to request.
You start from 4, you start from GC4, right? And then you would have something that works for all.
Ben does have, it does a lot of transformations to make like regular, functional lambda programs work with HVM, making sure that things are linear and etc. As far as we know, there is no like specific characterization of every program that can be safely executed in this way. But we know that there are some subsets of lambda calculus terms that are.
And so is Ben like circumscribing that safe subset?
Not yet, but that's like the next step. We already know like exactly the things that we want to implement. We can have a type checker that can make sure that your term is actually sound lambda.
Yeah.
So do you have a specification of the type system? What is the type system?
So the thing that we planning on implementing is elementary affine logic, and that's like a subset of terms that can be reduced in elementary complexity. And we know there are proofs that all of those terms are safely soundly reducing under this algorithm.
So very briefly, could you reprise? So you given the definition of an affine function is.
Mm-hmm.
So what's the elementary kind of tool?
Elementary, I mean the affine.
So that's left, so maybe we can make the questions also.
Sure. I'll just give the very last page then, and then we'll just go right to questions. But the future stuff we want to do, like we've been mentioning, is an interaction type interaction at type system is sort of like something we haven't seen much literature on outside of polarization. Lazy mode was something that was present in HVM1, but now due to the extreme eagerness of HVM2 is no longer present, which prevents like optimal evaluation for the subset of lambda terms we're targeting. Writing a bunch of custom runtimes is annoying if we want to change the specification, and now you have sort of 4 runtimes, 1 for C, 1 for CUDA, 1 for metal. And if you change the specification, we want to have to manage all those code bases. We're exploring the idea of sort of having a DSL that will generate these runtimes. And additionally, we want to formalize HVM's design and semantics as we don't have sort of a formal definition of HVM. That's the entire presentation, so we can go back to that question, which was about elementary affine logic.
Yeah, but actually before that, you kept referring to a paper. No, you go to the last slide because there's no link to the paper in the ICFP website. Is that the link?
Yes. It should be on the website. I'm not sure why it's not on there. I'll contact Mike about that and ask why it's not. Oh, the slides are definitely not on there because I was writing them moments ago. But yeah,
I think that is something that we might explore, but basically the general rule was that these papers are not officially published and therefore they don't want this to be publicly available.
Oh, the paper should not be publicly available? The extended abstracts as well?
Yeah, this is just for the,
Oh, okay.
papers have been published at the
I see.
library, but the abstracts are not available for that reason.
I see what you mean. Okay.
So what we can do is we can ask them whether we can provide, for example, pointers to archive or something like that.
Okay, understood.
But if you go to the HBM repository, you have drafts of a paper.
Yeah. I want to answer his question first, if that's okay. You had a question about elementary affine logic. So elementary like terms is a like complexity class, right? It's like the union of all exponential time hierarchies, and so that's elementary time. Elementary affine logic is a type system that you can ascribe on top of lambda calculus that's inferable, and will, like the simply typed lambda calculus, will restrict the terms that you admit. And similar to linear logic, right? It sort of it checks like linearity, but it's slightly different than just the vanilla linear logic.
You can have like some bounded amount of applications, or I mean, in their case they use
basically you can statically, like you can statically.
Yeah, you can statically determine like how much of these applications, and you have
Constant bound on.
Yeah.
constant bound, and you know that they don't like interact with each other because they're kind of layered in different.
Okay.
Because the linear logic alone is too restrictive, right? The linear lambda calculus is like complete, it always terminates. And so it's not Turing complete.
What about elementary affine logics? I guess it's not Turing complete either, right?
But with the references we have, it can be, because it like defers execution, it lets self-reference, it allows for loops. You had a question. Yes?
I was going to ask, the addressing space means that you can only have 4 gigabytes of memory. Is that 4 gigabytes of memory per GPU or per concurrent HBM2 program? Like if I have a
Per program.
So I can get a 64 gigabyte graphics card and just put like 16 concurrent HBM2 programs.
But they can't communicate with each other. They,
yeah.
Correct. You said we were almost up on time. I'm not sure.
I guess there's one more question.
Okay.
Sorry, can I ask about
Please.
the memory encoding you had? Right, so that was informed by the limitations of the architectures you're targeting. Right, you're trying to back it into like.
Yes, that's definitely definitely an influence.
So if that wasn't the case, I'm wondering what would change for you. So like maybe the encoding of the integer primitives.
Yes, great question. Yeah, 100%. Yes.
Does that give you like better performance, or is it just?
We can do many things. We can, at a minimum, increase the addressing space. Additionally, like you said, the integers right now are 24-bit. They would be 60-bit, I think, right?